Hi, folks. Just a quick note. If there are press reporters in the audience, we've got reserved seating for you in the front, so please come forward. If there are any reporters, please come forward right here in the front. We've got spots for you, so come on down. Thank you.
Hello, everyone. I'm Wolf. I am the technical lead for developer relations for machine learning here at Google. We're going to get the live stream started in just a minute, but for all of you here, we wanted to go over a couple of things. We have a great show, don't worry. But first, we wanted to say that this is an inclusive community. We want everyone to have the best experience possible at the TensorFlow Dev Summit. No matter your experience or background, you're welcome here. We encourage you to be excellent to one another and say hi to new faces, build on one another's ideas, and report any uncomfortable experiences. We have a zero tolerance policy for harassment of any kind, and our full code of conduct is posted around the venue and on the event website. Please share your positive and constructive feedback with anyone here. We're all wearing these cool t-shirts. We have orange ones for speakers and engineers, and we have gray ones for staff. Also, in case of emergency, there are exits behind you and to either side. In case of emergency, your nearest exit may be behind you. All right, let's get this thing started.
Hello, everyone, and welcome to the 2017 TensorFlow Developer Summit. I'm Zach Stone. I'm the product manager for TensorFlow on the Google Brain team, and I'm delighted to see all of you here today. I know several of you have traveled great distances in order to be here. Thank you very much. I'd also like to welcome everyone who's tuning in via the live stream, whether from home, from the office, or from the more than 60 events that Googlers and Google developer groups have organized around the world. Welcome to all of our remote viewers. We have a fantastic program organized for you today, including some exciting announcements and several special guests. It's my pleasure to introduce our keynote speakers, Jeff Dean, Rajat Manga, and Megan Kacholia. Jeff will speak first. Jeff Dean is a world-famous computer scientist. He's a Google Senior Fellow, and he's the leader of the Google Brain team. Without further ado, please join me in welcoming Jeff Dean to the stage.
All right, thanks, Zach. And thank you all for coming, and welcome to everyone on the live stream. We're really excited about the TensorFlow Developer Summit. So when we open sourced TensorFlow about a little bit more than a year ago, we really were hoping to build a machine learning platform for everyone in the world. It's very clear that machine learning is going to be incredibly important across many different kinds of applications and problem domains, across many fields of science, across many industries. And we wanted to build an open source platform that everyone could share and could contribute to, that was fast, flexible, and production ready. And that's really the kind of three mantras that we've been working towards as we continue to evolve TensorFlow. But first, a bit of history. So our group has been doing deep learning research for about five and a half years. And the first system we built was called Disbelief. And this was a system that worked well for us in our early work in this area. So we published a paper about disbelief in NIPS 2012 that was well received. Disbelief had a lot of really nice properties. It was very scalable, so we could train models on very large numbers of computers. We could train very large, powerful models. We did a lot of interesting work with that, and so did other people at Google, including some of the early inception image work, a lot of work with our speech recognition team to improve our speech recognition systems, work with our search team to improve our search ranking system by deploying neural nets in the middle of the search stack. But ultimately, we realized that disbelief was not really exactly what we wanted as we got more experience with applying these kinds of problems. It was designed for CPUs because that's what we had in our data centers when we first started this work. GPU support was added later, but it was kind of bolted onto the side. It wasn't really thought through as much as we would have liked. And the system worked really well if what you wanted to express worked in the programming model that Disbelief had. But if you wanted to do something a little bit outside of what it was originally designed for, it was a little bit hard, especially for research purposes. So what we wanted to do with TensorFlow is take a step back and redesign what we had with Disbelief and keep the nice properties of Disbelief, but make it more flexible and more general purpose. And so TensorFlow really takes the scalable properties that Disbelief had and the production readiness, but then extends it to be much more flexible for research. And so we really want to span this whole continuum of really flexible ideas and then being able to take those ideas and put them all the way into production without having to go into a new kind of system. So that's why we built TensorFlow, and we wanted to open source it so that everyone in the world could actually use it. We also felt it was really important to support many platforms. Disbelief was really designed mostly for data center applications, but obviously mobile platforms are really important. Being able to run workloads on CPUs and GPUs and custom accelerators like TPUs that Google has and that other startup companies and large companies are developing in this space as machine learning acceleration becomes more important. And running on a variety of mobile platforms, so Android and iOS support and Raspberry Pi support have been added to TensorFlow because we want to be able to take models and run them wherever machine learning needs occur. And we also want to be able to run on cloud platforms. So you can run this on Google Cloud or other cloud systems using TensorFlow running in raw VMs. Google Cloud also has a high-level cloud machine learning service that is more of a managed service where you can run TensorFlow. And so TensorFlow works really well on Google Cloud as well. And we wanted to add support for other languages. So we came out, when we initially released the TensorFlow, we had Python and C++ support. And over time, we and others in the community have added other language bindings and other higher level language support so that different languages can access the power of TensorFlow. We've also worked pretty hard on making it so that we can have good visualization tools and sort of monitoring tools for machine learning training and inference so that you can really understand what it is your models are doing. Really getting a good sense of what's happening in those processes allows researchers to be more productive and to really dive into what's going on. So we've had a lot of progress to date, so I'll just highlight some of it. So the area to the left is kind of mostly our Disbelief system, and we use that for a variety of different things. But you can really see within Google that as we release TensorFlow internally and then eventually as an open source product, that we've been able to have many, many more people and more teams at Google use machine learning and use TensorFlow to improve both our products, so it's integrated into many features in search and Gmail and Translate and Maps and many other things, but also to use it for research use. So we've done hundreds of projects that use TensorFlow, published hundreds of papers using TensorFlow as the basis for our machine learning research. And it's also now the #1 repository in machine learning category on GitHub. So we're pretty excited about that. It's been really well received in the external community. And you can see that TensorFlow adoption has really accelerated quite quickly. And I think that's testament to the community that we've started to build and are continuing to build, where lots of people are contributing to TensorFlow and using it for all kinds of interesting and innovative ways. We have almost 500 non-Google contributors have contributed code to TensorFlow. We have about 1,000 commits per month in the source code base. Many people outside in the community have created tutorials and other kinds of model implementations in TensorFlow, translations of the documentation, interesting projects. There's about 5,500 GitHub repositories now with TensorFlow in the title, only 4 or 5 of which are the official repositories. And we've had a lot of direct engagement with this community by answering questions on Stack Overflow, dealing with issue and feature requests that people have submitted. And one of the things we're really happy to see is that the use in machine learning classes is starting to happen in different universities. So Toronto, Berkeley, and Stanford, for example, are all using TensorFlow as the basis of important machine learning classes in their curriculum. Since we launched, we've been adding features and working with the community to understand what features are really important that they want to see. And just to highlight a few, distributed TensorFlow, distributed training support was added a few months after our initial launch. Various high-level APIs have been added so that people can more easily express the kinds of models they want without having to necessarily specify things at a very low level. Things like TensorFlow Slim. We've added Windows support and, for example, HDFS support, support for CUDA 8 and CUDA-NN many, many things here that the community has been asking for have made it into different releases. We've kept up about a release every couple months cadence, minor release. And all of this has happened in just over a year. So this is pretty amazing. This community is really vibrant and thriving. I'm really excited to be part of a big open source project. A lot of the work that I've done in Google in the past has been not open source projects, and it's really nice to see the external usage of the TensorFlow system and what people are doing with it. I'm going to invite Rajat Manga, our TensorFlow engineering lead, up to talk about what's new today. Thank you.
Thank you, Jeff. Thank you. Hello, everyone. So there are lots of amazing announcements today, and let's get started. Let me start with the first one and the most exciting one. Today, we are excited to announce TensorFlow 1.0. Woohoo! Jeff talked about a number of things that have come together to really get us to 1.0. And before I get into more of the things, the new things that we're announcing today, let's take a moment to just thank all the wonderful people who have made this happen. So kudos to an amazing team that's come together to make TensorFlow a great product. Thanks to all of you, the community, who's really gotten together. There are nearly 500 contributors, as Jeff mentioned, from outside Google who've contributed code back to TensorFlow. And there are many others on Stack Overflow and GitHub who are helping with issues and support and so on. So thank you all. Let's get started. Let's take a look at what's there in TensorFlow 1.0. It's fast. Performance has always been important to us. It's one of the things that's really helped deep learning get to where it is to give the great results that it's been getting. And today, with 1.0, we are showing a 58x speed up on 64 GPUs running the Inception v3, which is one of the great benchmarks for image performance. It's flexible. Jeff mentioned some of the high-level APIs. We are announcing even more. We want to make it easy for you to do all the things. TensorFlow's philosophy has always been to allow you to really give you the power to do whatever you want, but also make it easy, and this makes it even easier. And it's production ready. With 1.0 and semantic versioning that we follow, we're guaranteeing that we'll ensure backwards compatibility for all future changes. So as you get new versions and new features, you don't have to worry about breaking things. And many more, as some of the guests later will talk about. But let's take a look at some of these. Let's start with the high-level APIs. One of our goals has always been to bring machine learning to everyone. And these high-level APIs really make it easy, and hopefully we'll get to more people. So let's take a look at what they are. This is a picture that's probably familiar to a lot of you if you've been using TensorFlow. In the middle is the core distributed execution engine written in C++ for high performance. It abstracts away all the various kinds of devices, some of which Jeff showed earlier, like CPUs, GPUs, and so on, and does a great job at that. On top of it are the various languages, like the Python front end, the C++ front end, and again, many different languages that are being supported there. Now, today, we are announcing a number of APIs on top of the Python front end. The first one is layers. So these allow, really, if you're using deep learning models, to build fully connected convolutional pooling and all the standard layers that you come up with as pre-built components, so you don't have to really start making them from scratch. Again, making it easier for you. On top of that, Keras is an API that a lot of you are probably familiar with. It's pretty popular. And we are announcing the integration of Keras with TensorFlow and implementation to make it, again, easier to build those models. And an estimator API that really helps you take those models, combine them with your data sets, et cetera, make it easy for you to train and evaluate these models. And finally, on top of all of these, there are a number of models that are already there for you in the box for you. For example, linear regression, simple DNNs, and so on, that you can start with, that you can actually run on your code to train stuff with very few lines of code. Next up, so TensorFlow has always done great at deep learning, but we built the core to be really flexible to allow you to do all kinds of amazing things with it. And today we are announcing broad machine learning support with the help of many teams across Google and folks externally as well. So let's take a look at everything that we're doing. Of course, as with everything else, performance is important for these. So all of these implementations are pretty fast, and you can take advantage of them on a single machine or distributed in a cluster. If you're trying to do clustering, k-means is an obvious choice. So we have an implementation of k-means in TensorFlow for you. If you're doing classification, support vector machines are used often. And this might be a great place to start, especially if you have predefined features. But then going from there, if you want to, let's say, learn features or do something fancier, the same kind of APIs are there for you to try deep learning or other algorithms as well. We also have decision trees in random forests, again, for classification and regression. And many, many more. Ashish will be talking in more detail about these later today. Let's look at some new platforms and accelerators. Jeff showed a whole bunch of them that were there earlier. I'm just going to mention a few that we've added recently. TensorFlow is included in IBM's Power AI distribution. IBM announced this pretty recently. So if you're using IBM Power Systems for deep learning, now there's a software package that includes TensorFlow to give you high performance and the ease of use that you would like there. It's also supported by accelerators such as the Movidius Myriad 2 accelerator. This can be used for embedded platforms. So you can it takes a TensorFlow model and really allows you to run that efficiently on these chips. And most recently, there's been support for Qualcomm's Hexagon DSP. And to talk about that, I would like to welcome Travis Lanier, who's here with us from Qualcomm today. I would like to, Travis, please come on. So Travis is Senior Product Management Director at Qualcomm.
Thank you. We're very excited. We're very excited to have collaborated with Google to optimize TensorFlow for a Hexagon DSP. If you take a look at this little video we have looping up here, you can see about an 8x performance increase by moving it from the CPU to the DSP. And keep in mind, this is happening within a mobile phone's power profile. So this is very power efficient, really high power processing compared to what you've been able to see for these type of neural tasks on a mobile phone. Now, the good news is that we've already done the optimization for you. So if you have a TensorFlow model and you move it over, you should be able to see a similar type of performance uplift on our Hexagon DSP. We will be open sourcing this software, including the driver, and it'll be available on our Dragon Board 820 development platform. Thank you.
Thank you. Thanks. Thank you. Thank you, Travis. So Pete Warden will be talking in more detail about our support for mobile and embedded. It's clearly very, very important, and you can see more in his talk later today. So we care about performance in many ways. You've seen some of those areas. As you think of TensorFlow as a programming language as you're building these amazing models, what better way to look at performance than with compilation techniques? So today we are announcing XLA, which is an experimental TensorFlow compiler. It's really built for TensorFlow, so a compiler for TensorFlow. And it allows you, XLA stands for Accelerated Linear Algebra, basically accelerates the kinds of models you make with TensorFlow. It basically takes a graph and compiles that down to assembly code for the architecture that matters to you for the kind of chip that you're running. And it can be used for just-in-time compilation, for example, in training workloads, et cetera, whether in the data center or elsewhere. And also for ahead-of-time compilation, where it just takes the graphs, compiles it down to code, and then you can just ship the code and not worry about anything else. Again, Chris and Todd will be talking about it later this morning, so there's a lot more there. And with that, I would like to welcome Megan Kacholia, Engineering Director at Brain, and who's been leading our performance efforts to talk about TensorFlow in depth.
Thanks, Rajat. I want to start just by diving a bit more into performance. So as we've talked about, TensorFlow is really made for the community at large, and that spans a lot of different use cases, whether you're looking at things from the research perspective or thinking about just production environments and what that means. On the research side, being able to have performance improvements, get more and more performance out of TensorFlow and out of the machines you're using underneath it, gives you a lot of flexibility, whether it's you want to iterate more quickly, you want to train models faster, maybe you want to run more experiments in parallel. So it's very important for us to be able to continue to improve on performance to provide that flexibility on the research side. But we don't want to forget about the production side as well. And for production, there's, again, many different use cases, whether you're looking at large-scale server farms or also thinking about embedded use cases, like we've talked about, whether it's on device, right, running on a mobile device, or some other kind of smaller device that has a special setup. And again, even then, we're thinking about lots of different types of hardware, and low latency serving is also part of this. I think a lot of times people think of TensorFlow and they think of just the training perspective, but we've done a lot of work in open source things through our initial releases that provide ways of doing serving as well. And this is low latency serving that you can use in a production setup. But what good is it to talk about performance without actually looking at numbers? So this is just a little setup first. Let me explain some of this. So what we're looking at here is we have revised our implementation of the Inception v3 model, and we're currently working on open sourcing that, and we'll have that out in a few weeks. But all of the graphs shown here are using that model under the covers. And then we're looking across 2 different machine types. So we've done some benchmarking on the NVIDIA DGX1, a very, very powerful machine, so that we can see how TensorFlow really scales when you're using much, much faster GPUs. And also looking at K80s, since those are much more widely available, especially in all the various cloud computing platforms that are out there. And this is just the ideal scaling. So let's see how TensorFlow stacks up. So the first thing we're looking at is, again, looking at with training this Inception v3 model with synthetic data. I think the really cool thing to call out here is that even when you're moving from a K80 to a much more powerful machine like the DGX1, you're still seeing impressive scaling numbers across the 8 GPUs that we're showing here. But it's not good to just look at synthetic data. I know that's what is generally used for benchmarking in the industry, but we also want to understand how do things actually perform with real data, since that's what I'm assuming people are actually using for building their models and running their production setup and doing their research. So let's plop that in there as well. Now, you can see even when you move from synthetic data to real data, the scaling is still very impressive. And TensorFlow is scaling well across the 8 GPUs here, whether you're looking at a powerful DGX1 setup or you're looking at something like a K80 as well. But it's not just about these single machine setups. We also need to think about distributed performance. And for distributed performance as well, we've been doing a lot of work to improve that and improve our scaling to make sure that, again, whatever machinery you have and that you want to be using, TensorFlow can make the use of it, make the most use of it, and be able to give you whatever benefits and flexibility you need. So here we're showing a 58x speed up across 64 GPUs. This is the number that Rajat quoted as well when we were talking about the TensorFlow 1.0 release. So I think it's really exciting, just all of the improvements that we've made on the performance side of things and all the flexibility and the options that it gives back to the community. Now I want to go just a little bit into kind of examples on the research and the production side of things. So neural machine translation is a common example we've talked about a lot. So here you can see with the old phrase-based model, which actually had hundreds of thousands of lines of hand-tuned code. When we move that to a neural model in TensorFlow, we're actually able to see huge improvements across various language pairs, in some cases reducing errors by up to 85%. Here's a slightly more fun example. It's a little interesting to look at this graph, but this is neural architecture search, where you're essentially building a neural network in TensorFlow that can figure out what is the right under-the-covers neural architecture to use for solving a problem. And it's great to see these cutting-edge research cases also being done in TensorFlow. And here's another example that has been open sourced and by Google Research. So looking at things like captioning images. And it's not just about providing a caption for it, it's providing a human-sounding caption for it. So it's very impressive to combine this type of language understanding and also applying that with the images and doing that in TensorFlow. But again, it's not just about research. We also need to look at different types of production use cases as well. And it's important to, again, remember that TensorFlow, when we talk about production use cases, we're talking about both the training side of things and also using TensorFlow for low latency serving. A cool example here is something like word lens. So this is something where a lot of times when people think about production use cases, they think about large data centers. But a lot of production use cases these days are actually apps, right? You release an app, it's actually running on someone's device. So here's an example with word lens, where it's combining translation and vision, essentially, and actually running on the device using TensorFlow to be able to provide you what that sign might look like in a different language. And of course, at Google, we make a lot of use of TensorFlow and deep learning. So we talked about Translate a lot. There are other examples like using it in Gmail for spam detection, using it in Street View for understanding like signs, street sign recognition, and also using it in perhaps the Google Play Store for app recommendations. But while it's great that there's so many use cases internally at Google, that's not really the whole point of TensorFlow. The point of TensorFlow is to figure out how can we give this back to the community and make it so that everyone can be making use of deep learning and be able to use TensorFlow to further whether it's the research or their production needs. So it's great to have such a large list of companies that are actually making use of TensorFlow as well. So we've already heard from Qualcomm stepping up. There'll be other things that are be mentioned throughout the day as well. But we really want to make sure we're engaging with the community, understanding what the needs are, so that over time, this list of other folks who are using TensorFlow in their own use cases will continue to grow. And with that, I'd like to hand it back off to Jeff to talk a bit more about what's ahead.
Okay, thank you, Megan. So I think one of the things that's great about the community is that TensorFlow is really for everyone. And some of the things that people have done with TensorFlow are things that we would never have thought of, because really people have their own problems and they're using TensorFlow in very creative ways. So you may have seen this story a few months ago of this Japanese cucumber farmer and his wife and their son, who happens to be an automotive embedded systems engineer. And every harvest season, the wife would spend a lot of time sorting cucumbers, because you need to sort them for market into like big ones, small ones, curved ones, not curved ones. And so they rigged up a system using a Raspberry Pi and a camera and TensorFlow to essentially sort the cucumbers automatically into the right shapes. And so this is a creative use of TensorFlow that we would not have thought of. It's really cool that people are finding really neat uses for it. And now there's not a lot of human labor that needs to be done to sort these cucumbers, which doesn't sound like a very interesting task. Another area we're really excited about is the applications of machine learning for medicine. And our group has been doing some work on the diagnosis of diabetic retinopathy using computer vision. And so the task here is essentially to take a retinal image like this. You go to the ophthalmologist, they typically take an image like this, and then the ophthalmologist looks at this to see if there are any signs of early signs of diabetic retinopathy. And this is really important, because if you catch this disease early enough, it's very treatable. But if you don't, it's actually the leading cause of blindness in the world. And so we now have a system that was published in an article that was published in the Journal of the American Medical Association by people in our group, that shows that a computer vision model trained on the right kind of data can actually be as good or slightly better than the median ophthalmologist at diagnosing diabetic retinopathy. And this is really important, because in many parts of the world, and what's really lacking is access to ophthalmologists to actually interpret the images. And so this can really help increase access. There's other uses in medicine as well. So I'd like to invite Brett Coprell from Stanford. He's a Stanford PhD student in the EE department, and he's been doing some really nice work on dermatology assessment with the computer vision models. Thanks, Brett.
Hi, everyone. I'm Brett Coprell. My colleagues and I at Stanford have trained a model using TensorFlow to classify images of dangerous skin lesions. We're thrilled to have achieved dermatologist-level performance at recognizing melanoma and other types of skin cancer. At a sensitivity of 98%, we're 90% specific. I look forward to sharing the details with you during my talk later today. And if you have a copy of Nature, I'm happy to sign it.
Very good.
Thanks,
All
Jeff.
right, thank you. Thank you, Brett. Yeah. The cover article in Nature is like kind of a really pillar of achievement in the field of science. So this is really fantastic work. And we actually had a corkboard outside the venue here today to talk about other kinds of creative uses that people are doing for TensorFlow, and I just picked a couple. So there's, continuing on the medical theme, one group is doing classification and clustering of MRI-based brain networks to diagnose psychiatric disorders and plan treatment. So that's pretty cool. And another one is doing a painting robot, which sounds pretty cool also. So I think it's just really nice to see all the creative uses that the community is making for putting TensorFlow to use in solving their problems, and also that the community is contributing to improving the base core TensorFlow. So we're really excited to have everyone here, both in person and on the live stream for our first TensorFlow Dev Summit. And we want to see all the amazing things that you guys can do with TensorFlow. So thank you very much.
It's been just over a year since we open-sourced TensorFlow, and we've been thrilled to see the adoption by the community and the pace of development both here at Google and all around the world.
TensorFlow is really the primary tool that we're using for a lot of our machine learning work in all of our products. Towards the end of last year, we actually rolled out a completely new translation system that was based on deep neural nets. In Gmail, we were actually able to roll out a TensorFlow model that, by understanding the context of the message you just received, we can predict likely replies. And this is a feature we call Smart Reply.
Diabetic retinopathy is the fastest growing cause of blindness. It's a complication of diabetes. We gathered a very large data set and had doctors grade the images. And then we, using TensorFlow, trained a neural net that does a pretty good job of predicting whether or not there is diabetic retinopathy in the image.
Can we use something like TensorFlow to make music, to make art, and to allow us to communicate better with each other? With TensorFlow, we're able to think abstractly, almost at a level of like improvisation with machine learning. We're able to try new things, to chunk models together in ways that were impossible before we had that kind of expressivity.
Dugongs are classed as vulnerable to extinction globally, so we do a lot of aerial surveys using drones. Then once you've done a survey of a really large area, you end up with tens, if not hundreds of thousands of photos. The goal was to find a way to automate that whole process, and that's where we've been using TensorFlow.
One of the things that we've been focusing on this year with TensorFlow is performance. We've been especially excited to release support for distributed training.
We want to make it easier for people to use so they don't have to necessarily know all of the underlying internals in order to get the distributed performance the best it can be. XLA is something that can compile down TensorFlow. Maybe you want to compile your graph ahead of time and get it down to something much more compact in terms of memory size, so that way you can easily load it and execute it on something that might not have as much storage space, like a mobile phone or some other portable, smaller device.
When we introduced the Hexagon Vector extensions, what we had in mind was enhancing user experiences with imaging features.
So the TensorFlow team said that you only needed low precision multiplies to be able to execute these neural networks efficiently. So we did some tests, and on the same graph, Inception v3, we were 8 times faster and 4 times lower power than running on the CPUs.
TensorFlow is great to work with, easy to work with, lots of capability. And so our engineering teams and their engineering teams working together, we were able to do something very exciting. This is just the beginning of what will end up being a long evolution of some great things we can do with machine learning and image processing.
In addition to sharing TensorFlow, Google has also shared an ecosystem of tools, which contains everything you need to go all the way from research to production. One such tool is TensorFlow Serving, and this is an open source, high performance serving solution. Another great tool, which is actually quite beautiful, is the embedding visualizer. And you can use the embedding visualizer to interactively explore high dimensional data sets. On the education side, General Assembly has done great work teaching TensorFlow.
For my final project, I was really interested in doing lyrics generation, and TensorFlow was a really great match for that because it allowed me to build out and utilize the models that I needed to be successful.
The TensorFlow community is thriving around the world, and we're excited about as many people as possible being part of it. TensorFlow is an open source project for everyone. We're looking forward to building this into something even better and more useful and more powerful in collaboration with the whole worldwide community.
Well, that was really cool. So I'm Wolf. I'm the TensorFlow technical lead for developer relations. And we have a great show for you coming up. We have over a dozen different speakers talking about everything from distribution, scaling, serving, mobile, and applications like medicine and art. But our very first talk is going to be about XLA, the new TensorFlow compiler. And to talk about that, we have Chris Leary, who's an engineer on the compilers team. Chris, you want to join us?
Thanks, Wolf.
All right, good luck.
Hello, everybody. I'm Chris Leary. I'm a compiler engineer at Google, and I'm here today to tell you that we can compile TensorFlow, which is super exciting. And we have documentation about how you can compile TensorFlow. And we have open source documentation about the open source compiler that you can compile open source TensorFlow with. So, as the ancient proverb says, it takes a village to raise a compiler. And many people have been involved in the development of XLA. I'm up here speaking about XLA, but we've had a lot of contributions, and we look forward to a lot more community involvement and community contributions now that it's in the open source. So I wanted to start off by talking about some of the key strengths of TensorFlow. It's flexible, it's expressive, and it's extensible, and we've heard about some of those attributes in the keynote. So how is this accomplished in TensorFlow? The flexibility is due in part to its interpreted nature. It's in the name, TensorFlow. It uses this data flow programming model. So what the program does, you hand it a graph, it finds a node that's ready to execute, it grabs it, it runs it, and then a bunch more nodes become ready. And then it goes and grabs those nodes and executes them.
So that's the interpreter loop at the heart of TensorFlow. It's dynamic, and this is owed in part to its Pythonic heritage. When you get to use your full expressiveness when you define your graph, and you're not constrained by some external entity that tells you what you can and cannot express. And it's stateful, so you get to program using variables like you're used to programming in other environments. And it's black box modular, so you can come up with a new data flow operation and plug it into TensorFlow that the original TensorFlow designers had never even thought of. So the question is, how do we take all those strengths and add more speed? So this is a tank with jet engines bolted on the top of it. I thought that really exemplified what we're going for with this kind of approach. So the way that we accomplish this is with just-in-time compilation via XLA, which stands for Accelerated Linear Algebra. And this is compiler infrastructure that we've developed so that you can take a TensorFlow graph in and spit out optimized and specialized assembly for that graph. And to show you how this works, we're going to start with a shell, as programmers love. So if we start this video, you'll see the TensorFlow shell as you can build and run in open source. And we're passing it a flag to say, spit out the XLA assembly that's produced. So we're pasting in a very simple expression. So we're actually just taking 4 floating point numbers and multiplying them. And we're putting this explicitly onto the XLA CPU device. So the compiler is exposed as a device in one mode inside of TensorFlow. So when we press enter on this expression, and pause, then we'll actually see just a couple of assembly instructions get emitted. And some people in the audience are like, oh, of course, I know that assembly. But the point of this assembly is there are no loops because we knew that there were exactly 4 elements that you were going to multiply in the graph. So it actually emitted the one instruction that you need in this vector extended architecture to implement that expression on that CPU device. So optimized and specialized for the graph that you fed in with your TensorFlow expression. And if we continue on, we'll also see that we can place that same expression onto a GPU device and compile some GPU assembly code on the XLA_GPU device that corresponds to what we generated on the CPU side. So as we scroll up, the GPU assembly has a little bit more boilerplate because it's launching multiple threads and threads have to figure out what to do. But this number 4 here is saying, I am launching 4 GPU threads and I am specialized for the fact that that is the exact expression that you typed into TensorFlow. So this shows that we understand what expression you give us at runtime in the TensorFlow graph and then compile based on it for maximum speed. So if we switch back to the presentation, thank you. So we see that XLA for CPU and GPU works in standard TensorFlow shell as you would use it in a day-to-day basis. So the missing ingredient to all this is you. We need you to turn it on. So as you go and build TensorFlow, we really encourage you to turn this on, see how it performs for your use case, file GitHub issues, and tell us how you think compilation could benefit the way that you use TensorFlow. We really need more involvement from the community to understand where to prioritize efforts, because there's a lot of things you could do with compilation. There's a lot of potential avenues you can go down. So I've said just-in-time compiler. So what's this just-in-time stuff all about? The essence of just-in-time is that the program to be compiled is built at runtime. So when I type in a TensorFlow expression and press enter, I don't want to sit there at the command line for a few minutes while you figure out how to compile it. So we need to have low overhead compilation. In the blink of an eye, the assembly has to be generated. And another aspect of it is that in ML research, you don't want to say what your batch size is at the very beginning of time. You want to be able to say the batch size right when you figure out what you want it to be. So variables can bind very late in the process. You could say your batch size at the very last second, and because it's a JIT compiler, it will compile it at the point that it's defined. So you get to prototype with the normal freedom of TensorFlow development is the gist of this just-in-time compilation. So if we look at the TensorFlow level block diagram, we have the existing TensorFlow core. And Todd is going to be talking about this in more detail in his next talk, but XLA slots into the TensorFlow ecosystem here on the bottom right, where we have some auto-JIT capabilities where we'll find clusters to JIT for you, or you can place things explicitly on devices as we showed in that demo video. So what we think we've developed with XLA is a set of complementary attributes. So the flexibility that we get through interpretation we get the optimization benefits of compilation on the flip side. The dynamism that lets you write very expressive programs, because we find out all of these dimensions at the last second and then specialize for them, we get the benefits of having the static information about all the bounds of the tensors in your graph. We use pure semantics to make it easier to compile, so TensorFlow actually handles all of the external variable rebindings after the compiled executable is run, which makes a smaller surface area for compilation and makes it easier to target, say, new exotic devices. And you're able to build up many of the TensorFlow core operations from these primitives that we know how to compile. So you get the optimization benefits of all of the things on the right-hand side, but you get to think and write in the traditional way that's reflected on the left-hand side. So what has us excited about this whole approach? Server-side speedups for one. So through this JIT compilation and specialization that we've talked about, we see model-shaped benchmark wins of up to 60%. So those are models as you would run in the data center and model-looking micro benchmarks, see roughly in that speedup range. And for one extreme in-house example, we saw SyntaxNet get latency reductions from around 200 microseconds to 5 microseconds. And the reason for this was SyntaxNet had a lot of little operations in the graph, so the interpreter has to go grab each little operation, and that process of going and grabbing the little operations and running them incurs some latency overhead. And by compiling, you're actually able to eliminate all that latency overhead away. Another thing that has us excited are mobile footprint reductions. So with our ahead-of-time compilation, we talked about just-in-time compilation, but you can also go through a build process to turn models into executables if you want to do that up front. So this is just an executable like you would run on the command line, and it's able to eliminate much of the TensorFlow runtime and really reduce the binary size. And this lets you also cross-compile these models for ARM, PowerPC, and x86 CPU platforms. So one example that we have in-house was an LSTM model for mobile was able to go from 2.6 megabytes to less than 600 kilobytes, which was a 4x reduction in the deployment footprint. The general thing that has us excited about this approach is that analyzing a whole graph, a whole program, is made easy by this compiler infrastructure. So we have this thing called the high-level optimizer that's able to look at a linear algebra level graph and create a reusable toolkit of global optimizations to work on it. So even though you compile for different platforms, CPU, GPU, and other exotic devices, we've parameterized out the things that are specific to a given platform at this high-level optimization toolkit level. And so you're able to mix and match the platform agnostic and the target specific pieces so that if there's some optimization that really benefits, say, GPUs, you're able to use that for targeting GPUs, but you're able to use the general set of optimizations in the toolkit for targeting all the other platforms. So there are caveats here. It's experimental. It's still early days. Not all TensorFlow operations compile. And some of this is because very dynamic operations that it's very difficult to describe the type for won't compile by design. So for example, dynamic stitch has a very difficult type to define for its operation. So that is not something that XLA supports, and it may never support it. The performance is improving on a daily basis, so not everything is faster. And we haven't been able to devote equal time to all the platforms that we support. But with the community's involvement and prioritization, we believe that we could do much more. So it's open source. So really, we want you to try it out, file bugs, and let us know how this compilation could benefit your workload. So to recap, to go over the benefits of compilation, we're able to specialize the code for the computation that you handed to the compiler. So we're able to eliminate operation dispatch overhead. We're able to fuse operations together. So normally, if you take one operation at a time, you'll pull in all the data from memory, operate on it, push it back out to memory, and the next operation will come, pull it back in from memory, operate on it, and spit it back out. But when you have a compiler in the mix, you're actually able to pull all the memory in one time, operate on it with all the operations that you want to do at a time, and then flush it back out to memory. So this is called fusion. So we're able to avoid these expensive round trips to memory, which can benefit power on mobile platforms as well. We're able to perform precise and global buffer analysis. So really this means because we can look at the whole graph and how all of the tensors are flowing between all the operations, we're able to make compile time trade-offs between memory usage and speed. So you might have additional concurrency that comes, but it might be at the cost of additional memory. So if you were memory constrained, you may want to reduce the peak memory usage. And we're able to, in the code generator, unroll and vectorize, which are some key optimizations for today's modern platforms, via these known dimensions that we get. So we know that the tensor bound for batch size is a particular value, and by specializing for it, we're able to unlock a whole category of optimizations that modern CPUs and GPUs and other platforms are designed to run most effectively. And as we noted, you get much smaller executables out the back because you generate exactly what you need for this specific graph. So how does this work under the hood? Fundamentally, an XLA program is a set of static, decomposed TensorFlow operations. So they're math-looking primitive operations that you compose to make macro operations. So this is able to support many neural net definitions that we've seen in the wild today. So this is a classic TensorFlow example. You may have seen this graph before. So matmul and add, I know those from math. ReLU is just a fancy way of saying max of 0 and some value. But then softmax, that's kind of an interesting one. That one's not like the other ones. So softmax is implemented, hand-coded in C++ in vanilla TensorFlow today. And the question is, why can't we compose softmax out of the other TensorFlow operations if they support the definition? And one of the answers that we hear is because people don't want to pay a performance penalty for doing that. But what if operation composition had the performance of the hand-coded C++? So if you look at the kind of stuff that softmax has inside, it has dots and adds and reduces and exps. These are all math-like operations. And actually what the TensorFlow to XLA bridge that Todd will talk about does is this built-in operation decomposition, taking the macro operation and emitting several micro operations that we know how to compile out of it. So with the primitive operation composition, we're still able to generate the fused and optimized composite kernel like you would have written by hand. So note that this is all expressible in TensorFlow. All those operations that we showed in the softmax slide are all primitive TensorFlow operations, but XLA removes the performance concern of composing these TensorFlow operations together. So we're also able to avoid combinatorial explosions of custom operation fusions. For example, we see this a lot in ML research with LSTM cells, where you would technically have to specialize for every macro operation, for every set of primitives inside the macro operation, for every dimension size, for every backend CPU, GPU, different platforms, for every device within that platform. But the JIT is able to look at what you've provided to it in the graph, fuse it in a dynamic way, and then produce the optimized assembly for the platform that you're running on. We've also tried to make it a minimal surface area so that exotic devices can slot into this XLA set of primitives. So if you have a LLVM pipeline and a runtime plugin that we call Stream Executor, then you can actually slot into XLA today as a potential option, because the CPU and GPU backends are effectively using these two components. So we think that XLA is useful throughout the development lifecycle. So you get to use JIT compilation when you're prototyping. You get to use compilation caching as you scale. So when people request things from the server, you're not compiling every time. You're hitting in a compilation cache that says, here's the specialized and optimized assembly code. And you're able to use ahead-of-time compilation for mobile and embedded devices and for latency minimization on those platforms. So you get to control and observe static properties of the program, especially on mobile and embedded devices. This can be important, for example, for reducing peak memory usage. And so now I'm going to turn it over to Todd, who works on XLA as a member of the Google Brain team, to deep dive on XLA in the TensorFlow ecosystem. So Todd? Next slide.
Thanks, Chris. Let's see. So maybe, well, I'm an engineer, right? So like when Zach had mentioned to me that, would you be willing to present some of the work that you've been working on with a bunch of other people? I said, yeah, sure. But I always felt like in the back of my mind, whether there would be, some fear of his that, maybe I'd come up here and just show this one slide. This is the documentation for, how TensorFlow integrates with XLA. So it'd be like, well, just read this slide, we'll go along with it together. But no, I'm not going to do that. But I want to take this opportunity to introduce this symbol here, right? So what is this symbol? So everyone from the 90s remembers that this symbol meant, my website isn't really working, right? And so what's the significance here? Well, I mean, there's a reason why we sort of call it experimental, and on some of the documentation, we've sort of mentioned it like this, right? And it's not because like we don't really believe in it. In fact, it's the opposite. We think that the approach is actually really strong, and we think that the challenges that we face are sort of surmountable. The results that we're getting, the early results are really good, but we're definitely not done yet. And so that's why I wanted to present it to you guys now. And so I'm going to phrase this talk in terms of the actual open source directories for the code. Right? There's 4 directories down here, and I'm going to go through each one to describe what's actually inside of them. And so the first one is XLA. And so, unsurprisingly, this is sort of the compiler that Chris was just talking about. As a refresher, or maybe sort of to describe it at another level of detail, right? Like here's XLA in one picture. Okay, and so this is generally like how compilers work. Right? When you talk to compiler people, it's like, well, you've got some representation for the program that you want, and in the end, you want to generate machine code. That's what the thing does. And in the middle, it's like you go through these phases of like rewriting the graphs or like lowering the graphs, different representations. But at the end of the day, that's kind of it. And so on the left here, we have the XLA graph. And what this is composed of, the nodes are linear algebra operations, and the edges are sort of the flow of data, like tensors, through these operations. So that's pretty straightforward. We lower that to LLVM IR in the middle here. Now, LLVM is an open source compiler toolkit sort of framework that's pretty popular. IR is just like an abbreviation for its intermediate representation. So we've basically lowered the representation from sort of linear algebra type stuff to kind of assembly type stuff, general assembly stuff. And so LLVM then takes that and does code generation, where we code generate for actual machine platforms. The examples I've given here, there's x86, so that supports like servers or your workstations, ARM, right, for your like, mobile phones, or even like PTX, so this is for like GPUs. So we have like a sort of pretty wide range of support for the actual platforms that we can run this code on. And so the takeaway, the thing you want to remember from this picture is that like it's just a compiler. It's sort of like taking things from one representation and putting it down to another. In our context, the important thing is that as long as we can get things into an XLA graph, then out pops machine code for us. So the next directory under this compiler direct subdirectory is TF to XLA. And these literally, by the way, are the real directory names, right? We're not trying to like hide anything here. And so TF to XLA, sort of unsurprisingly, it's the stuff that turns TensorFlow into XLA. And so similar to that previous picture for XLA, here's one picture that sort of describes what TensorFlow is. And so on the left, we've got all the different programming languages that people can use to build their TensorFlow program. Right, but what you're actually, and like Python is sort of like the most widely used probably right now, but there's many others that we do support. And what you're doing when we build that program is that you're constructing this graph, the TensorFlow graph, and this is the graph of all your operations and all of the tensors flowing through them. Okay, and then we take that graph, and like as Rajat mentioned, we have a C++ runtime that actually executes this. And so there's 2 components here. One is called the executor, and the other is the kernels. So the job of the executor is to actually walk through this graph, and when it hits each node, it looks up in the kernels and finds like the appropriate kernel and actually runs it. And so as an example, I've labeled 2 of the graph nodes here, like add and softmax. So add is just adding 2 things, and softmax, well, Chris just described that. And so for add, when you think about it, like the executor is going to hit this add node and need to be add the 2 inputs that come in. And so it does that by looking up inside the kernels and finding the C++ fast implementation for it, for the device that you're on, and then actually performs the addition. Similar for softmax. We hit the softmax node, we look up in the kernel. This one happens to be a little bit more complicated. It's not just a simple, one arithmetic operation type thing, but still, it looks it up, runs it. And so that's basically how TensorFlow kind of works today. This is without XLA. So the next slide is going to show sort of how we take TensorFlow and turn this into an XLA program. All right, and this one maybe, it's kind of a lot of stuff going on, so I'll walk it through. On the left, we've got the TensorFlow graph. This is that same thing I just showed, and it has the add and softmax labels. Okay? On the right, what we're trying to generate is we're trying to generate that XLA graph. Right? Remember from that first slide about, well, as long as we can get things into this representation, then XLA is going to take care of all of the rest. It's going to compile the thing down to machine code. And so the way we do that, we have a local executor, which is basically the same thing that we had for the normal TensorFlow runtime. but we've swapped out the kernels. So remember, like in the previous picture, this was an orange box. Oh, by the way, so orange means sort of TensorFlow to keep with the theme and everything, and blue means XLA in all of my slides. So we swapped out that orange box, right, with the kernels, the TensorFlow kernels. We swapped in like the XLA ones. And the job of these kernels, instead of actually executing the operation, it's going to be to create this graph, right, to take the TensorFlow graph and turn it into the XLA graph. And so an example here for add, well, we hit the add node, and we say, OK, we need to do something. We look up the kernel, and it says, great, I know how to transform the TensorFlow add into the XLA add. In this particular example, it's sort of one-to-one, and so this is like a really simple case. So Chris mentioned softmax, how it's sort of this more composite operation, right? It's built up of a bunch of stuff inside, like dot and exponentiation and stuff like that. And so this graph here is showing that softmax on the TensorFlow graph is just one op, and we look up the translation kernel, and we've turned that into multiple ops in the XLA graph. And that's basically all there is to it, right? Like, this is how we transform TensorFlow graphs into XLA. We have a link here that describes where all of the kernels are that actually perform this translation. And here's the first point where we're going to see the this awesome men at work. I kind of wish it was an animated GIF, because that'd be more to the point. But like this men at work, basically the kernels that we have, they're not all there, right? Like, we haven't implemented every TensorFlow op. And this is a place where, for some of them, they're actually quite difficult, and that's the reason we haven't implemented them. And maybe, as Chris was mentioning, some operations really just don't translate that well because of their very dynamic nature. For other ones, we just haven't gotten around to it, really. And so this is a place where actually community support would be really useful. Okay, so we've sort of covered what XLA is, and we've covered how we translate TensorFlow into XLA. So the next 2 points are going to be about how we actually use this cool compiler inside TensorFlow. Right? And the first thing we're going to talk about is JIT, which is like the just-in-time compilation. And so in the theme of like graph transformations, I'm going to describe JIT as sort of this graph, how the graph changes. And so on the left we have this a normal TensorFlow graph. And in this red trapezoid, we've identified 3 nodes. And these 3 nodes are going to be sort of able to be compiled by XLA. The other nodes in the graph are not, for the purposes of this, going to be compiled by XLA. And there's many reasons for that. We said sometimes operations just aren't implemented, or other times, we've chosen a clustering that just happens not to cluster them in. And so in this example, we've chosen these 3 nodes. On the right, we see that we've taken the graph and we've rewritten it so that the same nodes outside of it are still there. But on the inside, we've taken that cluster, that subgraph, and put it inside this sort of pink bubble. Okay, and now when you think about how TensorFlow, like the runtime works, it's working exactly the same. It's going off of this right-hand graph where it's going to visit each node and it's going to look up the kernel for the operation that it represents, and it's going to execute it. When it hits this pink bubble, that's where some of the special stuff happens, right? We have inside of it the notion that this subgraph still exists, and we're going to compile that. We're going to transform that graph into the XLA graph and transform that into actual machine code, and then execute that. This is also where that caching occurs, right? Where if you happen to hit that same subgraph again, so if you run the same graph multiple times, or within your program even, if you have the same subgraph that shows up multiple times, we're not going to pay the cost of compilation multiple times. We're going to just compile that once and execute it over and over again. So in this picture, we're going to show some of the more standard sort of ways that you show up in these graphs. Like the previous one is kind of simplified. This one's obviously also very simplified. But the main point here that we're trying to show is that a single TensorFlow graph can have multiple such clusters show up. Right? And in this example, we've got 2 of them on the left. We've got this blue rectangle, and we've got that same sort of red trapezoid. So the clustering phase is going to go and identify, which clusters are going to be compiled. And on the right side, we've done the exact same thing. We've turned those 2 things into their respective little bubbles. And when the TensorFlow executor gets to these nodes, we're going to compile and run them with the caching and everything. So in this slide, we're going to talk a little bit about like one of the sort of challenges that shows up. You might think, well, that was sort of pretty straightforward. So here's a particular challenge. I mean, it's not like super difficult or anything, but it's kind of non-trivial at scale. And so this particular one, we're showing a graph where we picked a clustering that happens to be pretty bad. Yeah, in fact, it's a bad clustering. Now you might want to think a little bit about like, well, what exactly about this clustering is bad? If we happen to pick this clustering, like what would actually go wrong? And so the problem is evident sort of on the right-hand side, where we've created a cycle between like the non-JITted nodes and the JITted nodes. And the issue here is that just the execution engine, it's going to have no way to determine like, well, which one do I run first? How do I actually execute this graph? And so this is obviously something that we need to avoid while we're doing the JIT process. This particular example, it's not like super difficult, but I mean, as we get to larger graphs, this actually becomes a little bit more challenging and non-trivial. So this is an example, a flavor of the concrete things that the JIT level is actually performing for you. So in order to turn on the JIT compilation, we've got two main ways right now. And so I'll walk through the first one. That's in this blue box on the top. It's called whole session, right? And we've really tried to make it super simple. And so what this is, I say like, we really try to make it super simple, and then you've got like, this super long. Okay, but I mean, the concept is actually super simple. Never mind the long label, right? Conceptually, what you're doing is you've got this configuration that you're going to pass in to run your session, right? To create your session. And all you need to do is set this one flag on it to say like, turn on the JIT. And there you go. What that's going to do is it's going to take your entire graph, it's going to determine which clusters of the graph can actually be compiled, and it's going to go and rewrite the graph into that. And then when you actually execute, it's going to, like, every time we hit that node, it's going to perform that JIT process for you and actually compile down to machine code. And so the concept here is that you flip this one flag on, and you get like automatic benefit, right? Things just get magically faster for you. So the second way that we can actually turn on JIT compilation, this one's a little bit more explicit. We call it like manually scoped, right? And the idea here is that here you take your program, and instead of just turning on this one flag, you explicitly put scopes inside of your program where you can manually control exactly what gets compiled and what doesn't. Right? And one of the ideas here is that, well, you might know due to the particular model or graph that you have that certain areas, it's going to be very valuable to compute or to compile this subgraph, but not this other one. And so this is how you can accomplish that. You get like complete control. In this particular example, we've got like this one operation down here, which is add, and that's the only thing that's going to be compiled by XLA. Okay, so I said we wanted to make this sort of super simple, but it's not as simple as we would like, right? Like I kind of said, well, you just turn on this one flag and it sort of does all the rest. Well, ideally, it's like, why do you have to turn a flag on at all? Like, shouldn't it just be like doing this automatically? And this is the point where there's a little bit of work in progress. Like we have a lot of ideas here, right? Like about different heuristics that you might want to use in terms of when to turn the thing on, what kinds of clusters to create, and things of that sort. And so that's something that we're sort of working on right now. In the interim, there's sort of like these two ways that you can sort of try things out for yourself. Okay, we're like zooming right along here. Okay, the last, so far we've talked about XLA, how we transform TensorFlow into XLA, and how we do the just-in-time compilation, right? You sort of like flip this flag and automatically things should get faster, or sub-portions of your graph should get faster. This last part is going to be about ahead-of-time compilation. And keeping in the sort of graph motif, I'm going to describe sort of the one-picture sense of what does ahead-of-time compilation really mean, all right? And so on the left, we start with that normal TensorFlow graph, okay? And we take that, unlike the JIT, we take that entire graph now, and we transform that into the XLA graph, okay? Like, remember for the JIT, we were taking like sub-portions of the graph where, as you're running, like, if particular operations couldn't be compiled, that's fine. We'll just leave those out. We'll execute them as normal, but then we'll compile the stuff that actually can be compiled. In this mode, the entire graph needs to be compilable. But you get a benefit out of this, because once you've transformed the entire thing into XLA, then at the end outspits this binary, like x86 or ARM. I mean, you can just run this thing directly on your mobile phone or your server. And so this is a pretty powerful technique. The way that we do this is through something called tfcompile. This is a tool that's written in C++, which is really sort of like a wrapper tool, the same way that like GCC or like a Clang or something. It kicks off like the entire compiler, all right? And it's pretty simple the way that it works. The concept is that on the left side, you start with your normal TensorFlow graph, and you give it a configuration file that tells it what the feeds and fetches are. So feeds and fetches are just like TensorFlow terminology for what the inputs are and what the outputs are. Okay? You feed that into this compiler, this tool, and out at the other end pops like your binary, like machine code for whatever platform that you want to run on, and a C++ header. Okay? To give you a little bit more of an idea of what exactly are we doing, right? That C++ header is conceptually like a function, right? We've turned that graph and we've identified what the inputs are, we've identified what the outputs are. So we turn that entire graph into a single function where the feeds are the input arguments and the fetches are the output arguments. And so that's pretty simple, right? I'm actually pretty excited about this because this is a pretty cool way to think about things in terms of not just reducing binary sizes, but also like different ways of deployment, right? We've got this like, fancy way to describe machine learning computations in TensorFlow, right? And you can build these extraordinarily complex and intricate models. All of that turns into this graph for TensorFlow, and you can feed that entire graph into this tfcompile, and out at the other end pops like a single function that you can call, right, with your inputs and your outputs. And so that's actually pretty cool. Some of the remaining pieces of work here, right, that we have. One of them is that the only binaries that we currently support, the only backend is for CPU, and so that both for workstations like x86 or for mobile like ARM, but not GPU yet. And there's no technical reason why we haven't done this. It's just we have limited time, and so we haven't done it yet. But that's definitely something that we want to do in the moving forward. Another cool future direction, actually, is I've mentioned, well, the only sort of language binding that we support right now is C++. Or actually technically C as well, I guess. Either way, you can call this function through this header file. There's no reason why conceptually we couldn't add a thin wrapper that allows you to call this function now through your programming language of choice. Like basically everything supports binding to C to some extent. And so you could use like Python and Swig, or you can use like, well, in this example, like Java and JNI, or if you like Go, right, you could use Go and CGo. Like there's many different ways where like you could actually simplify your deployment story using a compiler. So the next few slides are going to talk a little bit about the details through the exactly how this tfcompile thing works. The first part I'm going to talk about is I had a little configuration file where we said what are the feeds and what are the fetches. And so this is expressed in sort of Google protobuf. So if you're not familiar with this, the file itself right now is the text version of the protobuf. It looks kind of like JSON. It's not very complicated, actually. So this top part has like two feeds, and remember, we're identifying the inputs into the graph, right? So in this particular simple example, we've got like X and Y happen to be our inputs in this graph. And we tell the compiler exactly what the shapes are. This is a good point to re-emphasize, right? Like Chris had mentioned, sort of TensorFlow has this extreme flexibility where it really allows you to do stuff very easily and quickly. But for compilers, it's much better if you can specialize, right? That's one of the benefits that you get if you can specialize based on the exact sizes that you have. And so here, for any of the inputs that come into your graph, you tell it exactly like here's the exact sizes that we're going to use. Similarly, as the feeds, we've got the fetch here. And for the fetch, you basically just identify which node or nodes you want as outputs of the function that you're going to generate. In this case, you don't have to specify the shape anymore. In fact, you can't, just because given the input shapes, we can sort of infer what the shape is at the output all the way through the graph. And so this is basically the only sort of piece of configuration that you're going to need to actually run this compiler. The next step is going to talk about, well, how do you actually invoke the thing, right? So I've got this configuration file. I've got my graph. Well, what is it? How do I kick it off? And so the example I'm going to present here is when you use Bazel. So basically, through Bazel, we've created a Bazel build macro, which is just like syntactic sugar to kick off the whole thing. We've introduced this one notion called TF library, and it's pretty simple. You're basically just giving it like three main pieces of information. And it's the ones we've just already talked about. The first one is the graph, right? You sort of give it the graph in protobuf form. The second one is the feeds and fetches. This is a configuration file. That was that thing that I just showed. Simple, like here's the feeds, here's the fetches, here's the sizes of the feeds. And the third thing here is a C++ class name. right? And so this is the class name that will be generated for you in that C++ header, which will allow you to invoke the computation. Now, one thing to note, I know, like, in the open source world, I mean, I experienced this too, right? Like, not that many people use Bazel. And so, if you don't actually use Bazel, all is not lost, right? Like, the TF compile tool is just something you can run in the command line. And basically, like, these configuration options that I just described are the flags that you pass into the tool. And in addition, you can tell it, where do I want my output object file and where do I want my output header file to go. And that's about it. So we've tried to make this sort of easily, integratable into whatever build system you have. Just a note on that, it's like, this is another place where lots of community help would be great, because there's like an astounding number of different, build environments that people have. So like make, CMake, and, there's like a whole bunch of these things. So it should be relatively simple to actually add in that integration. Okay, so here it's sort of like there's a whole bunch of code, and I know like people's eyes are sort of glazing over and stuff. So I'm gonna like just try to describe this in a sort of like straightforward way. And so what we're trying to describe here is like the simple way that you can actually invoke the computation that we've just described. This is C++ code because that's the sort of the language that we currently support. And at the top, you sort of include, well, your generated header. This is the thing that was automatically generated for you to invoke the computation. All right. And on this line, we instantiate this class, this test mapmul. That was that was the class that's defined inside of that generated header. And note we've got this mapmul variable now. So if you look through the slide, basically mapmul, that instance is like what we're going to use throughout. The next step was we just set up the arguments to actually run this computation. This particular computation we're going to assume is like a matrix multiplication. And so all of this code is really just a fancy, this is how in C++ you say that my first argument is going to be the numbers 1 to 6, and my second argument is going to be the numbers 7 to 12. And then you call this one thing called mapmul.run. And basically that's invoking, whatever computation you had in your graph. And at the end, you can grab the results out of the, the mapmul object. And so hopefully this gives you a sense for like kind of how simple it really is. You can take whatever arbitrarily complex model that you have and boil it down to a function that you can just call. And so to recap, we've covered sort of the compiler subdirectory under TensorFlow, which has XLA, right? This is the compiler. TF to XLA, which does the TensorFlow to XLA transformation. The JIT, which is the just-in-time, and AOT, which is ahead of time. And so now I'm going to present some results. And so one thing to note here is that when Megan was talking about some of the cool, the awesome performance results that we've had, none of that was actually including XLA, right? So the first slide I'm going to show is on JIT. And when you use JIT for different models running on GPU, what is the speed up? And so the way to read this is that each row is one particular model that we've run. And the numbers on the chart are describing, well, what's the speed up or slowdown? So in essence, for each row, we've run the this particular model two ways. We've run it once using just normal TensorFlow, and we've run it another time with XLA enabled, with that JIT flag enabled. And the JIT flag is going to compile things down and hopefully make things faster. And so what you're seeing here is that basically all of the green stuff is positive numbers. And so, kind of the whole point in this slide is, well, faster is better. And the collection of models that we actually have here are sort of things that we actually do care about. It's not just arbitrary things. The first couple of examples are for GNMT. That's the neural machine translation. So it's one of these stacked LSTM type models. Next, down the list, we've got Inception, AlexNet, like some of the image processing models. One of the reasons why we see speedups here are due to the things that Chris actually mentioned. Right? We get this fusion of operations, like element-wise operations get automatically fused together. And so, if the the long pole basically in your computation is streaming through all of the data, well, that's going to help a lot. Right? You've got like these tiny operations, like you want to add things, you want to multiply things. You can fuse them all together. Also, there's sort of different parallelization and buffer allocation strategies that we have that can actually provide additional speed up. Another thing I want to point out here is that it's not just for inference or not just for training. It's actually for both. And so here, the pink boxes are highlighting the training examples, or the models where we actually ran training, so both the forward pass and back prop. And this is actually pretty cool. One observation, though, here is that, well, it seems, at least on this picture, that lots of the training ones are sort of lower down on the list. Right? They're not getting as much of a performance improvement, or maybe even in some cases, maybe a negative performance improvement. So negative here means that we actually are worse, right? We're not as good. And so on the training side, one reason for this, it's basically, training graphs in general are a little bit more complicated. You can think about like inference graphs as only having the forward pass, but once you add training, you're going to have like back prop. You're going to have to compute the gradients. And so that makes the entire graph larger and more complicated. And that's one of the reasons why sort of like some of the numbers are a little bit lower for the training side, but it's definitely something that we want to work on. And so, trying to, improve all of these numbers as much as we can is something that we're actively, working on right now. So the next slide, this is kind of like so actually, with that previous slide, if you saw that in an academic paper or something, you'd be like, yeah, this, whatever, man, I don't believe this guy, right? Because it's like, it just looks like too positive. And so here, I've taken a collection of micro benchmarks. Oh, another thing to note, actually, these numbers are for real. These numbers are all actually, I grabbed them like yesterday off of the actual benchmarks that we've been running, like, constantly. And so I just grabbed like the snapshot of whatever yesterday was and like plopped them onto this chart. And so here, again, it's the same graph layout. The green stuff on the right, positive numbers, those are speed ups, that's good. And the red stuff on the left, negative numbers, that's kind of bad. And so we see some pretty good speed ups. There's a big hefty chunk here where things get up to as much as like 50%. And down here, there's like room to improve. I talked a little bit about some of the things that we might want to do to improve. Another thing that we've noticed down here is that you can't read the font because it's tiny, but then lots of the models down here, or lots of the micro benchmarks that we're running, are for sort of like pre-fused cells. So these are things where we take advantage of existing compilers or existing implementations of fast fused kernels. And so when the TensorFlow op comes in that does that, TensorFlow by itself does a really good job because it's kicking off this fast kernel, but the XLA side doesn't really do a good job at that right now. And so just to be like sort of honest about like where we are, that's kind of where we are, but we're trying to improve the thing. And so this slide really proves to you that I'm not like in marketing or something like that. I actually got like a C+ in marketing. I think so the previous two slides were GPU, right? And so this slide's like CPU again on the JIT, right? And again, speed ups in green are supposed to be good, and slowdowns in red are supposed to be bad. And so this is like not good. And so the simple way to like sort of describe this is that, yeah, we got the men at work thing, I can give you a little bit more detail behind that though, right? Like one of the simple reasons is because we don't have, unlimited people working on it. And so we have to prioritize. And we're kind of like practical people, right? We kind of thought, well, I mean, if you're using TensorFlow and you want to use this compiler, then you probably want to make things faster. And if you want to make things faster, then probably you're using GPUs right now already. And so the first thing we're going to focus on is like, improving GPU performance because you can get like, so the most benefit out of that. One of the concrete reasons why this particular, many of these benchmarks are actually worse is that currently TensorFlow already parallelizes much of the operations, right? If you have multiple operations, they can run in parallel. This is on top of the within single op parallelism, where let's say you have like a big map mall, and we do fancy tiling and stuff to parallelize that as much as possible. On the XLA side, we do have separate backends for sequential and parallel, but we simply haven't put very much time into it. And so there's a lot of low-hanging fruit here, actually, where I think we can improve these numbers, quite easily and quite dramatically. So this would also be an area where, if you're interested, then there's definitely, in terms of community involvement, there's lots of stuff here, and it's all in open source. So that would be kind of a lame sort of slide to end on in terms of performance. But one thing we haven't really talked about is smaller binaries, right? I mentioned there's many ways that you can use the compilation. You can do like a JIT or ahead of time. This is for ahead of time, right? And the specific thing we're trying to target here is that on mobile, like binary size actually makes a big difference. Like your users don't want to sit around and wait for like many megabytes to be downloaded for your application. And so using the compiler, we can actually get significant binary size reductions. The particular example we have here is for a stacked LSTM. This particular one happens to be like 3 deep and 60 wide. So you've got LSTM cells sort of like 60 wide in a sequence and then 3 deep. And it's compiled for Android ARM. And this is like a real application. The original binary size was 2.6 megabytes. And that breaks down to a 1 megabyte for the TensorFlow runtime with only the ops that we actually need, and then 1.6 megabytes for the graph. When we compile that down, we end up with 600 kilobytes, right? And so that was what Chris was talking about in terms of like a 4 times reduction. 272 kilobytes of that is code, and 330 kilobytes is weights. So I'm going to focus in on that 272 because even 4 times that's sort of not enough. I want to make it bigger, right? So I want to point out this picture down here, which is sort of like you can't really read anything on it. It's basically a tree map of all of the binary size usage broken down by what's actually using it. And so on this box here, this is the actual generated code that we created. It's only 88 kilobytes. So the next box that we have is eigen. And so this is 76 kilobytes. This is a good point to also mention that, so you might wonder, well, what's eigen doing in this picture, right? Like eigen, if you don't know, is a C++ templated sort of specialized linear algebra sort of library. So it lets you do like matmols really fast. It does that sort of tiling and stuff, depending on your sizes. In XLA, we have the opportunity to not just implement all of these things on our own, right? But if we have good implementations that already exist, we can just take advantage of it. And so in this particular case, we've taken advantage for single-threaded eigen for the matrix multiplications that happen inside the LSTM cells. So that takes up 76 kilobytes. And actually on the right, the majority is taken up by standard Android libraries. This is like 108 kilobytes. So this is just a snapshot of sort of like we believe we can actually make things much smaller even if we really wanted to. But 272 or 600 kilobytes even is a pretty good start. It's like a 4 times reduction already. And so to summarize, we've talked about how so TensorFlow graphs are compiled via XLA. We have both just-in-time and ahead-of-time compilation, and so they're both pretty cool and have serve different use cases. And some models, some real models, are actually already faster or smaller, so it's all really neat. And oh yeah, the last thing is that work in progress, right? Like we're continually trying to improve these things. Like all those benchmark numbers, we're working on that on a sort of a daily basis to try to make things better. And so with that, that's the talk. Okay, so next I want to introduce to the stage Dandelion, who's going to be talking about TensorFlow, this really cool visualization tool. So Dandelion?
Thank you. Hello. I always wind up doing these live demos, so I never get the privilege of just jumping straight into slides, but instead there's some amount of computer wrangling. But now that's done. All right, so my name is Dandelion. I'm the only person I know who has an emoji signature. It's the dandelion emoji and then the lion emoji, although I didn't actually put this on the slide. And I'm here to talk about TensorBoard. So TensorBoard is a really exciting tool. It's been built by a number of engineers at Google. And the basic idea behind TensorBoard is everyone knows that neural networks can sometimes be a bit of a black box. And so we want TensorBoard to be something of a flashlight, something that will let you take the confusing world of TensorFlow and start to dive into it. Now, it's a pretty complicated tool. It's got a lot of bits and pieces. So the way that I'm going to explain it to you is by going through an example. So we're going to take a simple MNIST model. It's going to have a couple convolutional and pooling layers at the top, and then it's going to have 2 fully connected layers, and then it's going to spit out our prediction. And we're going to just build this model together and kind of explore what can go wrong and how we can use TensorBoard to better understand it. So I'm about to show a bunch of code. I'm going to go through it kind of quickly. You don't need to worry about getting all the code right now because it's posted on my GitHub as a gist, and we'll also tweet out the link at the end. So to start, let's put together some layers in TensorFlow. So we wanted to have a convolutional layer, so we're going to make 2 variables. These will have the weights and the biases. We're going to then apply the convolution op. We're going to do apply a ReLU to the convolution plus the biases, and then we return that. Then we're going to make a fully connected layer. This is even simpler. Once again, we have weights and biases. We're going to do the ReLU of the matrix multiplication and addition, and we return that. Now that we have some layers, we can set up the feed-forward part of our network. We have some input placeholders, which will just take in our images and our labels. We'll reshape the image so that it actually looks like a 28 by 28 pixels so we can convolve on it. Then we'll start putting together our layers. We get the 2 convolutional layers. We flatten it. We get the 2 fully connected layers. And that's basically our whole network. And finally, we need to compute the loss and start to actually train things. So we're going to use cross entropy for our loss function. We're going to use an atom optimizer to do the training step. And just for convenience, we'll record the accuracy so that we can print that out to the console. So finally, we just need to do a little bit of work to turn this model on. We're going to initialize all of the variables. Then we're going to do 2,000 steps of training. For each step, we're going to take a BAST of the MNIST training data. Occasionally, we're going to report the accuracy so we can see if it's working. And then finally, we'll run the training step. So we have our model. Let's turn it on. At 0 step, it has 10% accuracy. That seems about right. At step 500, it has 12% accuracy. Not exactly what we were hoping for. And then it even goes down, and we can see really, this model didn't learn anything. It's just getting baseline 10% by random guessing. So what are we going to do about this broken model? Well, I just said we have a flashlight, so let's turn it on. And the first thing we might want to do is visualize the computational structure of our TensorFlow graph. Because we spent all this code setting it up, but what if it's miswired? What if somehow we just didn't make the connections or the computation we expected? So we're going to need a class that lets us write data from TensorFlow to disk so that we can read it in TensorBoard. And that class is called a file writer. It basically just writes any information you're going to visualize in TensorBoard. And to visualize the graph, it's very simple. We set up the file writer, we give it a directory, and then we add our sessions graph to that writer. And now finally, we just turn on TensorBoard. It comes pre-installed in the pip package, so you can just, at the command line, write TensorBoard and pass it a logdir. And that brings us to our first demo, which is here. So it has no scalar information, has no images. The only thing we gave it is a graph. So we can go to the Graph tab, and we get something that's really quite confusing. So I can kind of see how this corresponds to the graph we made, because maybe we see on the left we've got a convolution, we've got some addition, we've got a ReLU, we've got pooling. But it also has all of these parts that I really don't have any idea where they came from, even though I just made the graph myself. So what we're seeing here is that TensorFlow graphs are really complicated. And the way that we can get this tool to actually give us useful insight, we need to do a little bit of work to structure the graph. So essentially, we need to clean the graph. Now, you may know that every TensorFlow graph is based on this naming system, where it has these ops, and the ops have names. We can control the names by giving individual nodes specific names, and by setting up name scopes, which cause all groups of related ops to have the same naming structure. So let's go and apply that to the model we just built. First, in our layer definition, we're going to take a couple ops that are important, like the variables, and give them explicit names, like W for weights and B for biases. And then we're going to apply name scopes to the entire layers so that all of our convolutional ops will stay grouped, and likewise in the fully connected layer. Then when we actually set up our graph, we pass a couple more names, like giving the placeholders names, and we use this function to give name scopes to our layers. And finally, we add a couple name scopes to the training and the loss computation and so forth. So now that we've done that, we can construct another summary file writer pointing at a different directory. You always want to use a different directory with TensorBoard to keep data separated. And we can turn on TensorBoard pointing at that directory. And now we get a much nicer graph. So you can see here that this actually starts to correspond pretty meaningfully to the graph that we had in mind. We have this training block, which is connected to everything. That's because when you are computing the gradients, you need to connect to every variable in the graph. But maybe for now, we'll move it to the side, because it's not as interesting to us. And now we can kind of explore and say, OK, we have our X placeholder. We reshape the data. Then we go through each of these convolutional layers where we have some variables. We have the convolution, the addition. And we can kind of scan through our graph and see that everything is wired up the way that we expected. Now, I'll point out a few features of the graph visualizer. One thing is, as you've noticed, you can kind of explore different levels of abstraction by diving into individual pieces. And we can dive in further, and here we're getting the sort of mechanics of computing cross-entropy. It turns out all of this slice stuff was for computing cross-entropy. Also, you'll notice that different boxes have different colors. The way that the graph visualizer works is it identifies repeated similar substructures of the graph and gives them the same color. So we can be sure that these two fully connected layers have the exact same structure as each other because they are both colored green. Now this sounds like it might not be such an important feature, but actually when we were porting the inception graph over to TensorFlow back a year and a half ago, and this is a very complicated graph with tens of thousands of nodes, we were stuck for weeks and we were getting the wrong results, and we actually thought maybe TensorFlow was just broken. Maybe we had spent like a year developing this new software and it just wasn't going to train. And it turned out the real issue is that one of the inception submodules had a slight bug, so it was wired slightly differently, and that was breaking the training. There are a couple other settings you can use here. So for example, we can look at coloring by device. In this case, everything was put on the same device, so it's all gray. But if you were using a mix of CPU and GPU, you can use that to get an idea of where things were placed. We can also turn on trace inputs. And then you can choose any individual piece and kind of see what all of its dependencies are in the graph. Everything else gets grayed out. So from looking at this, it does look like we have more or less the graph we expected. But as we saw, it's not training at all. So it's time to get a little bit more information and time to start using these other tabs. Now to do that, we need to actually write data, runtime data from TensorFlow to disk. And the way we do that is through a system called summaries. A summary is basically a special kind of TensorFlow op. It will take in a regular tensor from your graph, and then it will output protocol buffers that we can write to disk. Now, there are a couple different kinds of summaries. The simplest is the scalar summary, which will just write down a single value, and you use it to create these nice line charts. Then there are image summaries, which will write out an image, and you can use it to visualize, for example, if you have a generative model of images, or if you just want to check that your input data is formatted correctly. We have an audio summary. So for example, the Magenta team, which you'll hear from later and is working on a lot of music generation, actually added the audio summary to TensorBoard. There are histogram summaries, and these let you look at the shape of distributions of different values. So it can be very nice to attach to your variables, like your weights. And finally, we have the tensor summary. The tensor summary is the newest summary. The idea is that it can write out any kind of value, because everything in TensorFlow is a tensor. But we haven't quite added support for it fully yet. And I'll discuss it a little bit when we get to TensorBoard's future plans. So now we'll add a couple summaries. We add these two scalar summaries because it would be nice to look at how the cross entropy and the accuracy are changing over time. It'd also be nice to look at our input images, just make sure that they're MNIST digits like we expect. And then finally, in each of our layers, we'll add a couple histograms that will show us the weights, the biases, and the activations. So with that all said, we need to think, okay, how are we actually going to run these summaries? And the answer is that we run each summary up, it gives us these protocol buffers, and then we can pass them to our file writer to get them to disk. It would be really tedious if we needed to keep track of those like 6 or 7 summary ops and run them all individually, especially if we go to a graph like Inception that might have hundreds or thousands of summaries. So instead, we have this merge all summary that creates a single target. We run it, and we get every summary in the whole graph. So we can go and create another file writer. We can go and modify our training code so that it will run the merged summary and write it to disk. And then finally, we just need to turn on TensorBoard pointing at our new directory. So now we can start to explore what's really happening in this model. So as we saw, the accuracy kind of bounces around 10%. In the backdrop, you can see the original data is very noisy because it's just got random sampling moving around. So we can smooth it to see the trend line more clearly. And then we also have the cross entropy. And this is pretty interesting in that the cross entropy is staying exactly constant throughout the entire training run, which suggests something is seriously wrong with the model. We can also take a look at the images tab. And here we find, okay, our images actually do look like fine MNIST images. And we can look at a true pixel size and then be reminded that something went wrong with that. We can also expand it. So we have a couple different capabilities here. And what we'll see really interesting is when we look at the distributions and histograms. So this is actually 2 different ways of visualizing the same histogram information. The distribution chart is telling us that all of the values were stuck at 0. And the histogram chart is going to tell us the exact same thing. All of our activations were one giant spike at 0. And also all of our biases and weights were stuck at 0. So this gives us an intuition that something was probably wrong when we set up our layers, because when the biases and weights are all 0, we're going to have 0 gradients passing through the graph, and nothing will train at all. So let's take a look at our code for where we set up these layers. I'm going to look at the convolutional layer, for example. And you can see that we actually set the biases and weights to initialize at 0s, which was a mistake. So we can change that to have a more sensible initialization, like a truncated normal for the weights and a constant value for the biases. And now we can just rerun our model with the changed settings. And we start to get much better results. We can see here that our cross entropy sort of rapidly decreases towards 0, and our accuracy rapidly increases towards 1, or perfect accuracy. If we want to see these two charts at the same time, we have the ability to create groups of charts using regular expressions. So we can just put everything in one chart, in one group. Similarly, we can now see that if we look at the histograms, for example, we actually have nice distributions over time. A sidebar about these histogram visualizations. They were made by the really talented Sean Carter, who used to work at the New York Times. And he was inspired, if you've ever seen this album cover called Joy Wave, where it's like an audio waveform spread out over time. He's the kind of guy who sees an album cover and thinks, that would make a great visualization. So we can do a couple cool things here, like we can switch them from offset to overlay. So this is sort of, if you want to see how it evolved over time, the offset is useful. If you want to see how it looked in absolute relative terms, the overlay is quite useful. We have the exact same information in the distributions charts, where now it's showing us a different view, where we can see, for example, this very pale line is the maximum value. So we can see that there was a very high maximum value for the activations. But here, when we're looking at the 90th percentile and the 60th percentile, it was actually fairly closely clustered. But the important thing here is that our model is finally working, and we can see that it's training a lot better. So now that we have a good model, we might say, okay, well, we chose a learning rate kind of arbitrarily, and we chose our model architecture kind of arbitrarily, but what if we had done things differently? What if we had tried a couple different learning rates, and what if we had tried a couple different model architectures? TensorBoard can be really useful for this as well, because it gives you a good way to compare how different versions of your model stack up on all these different variables. So we can make a couple changes to our code. We're going to iterate over 3 different learning rates, and then we'll iterate over using 1 or 2 fully connected layers and 1 or 2 convolutional layers. And we're going to make a unique string for each of these hyperparameter settings describing it. For example, learning rate underscore 1e negative 3, then fully connected equals 2, and then convolutional equals 2. And we'll create a new summary writer that's pointing to a directory that has that string in the name. And now we can actually run the model. And we're going to point TensorBoard at the parent level directory. So in the past, we've been pointing TensorBoard at the directories for specific runs. And now we want to look at the parent of runs so that it can find all of this data and compare it for us. So now we can go to our next demo. And here we have this run side on the left has got all of these different hyperparameter settings that we experimented with. And now we can look at, for example, our cross entropy and start to see how they compared across the different runs. Similarly, we have accuracy up here. So we can see actually there was a lot of variance. Some of our models barely learned anything at all, and some of them were extremely successful. If we look at cross entropy, maybe we want to make things a little bit clearer, like the beginning, everything starts high, so it sort of rescales the display. So we can zoom in, and we get things a little bit clearer. We can also toggle on a logarithmic scale, which makes the differences a little bit more pronounced and is sometimes very useful. And then we can start exploring with our tooltips here and seeing, okay, this run that was the worst was learning rate -3 and then both convolutional and both fully connected. And this one that was the best was the same thing but with a smaller learning rate. And if we want to do a more in-depth comparison, we can start to filter by settings here. So if we want to look at all of the things that had only one convolutional layer, we could type conv equals 1. And now we can see just the ones that had one convolutional layer. So that makes it a little bit easier to dive in. Or similarly, we could search for only the things that had the learning rate of e to the -4. And that includes our best run. A couple other features I'll point out. You can also just toggle one run at a time by clicking here. And we can also change the display to show us different ways of visualizing time. Right now, we're orienting the x-axis by step, but we could do it by, for example, wall time. And then we can see actually that while they're all aligned in steps, I ran them at different times. We could also use relative time, so this will show the number of minutes from start And then we can see actually that some models took a lot longer to run than others. So even though they took the same number of steps, the models with more fully connected and more convolutional layers ran about twice as slowly. And then we can also visualize, all of our other displays also give us more information. So if we wanted to look at like all the biases, we could see how they varied for different models. And let's see, conv1/bias maybe. And so that's kind of interesting that we can see that different models actually had very different patterns for how the biases evolved over time. And probably by digging into this, we could learn some ways in which the models are actually structurally different. Similarly, in the graph visualizer, we can explore the different runs. So we can see here that right now we have one of the models that had only one convolutional layer and only one fully connected layer. But we could go and compare it to different models instead. So the final thing, major feature from TensorBoard that I'm going to describe is the embedding visualizer. And it's maybe the coolest piece of TensorBoard. What the embedding visualizer basically does is it lets you take high-dimensional data and then project it down into 3 dimensions. Now, the way in which we might be really interested in doing this is when we take our input data set and we map it through the neural network to, say, the final layer. That embedding is actually the learned representation of how our neural network is processing the information. So I'm going to throw a bunch of code on the screen, and I'm not going to explain it in great depth, but I will say there's a wonderful tutorial on the embedding visualizer on the website. But basically what we're going to do is we're going to make a variable that will hold the embedding of each of our test set images. And then we're going to create a configuration object that has a little bit of information like where can we find a sprite PNG of all the MNIST images so we can display thumbnails in the browser, and where are we finding the labels so that we can organize the examples by which label they are. And then we write this all to disk using the file writer. And now every 500 steps, we're going to save a model checkpoint. And this model checkpoint contains all of the variables in our model, including that embedding variable. And then finally, we turn on TensorBoard once again, pointing to this directory. And here we have our embedding. This is 1,024 points from MNIST that I decided to use from the test set. And what we're looking at right now is the principal component analysis of the embedding. So we've taken the top 3 principal components and laid out these points in 3-dimensional manifold. So if we color by label, we can already see that it's learned a pretty useful separation. Like all of the ones have been separated on one of these principal components, and then like there's kind of one principal component that has the 9s and the 7s, which makes sense since they're kind of similar. And then on the opposite end of that principal component, you have more like 2s and 3s and 8s. But we can do even better than this. We can use my personal favorite feature here, which is tsne. So this is going to go and reorganize the data set so that it preserves local similarity. And then we get this really cool visualization that shows us kind of which pieces of data were locally connected in the manifold, in the embedding. So we can see, for example, that the 1s got really nicely clustered on their own, which makes sense since 1s are a very distinct digit. And we can see that it has a little bit more trouble, for example, with the 3s and the 8s and the 5s. Those are a little bit closer and a little bit more intermingled. And we can even start to dive into individual examples where the model made a bad prediction. So if we look, for example, at this 7, it's clustered with the 1s, so that's almost certainly a test error, whenever it incorrectly labels this 7 as a 1. But as we zoom in on this particular 7, it really does kind of look like a 1. It's probably the one-iest 7 that I've seen. So it makes sense that the model is making that mistake. And similarly, if we look at this 9, it really looks like a 1. This 4, I think, really is a 4, so maybe the model just has kind of an issue there. The embedding visualizer can also be used for a lot more than just images. So it's really useful for visualizing vocabularies as well. And I'll actually just show you an example. This is the smart reply data set. So every time that your inbox app suggests like saying thank you to someone, it's using this data set. And we can see here that we have like exclamatory statements are over here, like please confirm now, please confirm you got it. And then this axis has like less exclamatory stuff. And we can even do stuff like creating our own axes. So if you know the king-queen example, where you take a word-to-vec embedding, and you set one axis as king minus queen, and then you find that it's learned a lot of like gender-related concepts, you can interactively explore relationships like that using the embedding visualizer by defining your axes to be the differences between different words. So I'm almost out of time, but I'll talk a little bit about the future of TensorBoard. We're going to be, in the next quarter or so, integrating the new TensorFlow debugger into TensorBoard. So that means you'll start to be able to use the graph visualizer to do things like get an immediate view of where there are any nans or infinities anywhere in your graph, and if so, like when did they appear? Or you'll be able to use the graph visualizer to click on individual tensors and visualize them. We're also doing a bunch of work on plugins. If you remember, I said we're adding a new summary op that can write out any kind of data in TensorFlow. And the idea there is that we can start to have people contribute visualizations that will be really specific to particular problem domains. So if you go to distill.pub, you'll see that Chris Ola and company have made like amazing visualizations for inspecting handwriting models or for inspecting speech-to-text models. And we want to be able to incorporate these really domain-specific visualizations into TensorBoard. And we're going to do that by making it easy to add plugins. And finally, we're creating something I'll call organization scale TensorBoard. Right now, as you saw, TensorBoard is something that sort of one person locally turns on their own machine. And we're going to create a scalable productionized instance so that your entire organization or your entire research group could share a single TensorBoard and then like share results easily and keep a history over time. So that's it for my talk. The codes and slides are on this link. It's also on my GitHub, Dandelion Manet, and I think we'll tweet this link out. And so next, I'm going to introduce Martin Vicke. Martin is undoubtedly the most handsome, best dressed, and most intelligent person on the team. And he's also my boss. And he owns all of TensorFlow open sourcing, and he's going to tell us a bit about new APIs that make doing all this MNIST code much easier and much less complicated than in my example. Thank you very much.
Setting up there is, oh, already done. That was quick. Dan mentioned it, things will be tweeted out. If you want to tweet something, use TF Dev Summit and people can see it. A quick shout out to all the people who've joined us in viewing parties all around the world, literally. It's awesome to have you all here, and of course with the live stream, that's not limited to physical presence. Okay, I think I'm all set up. Thanks very much. I'm Martin Vicke. I'm going to talk about high-level APIs, and so really, why would you do that? TensorFlow is perfect. Well, so if shortly after we released TensorFlow, really what got a lot of nice reviews, and then some of the things people said, well, it's really low level. And this is my favorite quote about this. The first thing you realize of TensorFlow, it's really low level library, meaning you'll be multiplying matrices and vectors. Now, there's nothing wrong with multiplying matrices and vectors. In fact, it is one of TensorFlow's great strengths that you can do this at a very low level. It allows us to be very flexible. You can easily combine TensorFlow operators to create any algorithm you can think of, because they're at a very low level. You don't have to fit them together awkwardly. It's very clear what a matmul does. It'll always be a matmul. It's used in many algorithms, so you can just use it to do whatever you want. It's also extensible, so you can recombine these small little packets of code in arbitrary ways, and then you can create new algorithms without having to change core TensorFlow, which is great. And so a lot of actually our Python API is built that way, where we have taken the op kernels or the ops and combined them simply in Python to create new functionality. And as you will see, we'll use it extensively to make high-level APIs. It's also maintainable. So we have some history with this at Google, obviously, and other people have probably experienced this as well. If you have large fused operations, they accumulate features. And as they accumulate features, they accumulate CRUD, and things go out of fashion. And you end up with these large, unwieldy pieces. And so we avoid that completely by having these small operations that are really timeless. Nothing much was going to change to a matmul. It's always going to be matmul, so that's great. However, of course, this also has advantages. And it has advantages for our users. And one of them is that we lack higher-level primitives in core TensorFlow if we only stay at this very low level. And we may have all the tools you need to build your model, but you may be working at a level of abstraction that's actually not suitable for the kind of thinking that you're doing. And then also, we cannot really publish out-of-the-box algorithms this way. And this is why we are building a higher-level API for TensorFlow. So starting in 1.0, we're creating this high-level API. We're building this API by taking components that have been built over time by other people. Now, the idea of building higher-level APIs on top of TensorFlow is not particularly novel. So lots of people have done it. Much of that has happened in Contrib, in our Contrib part of TensorFlow. So there's been TF-Contrib Learn, TF-Contrib Slim, skflow, which is integrated in TF-Contrib Learn. And we're taking the pieces of those and making a fully supported high-level API inside of core TensorFlow. Now what that should give you is you will be able to iterate faster over model architectures or in general things that you may want to build with TensorFlow. Those higher level abstractions will allow us to encode best practices for you, so it's harder for you to make mistakes. And we'll be able to provide primitives that'll make it really easy for you to write code that's scalable right out the door. And you don't have to re-engineer it once you realize, oh, a single machine is not enough, or a single GPU is not enough. And then finally, we'll prepare all of this code to make it really easy for you to deploy. So at the level of abstraction that we'll be talking about, you'll be able to say, okay, export this to serving, and you'll hear a whole talk about how to serve models later. Export this to serving, and it'll just work. That is the promise. So how do we do this? So this, you've seen this before. Razat's talked about it. This is a very popular illustration, and what we're doing is on the bottom you have TensorFlow that you know about, the op kernels, the TensorFlow engine, and then the front ends that you're typically dealing with, and all of the things that I'm going to be talking about today are built on the Python front end. So the first step is to build a higher level of abstraction for building models, and we call this the layers. It is modeled after neural network layers, but it's not limited to neural networks necessarily. And basically larger pieces of code that are grouped together in sensible ways. And on top of that, we offer Estimator, which is a class that streamlines all of the things that you have to do in order to actually train and evaluate a model, which is most of the work. The actual model architecture is usually not all that complicated. And for simple cases, you're also going to be able to use the Keras model. And again, there's a talk directly after this one about Keras. And if you're interested in Keras, if you're a user of Keras, you should definitely wait for that. There's going to be a lot more detail. So for simple cases, you can use the Keras model. The estimator is a little more production-oriented or more for complex cases. And then finally, we have now this estimator interface, which is nice, and we can offer you models that are completely built out of the box, ready to go. And there's a number of talks in the afternoon that actually will talk about how what kind of models are offered and how they work. Okay, so let me start by introducing layers. So you've seen this before as well in Dandelion's talk. This is a convolutional network that is used for, well, this particular one I think is used on MNIST. This is written down in a way that you may see it written down in a paper. This could be an illustration in a paper, except for the color scheme. And our goal would be that you can write this network down in code without switching levels of abstraction here. So I want each of these layers in the neural network to be represented with a single function in my code. So if I have a convolutional layer, I want there to be a convolutional layer function that does the same thing conceptually, and that I can just use and replace my illustration with some code. So if I have a convolution layer, a convolution function. If I have a pooling layer, I make a pooling function, and so on and so on and so on. I've added dropout. That's the only difference to the one that you've seen earlier, I think, because dropout is better. Okay, so now if you write your models this way, what happens is that you avoid a whole lot of cognitive load. You don't have to worry so much about, oh, I have to make variables, I have to call this function, that function, reshape. All of this is done for you, and there's a lot of things that you probably wouldn't have done if you wrote it from scratch that are really useful to have. So again, you will be able to iterate much faster using this type of working, and then we introduce, or we encode these best practices for you. And a big one is scoping. So you've seen that the graph visualizer actually uses scopes to group nodes in the graph together, so it's easier to get an overview over big networks. All of that is done for you if you use layers. So each layer will show up as a little box. And only if you want to inspect the actual going on inside, which you probably don't, you have to move in. All the layers support variable batch size. So once you move it to serving, you don't have to re-engineer your model because suddenly you don't have a batch size of 32, you have a batch size of 1. All these kind of things are things that are easy to forget, but we do them for you, so it's okay. I want to mention that all of these layers are compatible with Keras. So if you use one of these functional layers, that is in fact equivalent. In fact, the implementation is shared to saying use a dense layer object that is in Keras style and apply it to the same inputs. And you'll hear about this in the next talk, but soon we'll be able to, we'll have a Keras module that is just completely compatible with the Keras API. And François will talk about this in much more detail, so I'll leave it alone. Okay, so this now makes it really easy to build models, but models are really only a small part of the total effort. The real effort is to getting them to train, and then maybe getting them to train in a distributed manner. And that's what Estimator is for. Estimator is an interface for to abstract away what the actual implementation will look like. So to start, let's consider a generic model. Any machine learning model will look somewhat like this. You'll have some inputs, possibly labels if it's supervised learning. There's some sort of model and it produces predictions. Now if that is trainable, then this looks a little bit different, where instead of predictions you can also produce some sort of training operations. Often this training operation is built on the predictions, but it's not necessarily so. And in TensorFlow land, what that looks like is that you have a train op that you call in a loop. And each time you call it in a loop, probably it's going to be feed a mini batch or absorb a mini batch and then update the weights of the model somehow. And we're not going to take a position on what that op looks like exactly, but it exists, and it's going to be run in the loop. Of course, if you're doing machine learning, you also want to evaluate, and while for small or for simple cases, you can use the predictions to evaluate and just feed some test data into it, in more general cases, it's very useful to have a separate evaluation graph or evaluation op that produces your evaluation metrics. And again, because your evaluation data set may not fit in memory, you want to run this in a loop and feed it mini batches. So basically, what we're saying here for Estimator is that every model looks like this. And so we draw a box around it and we call it Estimator. An Estimator is really going to be configured using this model function, which effectively contains the code that you have written anyway, which produces this training op, this eval op, these predictions. But it's just a single function, you pass it to Estimator, and then what you get in return is an interface that always stays the same, and that you can write downstream infrastructure against. And that takes away some of the work that you would otherwise have to do manually in every time you have a model. So in particular, it encapsulated all the information and all the necessary code about sessions and graphs, and it has the loops inside of it, so that you don't have to write them. Writing these loops properly is error-prone, and by using an estimator, you don't have to worry about this. You worry about what you actually care about, which is the details of your model. So there's one more thing that we added, which makes sense only in the context of TensorFlow, which is that you can export your model to a saved model, which is a data format that is directly usable in TensorFlow serving, which you'll hear about later. Okay, so this again, it encodes best practices. It deals with end of input exceptions. It deals with workers going down in a distributed setting. It produces the right summaries at the right time. All these things. You can easily deploy it to serving by simply calling the export saved model and using that saved model on the model server. And it's scalable by design. So what you get for free here is if you have a model that you can distribute using data parallelism, this will simply work, and you won't have to worry about it. So now I will tell you about some models that we have built. And I won't tell you about the details. You'll hear more about that in the afternoon. And I won't bore you with more diagrams, but let's just see some code. So here is a more or less complete piece of code that lets you write a linear model. It's a very simple model, linear model. And you see the class name here is linear regressor, so that is one of our canned estimators. It is an estimator in the is instance sense, but it has a slightly different interface. It has the same interface, but it has a slightly different constructor. The only thing I have to tell this estimator is what inputs do you want, or do I want you to work on? And for this, we have made this declarative language to specify input data, which is feature columns. And here in this example, I just say, well, this model expects a thing called area is going to be a real number. And if you were to parse it out of an input stream of some sort, let's say a TF example, the field it has in there is square foot. Square foot. Then there is another real number, and the name is num_rooms. And then there is an integerized feature, which is really a string that I treat as an integer, and I know that it's never going to be higher than 100,000. That's the zip code. Now, feature integerization is a little bit, it's not entirely straightforward if you were to do it yourself, so you can think of this as a one-hot vector that comes in, although it's not implemented that way because that would be terribly inefficient. But again, you don't really have to worry about that. So now, all I need to do is I already have an estimator here, so I just have to call fit and predict on it. The interface always stays the same, which is nice because if I want to experiment with different ones, I can simply say, oh, let me swap that out. Instead of a linear model, I want a DNN model, so a dense neural network. And then all I have to do is change the class name. And this is a more complex model, so it has actually some hyperparameters. And in this case, I can say, oh, how many units or how many layers do I want in this model and how many units should they have? And otherwise, it really stays the same. The only difference here, and it's worth pointing out, that dense neural networks really don't like getting integerized features directly or large one-hot features directly. So instead, I'm going to embed this. And again, using this nice declarative language for input specification, I can just say, oh, make an embedding column out of this integerized feature, and then we're done. And this embeds it into 8 dimensions, so it's very straightforward. Now all I have to do is make sure that the input functions actually produce features of that name, and I'm good to go. So really the only question that remains is, when can I have it? So right now, with 1.0, which I think should be released as of right now or something, I skipped the last 20 minutes of releasing this. You have layers in core. And the distinction between core and contrib is really in core, things don't change. Things are backwards compatible until release 2.0, and nobody's thinking about that right now. So if you have something in core, it's stable, you should use it. If you have something in contrib, the API may change, and depending on your needs, you may or may not want to use it. So layers are in core, they're stable. Estimators and canned estimators right now are still in contrib. We anticipate that we move estimator, the base estimator, the custom estimator, into core at 1.1. Canned estimator will still be in contrib, and they will move to core subsequently. So in 1.2, we expect to have some of them in, and then there will be more, and we'll keep building more, and you'll hear about it in the afternoon, how many we have already. Traditionally, these roadmap, these releases have happened 6 to 8 weeks apart. So that's kind of the timeline you're looking at. All right, and with that, I am done. And the next talk will be by François, author of Keras, about Keras. Thank you.
Hi everyone, I'm François and I'll be telling you about the integration of the Keras API into TensorFlow. So first of all, what is Keras? If you know about TensorFlow, you probably also know about Keras, but just in case, for those who don't know, Keras is an API that makes building deep learning models easier and faster. So it's a deep learning toolbox, and it's all about ease of use, reducing complexity, reducing cognitive load. And if you make deep learning easier to use, what happens is that you're also making it accessible to more people. So the key idea with Keras is to put deep learning into the hands of everyone. We believe that in the future, deep learning will be part of every developer's toolbox. It will not just be a tool for experts and researchers. It will be into everyone's hands. And this will happen with platforms like TensorFlow and APIs like Keras. So Keras is better understood not as a library or as a code base. It's more of an API spec. And it's an API spec that has several different implementations. There's the Theano implementations, which was the original Keras iteration that I released 2 years ago. There's a TensorFlow implementation, of course, and then there will be more implementations in the future. For instance, Microsoft is working on a CNTK implementation of Keras. And so until now, the TensorFlow implementation existed as a separate open source repository with lots of users. And what we are doing now is that we are bringing the Keras API directly into the Keras project, into the TensorFlow project. And we believe that's a big step towards making TensorFlow and deep learning accessible to everyone. So what's concretely happening is that we are bringing into TensorFlow this Keras compatibility module, tf.keras, which is an implementation of the Keras spec that's built from the ground up for TensorFlow. And so as part of this move, we are introducing into core TensorFlow new data structures, like layers, which Martin just introduced, and also models, which are containers for graphs of layers. So these used to be Keras data structures, and now they will be shared between core TensorFlow and this tf.keras module. And so because this Keras implementation is built from the ground up on top of these shared data structures, it is fully compatible with all of the TensorFlow functionality. That means it's also compatible with advanced features, such as the experiment API that Martin introduced. So if you are a Keras user, here's what this means for you. First, it gives you access to more flexibility. You become able to very easily mix and match pure TensorFlow functionality with Keras functionality, so you can build more powerful, more flexible models. And what's more, you gain access to really advanced, really powerful features through the high-level TensorFlow training API that Martin mentioned. You gain access to very quick and easy distributed training for your Keras models. You gain access to training on CloudML, distributed hyperparameter tuning, which is really, really powerful. And you can very easily deploy your Keras models to production with TensorFlow serving. If you're a TensorFlow user, what does this change means to you? Basically, it gives you access to the full scope of the Keras API to make your life easier without leaving your existing TensorFlow workflow. So you can just start using the Keras API at no loss of flexibility. You don't have to adopt all of Keras. You can just adopt the layers you need, for instance. And also, it gives you access to any existing piece of open source Keras code. You can just go on GitHub, copy some piece of Keras code, drop it into your code base, and by just changing the imports, it will just work. So this gives you access to a lot of existing open source code that you can start leveraging into your TensorFlow workflow. So to make things a bit more concrete, I will walk you through an example of what your workflow will look like when using Keras with TensorFlow. And we'll be looking at a video question answering model, and we'll be using Keras to define a model to solve this problem, and we'll be training it using the high-level TensorFlow training API in a distributed setting. So this is a problem that we'll be looking at. We have some videos which are sampled at about 4 frames per second, roughly 10 seconds per video, so we have about 40 frames per video. And we are asking questions about the video, about what's going on in the video, about the contents. Like here we have this video of a woman packing objects into a car. You can ask, what is the woman doing? What's the color of her shirt? And the answer should be a single word. So we'll build a deep learning model that will take as inputs the video as a sequence of frames, so about 40 frames in order, and the question, and the model should output one word, the answer. And so if you look at this question, what's the woman doing? She's packing. It's actually interesting because if you only take one frame and try to train a ConvNet, for instance, to answer the question, the problem is that just from one frame, she could also be unpacking as well, right? And the reason you know she's actually packing is because the order of the frames. Like if you look at the second frame, the rug is outside the car, and the next frame is inside the car. And so we expect our deep learning model to be able to leverage this order to correctly answer this type of question. So needless to say, this is a tremendously difficult problem. And just a few years ago, like 3 or 4 years ago, before TensorFlow, before Keras, this would only have been accessible to a handful of large companies or very well-funded research labs, especially if you wanted to make your model train on a cluster of GPUs. And now, with TensorFlow as a platform and with Keras as an API, we are making this really difficult problem accessible to anyone with just basic Python scripting abilities. So we are putting the full power of deep learning into the hands of everyone. So here's a model that we will use to solve this problem. At a high level, it has 2 branches. There's one branch that's meant to encode the video input into a single vector, and one branch meant to encode the question, so a sequence of words, into a single vector. So we have one vector encoding information about the entire video, one vector encoding information about the entire question. And then we concatenate these 2 vectors. And this gives us one single vector that encodes information about the entire problem, about the combination of the video and the question. And that's kind of the beauty and the magic of deep learning, is that you take perceptual inputs, like a video, for instance, you take semantic meaning, and you're embedding this perceptual input. And you're embedding this meaning into a geometric space. You're turning meaning into vectors. And then you can learn interesting transformations of these geometric spaces. So that's really like the beauty of deep learning. And so in our case, we'll be taking this vector encoding the entire problem, and we'll be training a fully connected classifier on top, and it will end up with a softmax over a predefined vocabulary. And so the word with the highest probability in this vocabulary will be the answer to the question. So now if you want to look at a higher level of detail, how do we turn a video into a single vector? How do we turn a question into a vector? So for the video, we're starting out with the video as a sequence of frames. So each frame is just an image. So it's RGB, it has a height, a width, a depth, color depth. You have a sequence of frames. You use a convnet to transform each frame into a single vector. So essentially, you're using the convolutional base of a pre-trained network, and you do some pooling to extract one vector that encodes the visual contents of the frame. And so what you get out of this is the video encoded as a sequence of vectors, where each vector encodes the visual contents of one frame. And then you take this sequence and you run it through an LSTM. So you probably know what an LSTM is, but basically it's a recurrent type of network that can process sequences and takes into account order, right? And this LSTM will output a single vector encoding information about the entire video. And for the question, to turn a question into a vector, we are following a very similar process. We represent our question as a sequence of integers, each integer standing for a word. And then we map each word to a word vector via a process called embedding, right? So we get out of this a sequence of words expressed as a sequence of vectors. We run it through a different LSTM layer, which will encode the entire question as a single vector. So in Keras, here's the architecture that we would use to implement this model. And it's literally just a very simple translation of the previous graph. So for the video encoder, basically we're starting from the video as a 5D tensor. So the first axis will be the batch axis. Then you have the time axis. Then you have a 3D tensor which encodes a frame. And so we will apply an inception V3 network pre-trained on ImageNet to every frame of this 5D tensor to extract one vector, one feature vector per frame. And so out of this, we get a sequence of visual vectors, which we run through an LSTM layer. And for the question embedding part, we are simply using an embedding layer to map our question, so a sequence of integers, into a sequence of vectors, and we run that through an LSTM layer. Finally, we use a concat operation to bring together these 2 vectors, and we stack a few dense layers, and we end up with a softmax over our predefined vocabulary. And we are training that with a target answer word encoded as one hot vector. So what does the implementation look like? It's very simple. This is what you're seeing here is the video encoder in just 5 lines. So in the first line, you're just specifying the shape of your video input. So it's a 5D tensor with a shape argument. You do not actually specify the batch size. So the first axis, set to none, is a time axis. So it's set to none because we want it to be variable. We want this model to be able to process videos of any number of frames. And then you have the shape of a single frame. So a single frame is 150 by 150 RGB image. So it's a tensor that's 150 by 150 by 3. In the next line, what we are doing in a single line is instantiating an inception V3 network that will automatically load pre-trained weights, so train on ImageNet, and we'll configure this network to be doing visual feature extraction. So essentially, we'll not be including the classifier part of Inception V3, only in the convolutional base, and we'll applying some average pooling on top of the bottleneck layer to just extract one single vector per image input. Then in the next line, we are setting this covenant to be non-trainable. So what this means is that during training, we'll not be updating the weights. And why? Simply because it's a pre-trained model. And if you were to update its weights while training on this new problem of question answering, we'll likely be wrecking the representations that this model has already learned on ImageNet. So you don't want to do that. You just freeze it. And so what the next step is to use a time-distributed layer to essentially take this covenant and apply it to every step of the time axis of the video input. So this time-distributed layer just takes this covenant and apply it to every frame. And what comes out of this layer is simply a 3D tensor, which is a sequence of visual frames, a sequence of visual vectors, so each vector standing for one frame. And finally, we run this sequence tensor through an LSTM layer, and this gives us one single vector encoding the entire video. And as you can notice, when we are instantiating this Keras LSTM layer, we only specify one parameter, which is the number of units in the LSTM layer. And if you think about it, that's quite remarkable because there are so many advanced configuration parameters in this LSTM layer. There are a lot of best practices you have to follow when using LSTMs. For instance, you have to remember that your recurrent weights should be initialized with an orthogonal initialization. And you have to remember that the bias of the forget gate should be initialized to 1. This type of best practices that you really need to follow if you want training to go smoothly. And one key principle of Keras is that best practices are included. So every Keras layer has a well-optimized default configuration that takes into account all these best practices. So you can just rely on Keras defaults to be good default and to just get your model to train out of the box without requiring you to fine-tune every of these hyperparameters. So best practices included, and you should just care about only specifying a few key parameters, like the number of units, and everything else should just work right out of the box. So for the question encoder, it's even simpler. We just have 3 lines. First, we specify the input tensors of the question. So every question will just be a sequence of at most 100 integers. So we'll be limited to questions that are 100 words long. And then we embed every integer into a word vector via this embedding layer. And note that we use masking on this embedding layer, which means that, for instance, if we do left padding on our questions, which means that if the questions are shorter than 100 words, we will just pad the rest with zeros to get to 100. And this creates a mask which will be propagated to the recurrent layer right after that. And so we finally encode this sequence of word vectors into a single vector via another LSTM layer. So note that when we're using this pre-trained inception network, it's absolutely fundamental to be loading these pre-trained weights because you're dealing with a fairly small data set, and this data set alone would not have enough data to allow you to learn to extract interesting visual features. So you really need to make this network actually train. You really need to be leveraging these pre-trained weights. And so finally, this is how you end up with the answer word. You are taking the video vector and the question vector, you are concatenating them with just a concat operation. And finally, you are applying a couple of dense layers. and you're ending up with 1,000 units. So we'll have a vocabulary of possible answers that is just 1,000 different words. And here's a step where you're specifying the training configuration of your network. So you're just instantiating a model, which is a container for a graph of layers. And you're instantiating them by just specifying what are the inputs of the model, what are the outputs. You can have any number of inputs, any number of outputs. And you are telling the model that it should use the ADAM optimizer during training. And this allows softmax cross-enterprise logits. Like you can notice that when specifying our classification layer with 1,000 units, we did not specify any activation. So it's actually a purely linear layer. The softmax activation will be included with the loss. And so to sum up, this is our entire code. It's just in about 15 lines, so it's very, very short. So we are essentially turning this very complex architecture, including loading pre-trained weights, into just a handful of lines. So really reducing complexity, and by allowing you to rely on default configurations for every layer, we are really reducing cognitive load. You don't have to care about most of the parameters of your LSTM layer, for instance. And the best part of it, the most magic part, is that because this implementation of Keras is built from the ground up for TensorFlow, it's fully compatible with things like estimators and experiments. So in just one line, you can instantiate a TensorFlow experiment. And this gives you access to distributed training, to training on CloudML, and so on, and also access to TensorFlow serving. So in just a few lines, you can start running your experiment associated with your question answering model, reading your video data and question data and answer data from a Panda data frame. You can start running it on a cluster of GPUs in just a few lines. So what you should take away from this talk is very simple. We are taking the Keras API. We are bringing it into TensorFlow. It's a new implementation of Keras built from the ground up for TensorFlow. And this gives you, as a Keras user, more flexibility. You can start mixing and matching pure TensorFlow functionality with your Keras model. As a TensorFlow user, this gives you access to the full Keras API to make your life easier. And so you can expect this Keras compatibility module to exist as tf.contrib.keras by TF 1.1. And finally, tf.keras in TensorFlow 1.2. And so we believe this is a big step towards making TensorFlow and deep learning accessible to everyone. So that's it for me. I believe next we have some snacks. Thank you for listening.
Thank you very much. That was great. I'll take that. Take that. We're good. All right, everyone. We've hit the end of our first round of talks. We're going to have about a 20-minute break, which is pretty fast. So everybody get up, get out there, get a break, get back. When we come back, we're going to hear from DeepMind. We're going to hear about skin cancer research, and we're going to hear about mobile. So one last thing, when you guys come back in, pack tightly. We've got a couple little holes, and we have a lot of people in the back who'd like to sit down. All right, let's come back soon. And on the live stream, see you soon.
Hello, everyone. Hello. Welcome back. I'm absolutely thrilled to introduce our next speaker. Daniel Vizentine from DeepMind Applied is here to tell you about some of the many different ways that TensorFlow is used at DeepMind. Let's please welcome Daniel.
Thanks, Zach. G'day, everyone. So as Zach said, I'm from DeepMind's Applied Group, where I work on a team that applies DeepMind's research to machine learning and reinforcement learning, DeepMind's research in machine learning and reinforcement learning to Google's products. Today I'm going to briefly talk to you about why we chose to use TensorFlow, how we use it, and how it's helped us. So the choice of a numerical computing platform such as TensorFlow is incredibly important to us. It's how we express our ideas, and it's the piece of software our engineers and scientists spend most of their time interacting with. The quality of that platform has a direct and significant effect on the quality of our work and the speed with which we can deliver results. And there are several aspects to what we look for in that. So from flexibility, our researchers continue to concoct all these weird and wonderful networks, which we're hoping to put into use. Usability. Using this platform has to be easy and natural. Simple things like getting some embeddings and passing them through a feed-forward network have to be trivial. Composing things should be easy. We should be able to take all these components which people are developing and knock them together to create new things. We need to be able to reach into the guts of that network to see what it's doing. And we need tools for visualizing and debugging what's going on. The platform also has to be scalable. We see this move towards increasingly more data, increasingly larger networks trained on more powerful accelerators across multiple servers. And the more that trend continues, the better. We need to be performant. So training machine learning models is the new compile-link cycle. It often takes days or even weeks for us to get results, which reduces the speed with which we can iterate and try new things. So the faster it goes, the faster we can develop. It's also important at serve time, where latency is a critical factor in what we can do. We often have quite tight latency boundaries. The more performant the model is, the more expressive and more computationally powerful models we can use, which will give us bigger accuracy gains. Also with training, performance matters because when we're training on real data at serve time, the speed with which we can train affects the freshness of the model, which often has downstream effects on our accuracy at serve time. And finally, production readiness. We often spend all this time doing research and evaluation and experimentation of our models, and when we finally come up with a good thing, we want to get it into production as soon as possible to do live experiments and ultimately scale it up to all the traffic that we have. So previously at DeepMind, our projects were all implemented in either Torch or Disbelief. As TensorFlow began to mature and head towards its first open source release, we started looking at it as an interesting thing. In the Applied Group, we began experimenting with it by trying a few new projects. Meanwhile, the research team, who have this very stable, much-used code base they needed to think about, began by carefully evaluating the suitability by re-implementing several existing projects. Based on the results of that, we decided that TensorFlow was the way forward, and so we started to migrate. So over the past year or so, we've been working on that process, and as of today, most of our code that we currently use is in TensorFlow, and all the stuff, the significant amount of stuff we're building from now on will be in TensorFlow. What's quite cool about this is we made this decision a year and a half ago, and since then, the TensorFlow and the ecosystem around it has improved beyond our expectations, so we're even more happy with this decision now than we were then. So I'm going to spend the rest of my time talking a bit more specifically about how we use TensorFlow and how it helps us. And since I'm from the Applied Group, I'll start there. So one of the coolest things we've done recently is on optimizing the energy usage in Google's data centers. This began when the technical infrastructure team came to us after seeing the AlphaGo matches and wondered how we could use RL to control the data centers more efficiently. So we worked with them, and subsequently we worked with teams in Google Brain to build models to control the cooling infrastructure. Briefly, this is what a cold aisle in one of Google's data center looks like. This is the servers. Some of them maybe are running TensorFlow and they're getting hot doing so. So we have these fans at the back which pull that cold air over the servers into this hot aisle, where it travels down and is transferred into a water cooling system. So here are some pipes and some pumps, and the pipes take the hot water from the hot aisle to the chillers on the roof, and the cold water from those chillers back to the cold aisle. And here's what those cooling towers look like. They're just big fans which take the water and cool it down into the air. So we spent a while working on this offline. We had to take into account safety. The model couldn't go and try random things, otherwise we'd break billion-dollar data centers, which is never great. And we had to work out how to do a bit of exploration as well, because if we just learned on the data which we had available, the model would probably never learn to do anything more optimal than what the human operators had done. So we iterated a bit, and when it eventually came time to experiment, we turned it on and we saw this nice drop. From my experience, it's kind of rare to see something so defined and sustained like this, so we were quite happy with it. So we had this initial result, and it came time to implement it. Because the data centers didn't really have the infrastructure set up to run and train and evaluate and verify machine learning models, we had to write a lot of this ourselves. So we did that. We took our original Torch models and moved them to TensorFlow. We built up all this training and validation and serving stuff. But over the past year, what we've witnessed is a rise, a development in these high-level APIs around TensorFlow and components like TensorFlow serving, which basically negate a lot of the work that we had to do. Which from our perspective is great, because we'd rather focus on the modeling aspects than all this kind of infrastructure stuff. Cool. So another example where TensorFlow helped us is we previously had this system called Gorilla, which stands for General Reinforcement Learning Architecture, with some extra letters thrown in there. And we wrote this initially to speed up training of DQN-style agents. So what this was a framework built on top of disbelief. We had the parameters of an agent stored across multiple parameter servers and multiple instances of that agent, pulling the parameters from that parameter server and interacting with environments to get experience. That experience was then stored in a distributed memory where multiple learners sampled from it to make updates to the model parameters, and the whole thing kind of cycled around like that. By doing it this way, we could get more experience faster because we had multiple agents, and we could learn faster because we had multiple learners. But often more than speed of convergence, we often saw that sometimes these models actually did better than models trained on single servers, and we think that had something to do with the breaking of correlations between the examples we trained on from time to time. This also was one of the inspirations for the A3C training algorithm, which our researchers later developed. So with the introduction of TensorFlow, we were able to basically deprecate this because much of the functionality is handled by TensorFlow or can be written from within TensorFlow, which is great because it's less time we need to spend on code and maintaining it, and more time we can spend on our actual projects. More generally, since we've started using TensorFlow, we've seen a reduction across the board in the amount of ancillary work we have to perform. And things are only getting better as TensorFlow and the ecosystem around it continues to develop. So one of these is the high-level APIs which are developing, which take care of a lot of the work we previously had to do to start a new project, to build a prototype, to train it and evaluate it, meaning we can spend more time on modeling. It's easy to experiment with models in TensorFlow. It's easy to put together a baseline and a couple lines of code. It's easy to change things about it. So for example, if we have a bunch of embeddings from various time series, do we want to concatenate the last 10 of them together? Do we want to convolve over them? Do we want to pass them through an LSTM to get the state? It's all just a couple lines of changes, which is quite nice. The distributed training helps us. We can try more things quicker and sooner. And finally, once we've gone through all this work and we're excited and wanting to put the model into production, TF serving kind of gets rid of a lot of the pain that was previously there. So all this amounts to a quicker development cycle, meaning we can support more projects, we can experiment more, and we can deliver quicker, which is great. And what's more, we've yet to come across an instance in any of these collaborations with Google where TensorFlow has not been suited to the problem we're working on, hasn't been flexible enough, which is great. So I'm excited about the possibilities here, and I hope we can tell you more about some of these projects soon. So the applied team is only one part of DeepMind, and our friends in research are also busy doing lots of cool stuff and have begun to take advantage of TensorFlow to do so. So one of the obvious things and one of the most exciting moments for us last year was when AlphaGo succeeded in a series of matches against Isidol, one of the greatest Go players of the last decade. What made this so exciting was it was a combination of a great technical achievement in making a strong Go player, but it also represented something of a new beginning in the game of Go. Interest boomed, Go boards sold out across the world, which is interesting. And players responded not with a sense of defeat, but they were excited about it as a new beginning because they could work with these machines to explore more deeply the mysteries of this ancient game. More to the point, AlphaGo is one of the first significant uses of TensorFlow at DeepMind, where it was used to great advantage to train these networks, powering AlphaGo. So I won't spend too much time talking about Go itself. Just suffice to say, it's a perfect information game with a very high branching factor and a lot of moves in a particular game. So your standard minimax search obviously won't work. The main component of AlphaGo was composed of these two networks, a policy network and a value network. The policy network was trained to, given a game state, work out which move the opponent was going to make. And the value network was trained to, given a game state, predict how likely we were to win that game. So naively, while you could just use the value network to evaluate your next set of moves, in practice that wasn't quite good enough for what we needed. So we resorted to a bit of a compromise using a combination of using these nets with a Monte Carlo tree search to get better results. And the way this basically works is if you do a full Monte Carlo search, that's way too many possibilities. So we use this policy network to guide the paths in this search tree to the most likely paths. And then at some point further on in one of those paths, we'd use the value network to evaluate how good that path was, meaning we didn't have to go all the way to the end. Why the value network performed better in that case is because as we unrolled these paths, more of the game had unfolded and things were more certain, so the value network had a better prediction. But the real thing where TensorFlow came in was the training of this thing, which was quite a significant, it took quite a significant amount of work. So we started by taking games from expert players and training this policy network, and then we began this iterative process where we used reinforcement learning to train a value network from that policy network, and then update the policy network to produce better moves. Previously, doing this on Torch, it was slow, and when we moved to TensorFlow, we were able to bring the whole power of distributed training to bear on this, which made it the whole thing faster and meant our researchers could iterate quicker and try new things. Another cool thing from this year was WaveNet, which we used to generate realistic audio signals. So this is hard in general because sound waves are have this complex oscillating structure with a very high sampling rate on the order of 16 kilohertz. Generating an audio signal requires a model which is able to reproduce this sort of signal at both these very fine-grained oscillations on the order of milliseconds and the whole signal over seconds, which is difficult because of the amount of information. So there were two main approaches to this previously, concatenative models and parametric models. So a concatenative model worked by having a speaker say a whole bunch of sound and chopping it up into little bits and then reassembling those to say whatever you wanted. What you often see from these is the sound seems kind of choppy because these transitions between these sound segments don't quite match up. It's also difficult to modify the voice, either adding a new speaker or altering the emphasis or emotion. Similarly, the other approach was parametric models, of which WaveNet is one, where all the information required to generate speech is stored in the parameters of the model, and you supply information about what you want to say and the characteristics of that as inputs to the model. However, prior to WaveNet, we noticed that parametric text-to-speech had tended to sound a bit less natural than concatenative models. So WaveNet changes the paradigm that was previously in parametric models by directly modeling the waveform of the audio signal one sample at a time. So as well as yielding more natural sounding speech, by directly modeling the raw waveform, it means that WaveNet can produce any kind of audio, not just speech. So the architecture for this evolved out of work on pixel RNNs and pixel CNNs, which were used for generating images. And the key piece of architecture here was the use of a dilation, a dilated convolution with an increasing, an exponentially increasing stride as the layers increased. What this allowed the model to do was to have a receptor field size that was exponential in the number of the layers in the model, which allowed it to incorporate all this information about the signal. The other cool thing about this structure is that it, in the first half of the input compared to the second half, there are twice the number of connections, meaning it uses that information to a greater degree. So here are some samples generated from the various systems. So on the left, we have audio from a concatenative model. If we can play. Go ahead. The left one, yeah.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So if you listen closely, you can perceive some of the discontinuities in the generated audio due to the slight mismatches in the transitions between the different recorded chunks. So in the middle, we have a parametric
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser,
which is less choppy, but it doesn't have that natural quality we associate with normal speech. And so finally, we have WaveNet.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser,
which compared to the other two is very smooth and natural. The only slight thing that WaveNet does is it has a bit of noise due to the sampling procedure and the neural network. So maybe if we play them all again, just so people can see here. Just from left to right. You want to play them again? Yeah, thanks.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. The Blue Lagoon is a 1980 American
Thanks. So we compared WaveNet against other models through the use of opinion scores, and what we found by human raters, and what we found was that it narrowed the gap to human speech by about 50%, which is great. And because WaveNet models they model the raw audio signal, we can also get it to produce sound other than speech. So here's an example where we trained it on a corpus of classical music. Thanks. As you can hear, it's able to generate, go back one, yeah, thanks. As you can hear, it's able to generate realistic sounding piano notes on a moment-to-moment basis. And finally, with what must be one of my favorite paper titles of the year, Learning to Learn by Gradient Descent, in which some of our researchers trained a neural network to train a neural network, which I think is a great example of the kind of flexibility that TensorFlow offers. And I think going forward, we're going to see more of this kind of crazy out there stuff, like with models, learning architectures of models adding bits and pieces to themselves and so on. And so it's exciting to see that TensorFlow can handle that. And I know, at least from us at DeepMind, that TensorFlow is going to be our choice of how we model these things going forward. So if you're interested in more details, you can look at our website, deepmind.com. There's a blog post linked here, which rounds up some of the things from last year. And we also have links to the over 100 papers that we've published so far. Thanks for listening. So up next is Brett, a current PhD student at Stanford, who's going to demonstrate how TensorFlow was used by the Artificial Intelligence Lab to classify skin cancer images.
Hi, everyone. I'm Brett Caprell. I'd like to tell you about some of the work we're doing at Stanford on skin cancer image classification. This project has been a collaboration between the Artificial Intelligence Lab and the medical school. So let me warm up with some facts to motivate the threat of skin cancer. It's the most common cancer in the United States. 1 in 5 Americans will develop skin cancer at some point in their lifetime. And in 2017, it's estimated that there will be 87,000 new cases of melanoma, which is the deadliest form of skin cancer, and almost 10,000 deaths from it. Fortunately, there's good news. There's hope. The survival rate for melanoma is 98% if you can detect it early on. Also, by 2020, it's estimated that there will be 6.1 billion smartphones in circulation globally. So this collaboration began a couple of years ago when a dermatologist at Stanford saw the recent breakthroughs in computer vision, and he emailed the director of the Artificial Intelligence Lab, and he said, if your program can differentiate between hundreds of dog breeds, I believe it could make a great contribution to dermatology. So the first step to making a contribution is acquiring a data set. So we have acquired a data set of almost 130,000 images spread out over 2,000 diseases. We worked with the medical school to clean it up and put it into this nice taxonomy, a subset of which is shown here. So in this taxonomy, you can see green nodes and red nodes. Green is safe, red is dangerous, black is deadly. And there's also some orange nodes which could go either way. It's not a clearly binary task. So on the next couple of slides, I'll show some benign and malignant lesions. So here's some malignant lesions. Here's some benign lesions. So you can kind of see, flipping back and forth, a visual distinction. But there's also some lesions that are very similar between the two, which I highlight in green, for instance. Okay, so now we have a data set. Next step is to train that. We find that training on finer classes results in better performance. So if you consider the figure shown, if we train on the green nodes, we actually train on more, like 700 of them. But just imagine we trained on the green ones. At inference time, we would sum the probabilities up the tree to the red nodes, the classes of interest. And then further, if we're interested in a binary task of distinguishing malignant melanoma from its binary lookalike, or from its benign lookalike, melanocytic benign lesions, we would renormalize the probabilities to sum to 1. And this is consistent with Bayes' rule, conditioned on the information that the disease is one of 2 things and not one of all the 9 red nodes. So we found that we got the best performance by fine-tuning an ImageNet pre-trained model. We tried a few different architectures. We trained with AlexNet, VGG Inception versions 1 and 3. We found Inception version 3 worked the best. We also tried feeding with a spatial transformer network, because many of our images have lesions taken from far away. We didn't find improved performance, and using Occam's razor, we just didn't use it. So next step is evaluation. We use 2 metrics to compare with dermatologists. Sensitivity, which is known as the true positive rate, and specificity, known as the true negative rate. So we show the doctors, dermatologists, a bunch of images of benign and malignant lesions. We can then calculate their sensitivity as the % of malignant lesions they were shown that they ordered a biopsy for. Similarly, the specificity is the % of benign lesions they were shown that they did not order a biopsy for. And if they order a biopsy, it goes to a pathologist, which results in a near perfect diagnosis. And for our network, for our classifier, we output a malignant probability. So imagine we fed the same images through, and we got the probabilities as shown. then the sensitivity would be the percent of malignant lesions that falls to the right of some chosen threshold. Similarly, the specificity would be the percent benign lesions that lie to the left of the threshold. And in this image, in this particular threshold, it would be a sensitive classifier, because almost all malignant lesions lie to the right of the threshold. And we can vary this threshold to get a whole range of sensitivity and specificity pairs. So doing that, we get these results on 3 different tasks. So the first task is the most prevalent type of skin cancer. Second task is the most dangerous type of skin cancer versus its lookalike. And the third task is the same as the second task, except it's using dermoscopy images, which are taken with a dermoscope. It's a special device that shines polarized light at the lesion to expose underlying layers of tissue. And you might think that dermoscopy is harder, but no, it's just a completely different set of lesions. And we also see that the dermatologists don't do as well on that data set. So let's see how the dermatologists do. So this is the most important slide. We can see, for one, the line is more jaggedy than the previous, and that's because this is a subset of our test set. Dermatologists have important things to do. They can't just classify thousands of images. We can do it really fast. Another thing to notice is dermatologists are actually widely varied in their performance. Anyway, from these plots, we conclude that we have achieved dermatologist-level performance at skin lesion image classification of skin cancer. So here are some confusion matrices on a 9-way classification task. It's interesting to look at these to see the similarity. One thing you might notice is that we often mispredict inflammatory in such a broad category. Another thing you can notice is that dermatologists will err on the side of guessing a benign lesion is malignant than that a malignant lesion is benign, because that would be a deadly mistake. And you can see that from this box. Anyways. Okay, so I brought a demo of this classifier. Okay, so first, let's just do a sanity check. We'll get the images out of the way. So sanity check, not skin. Okay. Yeah. All right. So this one, it can't actually read the text, but it's yeah, you can see it's malignant pigmented. Let's do a couple of these. Let's see, this one's epidermal malignant. There, that's probably good. Don't want to embarrass myself. All right. So. I just want to say I'm honored at how well received our work has been. It's remarkable that Andre and I didn't know anything about dermatology going into this, and I think that's kind of the spirit of deep learning. You can just get a large enough data set and feed it through Google's latest image classifier, fine-tune it, let them do all the hard work, take the credit. And it's just a really amazing time to be an AI researcher, as evidenced by 3 covers of Nature dedicated to breakthroughs in artificial intelligence, 2 of them here at Google. I just wanted to comment a little bit on the future of AI applied to dermatology. And I think this could also apply to other skin diseases. But there will be increased access, because a lot of people might have access to a smartphone who don't have access to a dermatologist. Also, it will be more convenient to classify your lesion. And because it's more convenient, it will hopefully lead to earlier detection. And the survival rate is much better when you detect it early. Thank you. Thanks.
Good luck, Sarah.
Thanks.
Thank you very much for sharing that research for you. I will say that from here on out, our slides will have 100% fewer lesions. So I'd like to invite onto the stage next Pete Warden, who is the lead of our mobile efforts, and he's going to tell you all about mobile TensorFlow and all the fun tricks you can do with it. Okay, good luck, sir.
Thanks so much, Wolf. Hi, so I'm Pete Warden, and I'm the only thing standing between you and lunch, so I'm going to try and talk as fast as possible. So I'm here to talk about mobile and embedded TensorFlow, using TensorFlow on mobile and embedded devices. And the first question is, why would you want to do that? Isn't TensorFlow and deep learning something that you do on massive clusters of GPU machines in big data centers in the cloud? Well, yes, it is, but it's also an incredible way of offering unique user experiences that we've never been able to offer people before by running interactively on devices that are close to data and the people that they're working on. Everything from real-time translation to predicting next words on keyboards, to helping people scan old photos with PhotoScan, to all of the amazing stuff that Snapchat is doing in real time. And as you just saw, actually trying to help detect diseases running real-time on device. So because it's so important to us and because we think it's such an important area to be working on, as you saw in the keynote, we've been working with people like Qualcomm and all sorts of other hardware manufacturers to make sure that TensorFlow runs as fast and as smoothly as possible on a whole bunch of different hardware. And once my clicker works. Yeah, the joke around the office is we may be on the way to solving AI, but AV is still well out of our reach. So I'm going to talk in a lot more depth about all the sample code and documentation and build support we have for Android, iOS, and Raspberry Pi. But if you have something that's not listed here, we really care about all the diversity of platforms that are actually emerging. So please do get in touch. We're really keen to see TensorFlow running as many places as possible. Still nothing? Yeah, still nothing. Okay, we're going to do this manually. So how can you actually get running on Android? Well, if you're an Android developer, you're probably already using Android Studio, and TensorFlow can actually be built with just a few simple steps using Android Studio directly. Yeah. So if we go back one more. So back. Yes. So here we actually show you how you can actually alter the build script to let it know where Bazel, which is the underlying build system we use to build for Android, is located in the build.gradle file that we supply as part of the sample code. And then you just add the sample folder as a new project in Android Studio and go ahead and build it. Now, if you actually want to get in a bit more depth and make alterations to TensorFlow and do more complex rebuilding, you use Bazel, which is Google's open source build tool. You grab the latest version, the URLs listed here, and you need to grab the SDKs for Android, both the SDK and the NDK for the C++ part of the building. And I like to use Android Studio's SDK manager because it makes it a lot simpler than having to figure out all the URLs. And it makes it really easy to have multiple versions lying around too. So make a note of what version of the SDK you've actually got and also where it's located on disk. And you need to add this incantation to the end of the workspace file in the source tree of TensorFlow at the root. And what this is saying is basically which API you've installed and whereabouts it's actually living. And because I actually end up doing this a lot as part of my job. I like to keep this information around as a little file snippet, which I can just do a one-line append to that workspace file whenever I set up a new source tree. And then to build the demo apps, all you have to do is call this one Bazel build line. And just as a note, this is only the workspace here, the build file here is actually only set up for Android, so you don't have to specify it. But for other tools like the benchmark and things that can be built for multiple platforms, you'll need to specify ---- config equals Android as part of the build process. So what do you get after that? The Android examples are designed to help you think about some of the different things that you can actually do using TensorFlow on device. So if you're interested in ideas on improving your apps or new things you could build, they're a great place to start. And unfortunately, this doesn't come with cake. I could do with some right now. But this is the classify example. And what this is doing is it's taking a live camera feed and it's actually trying to label images using the Inception v3 network, the same one that we saw in the previous presentation, but for the objects that are known in the ImageNet class. And one key thing about this is you can actually use the TensorFlow for Poets tutorial, which is a code lab which you can Google, and that lets you train your own model using Inception v3 with no coding required on images that you actually care about. And then you can take that model and you can drop it directly into this sample and have your own custom image recognition app with very, very little coding involved. And a couple of other details. If you play with the volume button, you'll get to see statistics about where the time is going and other debug information. And you may notice with the default ImageNet model, if you point it at people, it will come up with results that are confusing because there's no person label in the ImageNet class set. So it will show you things that it often sees together with people, like oxygen masks and seatbelts. But if you do want to recognize people, we have the app for you. And this is TF Detect. And what this is actually doing is drawing bounding boxes around any people that it actually detects in the live camera view. And here's a screenshot, but just to live really dangerously, I'm actually going to try and do a live demo that we haven't even rehearsed. So I'm going to give some offerings to the demo gods, and hopefully they will smile on us.
You ready to switch over?
I am ready to switch over.
Almost switched.
So can you... Do we need more light?
Let's see.
Well, hopefully you can see... Yeah, that actually helps. You can see my little nephew there is being detected as a person in this picture. And if you look at the bounding box, you'll see that it sort of follows him around as you sort of move the camera. So before anything goes wrong with that, I'm going to skip quickly past, since I think I got away with that. Should I bother? Yeah, I'll bother this. Yeah. Okay, let's see if this... No, clicker still... Oh! Okay. It uses tracking, which is really important when you're doing object detection, because that means you can actually know which objects are the same from frame to frame. So we include a full tracking solution as part of this demo, and it makes it really useful for doing things like counting objects, because you know when a new one appears. There isn't training for the person detection yet, but if you look in the README, you'll see that the great open source project called YOLO, which actually supports object recognition. We also support that as part of the demo. And finally, you've probably seen the Magenta group talking about stylization and style transfer. You can actually run this live on the phone using the stylize example. And because it's part of the Magenta model set, you can just grab the model directly from there and train it on any styles that you actually want to do. So if you're developing for Android, you're almost certainly writing your code in Java. And the bulk of TensorFlow's core that you're actually going to be using is written in C++. So how do you deal with that? How do you actually call TensorFlow from your app? The answer is a thing called the Android Inference Library. And if you don't want to understand what it does, you don't need to, but basically it acts as a bridge between the Android Java level and the C++. And you can actually grab a pre-built binary of this and an APK of all of the demos that I've just shown you at this URL where the nightly builds are actually put. So if you don't want to compile the library yourself, you don't want to compile the demos yourself, but you want to give them a try, this is the URL to check out. And even better, oh, go back. Even better, we actually have a full Java API that has just been created, which is going to offer a whole range of access, much beyond just like loading and running a model, which is what the inference library focuses on. So also check out the full Java API. So if you're building for mobile, you almost certainly care about iOS as well. So what can you do there? We have full support for building for iOS. We actually use a makefile to help us get this running because we call out to Xcode's command line tools. So you need to make sure that you have a recent version of Xcode running and also install a couple of dependencies you need to help makefiles actually run. And I like to use Brew because it makes life simpler, but whatever you use, just try and make sure you've got automake and libtool. And then all you have to do is run the build all ios.sh script, and it usually takes somewhere around 20 minutes. And at the end of it, you'll have a universal library implementing TensorFlow in all of the architectures plus bitcode. And just in case you need to dive a bit deeper and you need to make iterative changes to the TensorFlow library, you can run the individual steps, and they will only rebuild things that have changed. And to make sure that things run as fast as possible, by default we use the -OS flag, optimizing for size, which we also find gives a good speed profile. And we love using Apple's Accelerate framework because they offer really fast linear algebra, matrix multiply operations on iOS devices. And when you're ready to use this in your own app, you need to link against the TensorFlow library that you've just created. You also need to set up your project to link against the protobuf libraries that were created as part of the previous steps. You need to add include paths to the TensorFlow headers as part of your project so it can find the .h's. And you need to use this -force load flag as part of your linker opts when you're building your final executable. And this is mysterious, and I'm going to be explaining why you need to do this in more depth in a little bit later. But for now, just remember, do this or bad things will happen. So what can you do on iOS? Well, you can create some really, really ugly UI, which is the demo app that I first created. And all this does is has a single button, which you tap the button to run a model. It loads a picture of Admiral Grace Hopper from the assets and runs it through an inception model and prints out the label. So why does this exist? It's very simple and it's very small. So if you're looking for something to start with to look at how to integrate this into your own project, it's a very small amount of code to look at, and you'll get a good idea of how to work with it. But for something more fun, these are actually my two cats from home. And much like the Classify app that I talked about earlier, this takes a live camera feed and runs an inception network on every frame and prints out the labels on screen to show what it thinks it's found. And just like the Classify app on Android, you can take a TensorFlow for Poets trained model and drop it into the example and have it work with very, very few changes. So again, it's really easy to build your own custom image recognition app with almost no coding required. And I love the Raspberry Pi. It's a massive amount of fun. I have so many of them cluttering up my house. But it's also a really powerful platform for prototyping all sorts of devices sort of in the Internet of Things world. So it's a really important platform for us to be supporting. And the good news is that building for it, it looks a lot like a normal Linux machine that you might have in your development environment. The bad news is that it's an incredibly slow Linux machine compared to any desktop or laptop that you're used to. So the temptation might be to compile everything on your fast machine, cross-compiling for ARM and for the Raspberry Pi. But I've gone down that route, and I actually found I hit a whole bunch of very hard-to-diagnose problems. So you might have better luck, but I recommend actually building everything locally on the Raspberry Pi, even though it's going to take a few hours to run. And to build the C++ core of TensorFlow on the Raspberry Pi, you need to install a few dependencies again, and we're going to be using the makefile, so you need a few makefile dependencies. And also, if you're running on a recent version of Raspbian, make sure you install GCC 4.8 because TensorFlow has had some issues with the ARM version of 4.9. So we found switching back to 4.8 makes things a bit smoother. And just as another note as well, there's a fantastic tutorial out there if you look for it for building the whole of TensorFlow on your Raspberry Pi, including the Python parts. That requires a swap drive and about a day of compiling last time I tried it. So I like to just start off with the makefile so you can run models and do inference. And then to build it, you just run this makefile script, again specifying GCC 4.8 so that you use the version that you've just installed. And one fantastic thing about recent versions of the Raspberry Pis is that they actually have SIMD acceleration. They have neon acceleration instructions. And so if you want to take advantage of that, which you really should if you can avoid deploying on Raspberry Pi 1s, you need to specify these optimization flags. And you'll get a many times speed up compared to the normal scalar code. So what can you do on the Raspberry Pi? As is traditional at this point, we have a very small, kind of boring example to get you started called label image. And this is a small amount of code that loads an ImageNet inception model, and it will take an image file as an input, and it will run that image through and print out what the labels are. Now, for more fun, the camera example actually takes a live feed from the Raspberry Pi camera accessory, if you have one attached, and it runs it through an inception network, and it prints out the labels it finds continuously to the console. And again, just to emphasize this, you can take a model that you've trained with TensorFlow for Poets and drop it into this example and have something running that's running your custom image model for things that you actually care about. And just for fun, I have actually tried to set things up so you can just pipe on the command line the output of this tool into flight and have your Raspberry Pi sort of saying what it's seeing as you point it around the room. Okay, do you remember I mentioned ---- force load with lots of mystery? Well, you'll need to know about it when you run into this error. You've built your app successfully. You've managed to link in, get all of the header files and everything else set up. You've written the code. Everything's compiling. You run your app trying to use TensorFlow for the first time, and you get this no session factory registered error. And you're just left scratching your head, like, what's going on? Well, the punchline is, if you don't want to know the details, use -force load, or on Linux, --whole archive to link in the TensorFlow library. But why do you need to do that? So to understand that, you have to jump into how TensorFlow is built a bit more. There are actually hundreds and hundreds of components in TensorFlow, and there's no single source file which lists all of them. Instead, we have a pattern where each object, each component in the system, each module, actually advertises to the rest of the system what it can do. It registers itself to say, hey, here I am, I can implement this thing for you. And then TensorFlow as a system actually gets that full list at runtime and figures out what's actually available. And this error is a sign that the session factory, the sessions, which are some of the most basic things, the first things that TensorFlow tries to grab, the registration mechanism hasn't worked. So what do I mean by a registration mechanism? This is a super simplified example of an implementation of the multiply operation in TensorFlow. It's a C++ class that effectively has a few functions, probably the most important of which is compute, which actually takes some inputs, processes them, and puts the results into an output tensor. And in order to let the system, let the whole of TensorFlow know that this is available, there you'll see if you look in the .cc file, there's something like this register_kernel line. And the meaning of this is saying, hey, this class molkernel is available if you ever run across a graph that has a mol op in it, you can use this class to actually implement that functionality. And that's fantastic. That means that we can easily build very complex systems with no sort of single global list that we have to worry about. It's very flexible as you can swap modules in and out. But it's implemented using a bit of C++ magic. And the way that line register kernel actually works is it expands into something that's kind of a more complex version of this. And what this is doing is it's defining a class that pretty much just contains a constructor, and the constructor calls the registry method to tell the rest of TensorFlow, hey, if you've got a molop, here's a factory method, here's a small function that will return classes that will actually implement that for you. And then the real magic comes in because a global variable of that type is actually declared immediately after. So when that global variable is created, which should happen before the rest of the program is run, before main is actually run, then that registration call will be made. So by the time any user code is run, all of the objects which use this pattern will have actually called into the registry and let the registry know about them existing. But linkers are stuck in 1978 and have no idea that C++ exists. And they're extremely keen to get rid of any variables that aren't actually being used. And they look at that global that you just created. They see nobody's reading from it, nobody's writing to it, so they say, oh, great, I can just get rid of this. They don't know that it actually has a side effect in its constructor. So what happens is that all of the register calls get stripped out, and the first problem it hits is that sessions themselves aren't registered. So what do? So as I mentioned at the start, -- whole archive on Linux or - forced load on iOS or OS X is a flag that you have to put into your linker flags when you're building your executable. And this is the tricky part, because this is not something we can put into the library compilation scripts, because it's something you need to do when you're adding the TensorFlow library to your binary. So just to reiterate, you ever see the no session found error? First thing to do, go check your linker options and try putting these in to make sure that you're loading TensorFlow without the linker trying to get clever. So you've got something up and running, and you're getting ready to put your app out into the world. But you really, really care as a mobile developer about the size of your app. And Inception v3 is almost 100 megs, which is appalling if you're a mobile developer. Like, that's just mind-blowing that people could be shipping that sort of stuff around. But do not worry. We actually have a whole bunch of solutions to help you shrink the model size down by a massive amount. So to understand how that works, to get started, you need to actually run the freezegraph script to take a model from the normal checkpoint format into something that's just a single graph def, so you can do more easy processing after. Then you use the graph transform tool to actually do a whole bunch of optimizations. It's a big toolbox full of useful things for helping to speed up and tidy up your graph. But the most important one for this problem is the quantized weights transform. And by default, TensorFlow will store the weights for most models as 32-bit floating point values. And models contain millions and millions and millions of these weights, typically. So the Inception v3 has over sort of 20 million weights, which means that you end up with this very large, almost 100 meg model file in the end. But those numbers are actually usually within fairly small ranges, so you can actually compress them down to 8-bit using this quantized weights transform. And you will get a very surprisingly small loss of accuracy in most cases for a very, very big reduction in file size. And if you want to get even more fancy, this is still a very experimental feature, but we do have quantized nodes which actually does the calculations in 8-bit as well. And there's lots of asterisks next to this, depending on which model you're using, but we're working hard, and it's actually how we're doing the Qualcomm integration, for example, on their DSP. And if you're actually running into problems with RAM usage when you're actually running your app, for example, on iOS, on older devices, it can be very easy to have your app killed if you're using more than 100 megs of memory at a time. You can actually use memory mapping to avoid loading the weights explicitly into an allocated buffer in RAM, which will help a lot with both loading speed and avoiding getting killed. And at the end of it, you end up with a quantized version of Inception 3 that's just 24 megs. And if that's too big, you can actually look at older versions of Inception, like V1, which still gives pretty good accuracy, and that can be just 7 megs. So you've actually managed to get your model size down. The other side of your application bundle is how big is your binary. And another scary number, TensorFlow will increase your binary size by 12 megabytes if you just add it before you do any tuning. But do not be scared. We actually have, again, a whole bunch of ways to reduce that size by taking a few simple steps. And to understand why TensorFlow is so big, it includes hundreds and hundreds of ops. And each one of those ops has an implementation that takes up a bunch of code space. And to actually keep the size even down to 12 megs, we actually don't include some data types and some ops by default. So if you run into the no op kernel found error, you may actually want to add some .cc files to either the build files or the make file listing of files that you need to include, depending on which system you're actually using. But if you're trying to keep the binary size down, you can run this print selective registration header script on your model. And what this does is actually looks at what ops your model is using and then creates a header file that you can put in the root of your source tree, and then you specify the selective registration macro, and TensorFlow will be compiled to only include the implementations of the ops that you actually are using in your model. And for example, with Inception v3's set of ops, you can get the binary size increased to under 2 megabytes. So thanks all for listening. I know I've been keeping you from lunch, so I'll wrap up now. But I'm really excited to see everything that you guys are going to be creating. And please do get in touch and let me know how you're getting on and how we can help. Thanks, everyone.
All right, all of you are getting up, which is the right thing to do. Lunch is outside. It's please be back in your seats at 2:30, and we'll be talking about distributed TensorFlow and all kinds of fun stuff. Thanks.
Hello, everyone. Welcome back. I hope those of you here in Mountain View and at remote viewing events enjoyed the break and had a chance to get to know one another. You're all doing really interesting things with TensorFlow and with machine learning. This next set of talks is united by sort of a theme of TensorFlow in practice. First, you'll hear about distributed TensorFlow. If you have racks and racks of powerful GPUs, you might wonder, well, how do I get all these GPUs working together to train faster on larger data sets and build larger models? And Derek will be here in just a moment to tell you about that. Then you'll learn about the ecosystem of tools around TensorFlow that you might find in a production setting in a data center. How do you get all these production data sets feeding into TensorFlow, into this amazing distributed training cluster that you just learned about? After that, you'll hear about TensorFlow serving, which helps you take a trained model and then serve it at scale to many customers, especially when you have latency requirements or other details you need to deal with. And serving large numbers of customers is an important thing for TensorFlow, and we want to support you all the way from the inception of the model to the large-scale deployment to the mobile phone, as you saw earlier today. And then finally, if you have some existing production system, say with random forests that you're already happy with, but you're interested in migrating to TensorFlow, well, the final talk on the ML Toolkit will show you can take your random forest implementation and port it to TensorFlow, and then start incorporating some of the more cutting-edge deep neural network techniques that have been proving to be so powerful. So, without further ado, I'd like to introduce Derek Murray, who's one of the core engineers on the TensorFlow team, to tell you about distributed TensorFlow. Let's all welcome Derek.
Okay, hello everyone. Hope you all had a nice lunch. So as Zach said, I'm Derek Murray. I've been working on TensorFlow for a little over 2 years now. And in that time, one of the most interesting things I've worked on has been distributed TensorFlow. So that's what I'm going to be talking about today. Before I get started, I just want to get a sense of the room. So how many people here have ever written or run a distributed TensorFlow program? All right, I'm going to say that's like 5% of you, maybe. And I'm sorry to the folks on the live stream who can't put your hands up and give me this immediate feedback, but if you want to follow me on Twitter, that would send a very strong signal. Okay, so why, thank you. So why do I care so much about distributed TensorFlow? Well, it's what enables us here at Google to scale up the training and inference of machine learning models on these futuristic-looking machines in our data centers. And since we made it open source just under a year ago, you've been able to run it on your clusters at home as well. And why might you want to run TensorFlow on lots of computers at the same time? Well, Zach kind of gave you a clue in the introduction. The most common reason is that you want to increase the throughput of training your models to train them faster by harnessing a load of GPUs and train that model in parallel. So this graph is taken from our OSDI paper that we wrote last year, and it shows how the training throughput of the Inception v3 model scales up using up to 200 GPUs. And actually, this is, I think, TensorFlow 0.8, 0.9 was the version we used for this, so the numbers have only gotten better with all the improvements you heard about this morning. So the Inception model is nice because it fits neatly in a single GPU. We also have more complicated things like the neural machine translation model, which Megan mentioned in the keynote. And this model is so big it benefits from being split across up to 8 GPUs in the same server. And then we use multiple servers to train that model in parallel. If you're interested in finding out more about models like this, Eugene's going to be talking about the LSTMs that make up each layer of the translation model later on. Okay, another reason you might want to use lots of computers is that your model is so big that it doesn't fit in a single machine. So this is true for a lot of the wide and deep models that Hengsi is going to be talking about later today. And these use large embedding matrices that can be gigabytes or tens of gigabytes in size to map sparse data, like in this example, pairs of apps that users have used together, to map those down to a dense representation that we can train with a traditional deep neural network. And then why settle for very large models when you can train outrageously large models as well? So our colleague Noam Shazir has a bit of a reputation for pushing the envelope on making large models practical to train. And he uses tricks like distributed candidate sampling to scale up to very large output class sets. Recently, he's been working with a team, I think they just got a paper into ICLR 2017, to train neural networks with tens of billions of parameters, using techniques like conditional computation and mixtures of experts to get even better performance on some language modeling and translation tasks. So what all these examples have in common is that they take advantage of the flexibility distributed TensorFlow gives you to train bigger models faster and to better accuracy. And this flexibility, it's great if you're an expert user, but it can make distributed TensorFlow look a little bit daunting. It actually is a very simple, very minimalist core, but it wears a lot of the complexity of distributed computing on the outside. So while we do have some nice high-level APIs, sometimes for the really cutting-edge stuff, you have to kind of get in there and move some tensors around using the low-level TensorFlow API. And so my aim over the next 25 minutes or so is to give you a bottom-up introduction to distributed TensorFlow. I'm going to show you how the core concepts you might be used to in single-process TensorFlow translate to the distributed world. And I'll give you some ideas for how to deal with the complexity that ensues. So I just claimed that distributed TensorFlow has a minimalist core. What did I mean by that? Well, let's say I've got just one computer, and it's got a CPU device and a GPU device in it. And if I want to write a TensorFlow program to use these devices, I can put these little with tf.device annotations in my code so that for this example, the variables go on the CPU and the math goes on the GPU where it's going to run faster. Then when I come to run this program, TensorFlow splits up the graph between the devices and it puts in the necessary DMA between the devices to run it for me. Now what happens when my clicker runs out of battery? Okay, we're moving over here, I think. When we have multiple, no, is it working again? Okay, just a little bit of lag, sorry about that, folks. All right, so what happens if you have multiple machines? Let's say for reasons that will become apparent later that we want to take those variables and put them on the CPU device of a different process. Well, TensorFlow treats the remote devices exactly the same as local ones. All I have to do is add just a little bit of information to these device names, and the runtime will put the variables in a different process, splitting up the graph between the devices in the different processes and adding the necessary communication. In this case, it will be using gRPC to transfer tensors between the processes instead of DMA from the GPU device. So there you have it. Using distributed TensorFlow is just a simple matter of getting all of your device placements exactly right. And yeah, I heard a wry chuckle. Yeah, I'm sure you know exactly how easy that can be if you've ever written a TensorFlow program. All right, I should have put like a sarcasm tag in there or something. But okay, maybe we should back up a little bit and see how we can make this problem a bit simpler. Well, one thing we can do is we can take inspiration from other systems, including our previous system, which was called distbelief. And in distbelief, we had two distinct kinds of processes. We had parameter servers and worker replicas. And parameter servers are responsible for holding on to all of the model state, so the parameters, and updating them in response to incoming gradients. Whereas the worker replicas, they would do all the intensive part of the computation. So they would do the input processing, they'd calculate the loss sphere network, and they'd do the backprop to actually calculate those gradients. In TensorFlow, we can mimic this architecture by designating some of the processes to be what we call PS tasks. And we put the variables, the variable nodes and the ops that update them on those tasks. And then we put the rest of the graph, the nodes that do the pre-processing, the forward and the backprop, on the worker tasks, which tend to be more powerful and have multi-core CPUs and GPUs. And one big difference between how we did things in distbelief and in TensorFlow is that in distbelief, the parameter server and the worker replicas were two completely different programs. They were basically two loosely coupled distributed systems that had very little in common, and you would program them by a very different API. This gave, in TensorFlow, the PS and the worker tasks run exactly the same code. They are just servers that you can send little bits of TensorFlow graph to, and it will react to those bits of graph and execute them very quickly. And this gives us a lot of flexibility. So a PS task, for example, we could have it use a GPU to accelerate some of the parameter update computations. Or we could have the workers store some state locally to avoid network traffic, to cache some of the reads. Or we could even cut out the PS altogether and use direct connections between the workers if we had a network that was fast enough to deal with that communication. But with that said, the old PS worker split has been really useful for training a lot of our models. And so we've developed a decent amount of software support around this idea. And I'm going to show you now some examples of how we do that on the next few slides. All right, so the first idea that works pretty well for distributed training, particularly when a single model will fit in a single machine, is replication. So just like in disbelief, we take the compute-intensive part of the model training, the forwards and the backprop, and we make a copy of it in multiple worker tasks so that each task works on a different subset of the data. This is data parallel training like we were doing for that inception example back at the start. And the simplest way we can achieve this is by doing something I'm going to call in-graph replication. The reason for this name will hopefully become self-explanatory or maybe just explanatory when I tell you what the code does. We start by putting the variables on a PS task, like the earlier example. And this is just so that they're in a central location that they can be accessed by all of the workers. And then the easiest way to do the in-graph replication is just to split up a batch of input data into equal-sized chunks, loop over the worker tasks, and use this tf.device string here to put a subgraph on each worker to compute a partial result. And then finally, we combine together all of the partial results into a single loss value that we optimize by using a standard like TensorFlow optimizer. And sure enough, when you tell it to compute the loss, TensorFlow will split up the graph across the workers, and it will run across these worker tasks in the PS all in parallel. So in-graph replication is pretty easy to achieve. It's not a big modification to your existing programs, and it works pretty well up to a small number of replicas. If you want to replicate across all the GPUs in a single machine, then maybe in-graph replication is the way to go. But one of the things we found out when we tried to apply this technique to a large model like Inception v3, and we tried to scale it up to a couple of hundred machines, was that this graph gets really big if you have to sort of materialize all the replicas in it. And the client gets bogged down trying to sort of coordinate the computation and to build this whole graph. And that's why we came up with an alternative approach, which is called between-graph replication. This is currently what we use most internally. It's what we recommend in Cloud ML, and it's also what our high-level APIs are designed to do. So if you've ever written an MPI program, between-graph replication should be a kind of familiar concept. So instead of running one all-powerful client program that knows about all of the worker replicas, we run a smaller client program on each task. And that client program just builds up the graph for a single replica of the model. And each client program is essentially doing the same thing with one key difference in the device placement. So it takes the non-parameter part of the graph and it puts it on the local devices, or the devices that are local to that worker replica. So now when you run it, each program is running its smaller graph independently, and they get mapped to different subsets of the devices that intersect on the PS task in the middle. There's a little bit of magic here, which I should probably explain in the interest of full disclosure. So each replica places its variables on the same PS task. And when you're running in distributed mode, by default, any two clients that create a variable with the same name on the same device will share the same backing storage for that variable. And if you're doing replicated training, this is exactly what you want. So the updates from task 0, when it's applying its gradients, will be visible in task 1 and vice versa. So you'll train faster. But this brings us to another issue, which is how do you decide where to put the variables? So far, I've just been putting them on job PS task 0 and setting that as the explicit device string for the variables. But device strings, they're all very good if you want to put all of your ops in one particular location. But you often want to do things like have more than one PS task. Say if you want to distribute the work of updating the variables or distribute the network load of fetching them to the workers. So instead of passing a device string to tf.device, you can also pass a device function. And we use these to build more complicated, more sophisticated placement strategies. Device functions are pretty general, very powerful. They let you basically customize the placement of every single op in the graph. That makes them a little bit tricky to use. So one of the things we've done is to provide a few pre-canned device functions to make your life a bit easier. And the simplest of these is called tftrain replica device setter. Its job is to assign variables to PS tasks in a round-robin fashion as they're created. And one nice thing about this device function is you can just wrap your entire model building code in this with block. It only affects the variables, puts them on PS tasks, and the rest of your ops in the graph will go on a worker. So if you're doing between-graph replication, this takes care of it all for you. So for this program, it will assign devices to the parameters as they're created. So the first weight matrix will go on task 0, a bias vector will go on task 1, the second weight's on task 2, and then the second bias is back in task 0. This is obviously not an optimal balanced load for these variables, and neither in terms of the memory usage or the amount of work that would need to be done to update these variables. And just think, if we only had 2 PS tasks here, I guess I should have drawn a diagram, we'd end up with an even worse case, because all the weights would be on task 0 and all the biases would be on the other. We'd have an even bigger imbalance between those tasks. So clearly we can do better here. One of the ways that we've provided to achieve a more balanced load is to use something called a load balancing strategy. And this is an optional argument to the replica device setter. Right now we only have, I think, a simple greedy strategy that does a kind of online bin packing based on the number of bytes in your parameters. And it leads to this more balanced outcome. Each of the weight matrices is put on a separate PS task, and the biases get packed together on task 1. It's a lot more balanced, and this should give you a lot better performance. And so far, I've only talked about relatively small variables that all fit in a single task. But what about these outrageously large model parameters? Things like the large embeddings that might be tens of gigabytes in size. Well, to deal with these, we have something called partitioners, which they do exactly what it sounds like they would do. If you create a variable with a partitioner like this one here, TensorFlow will split the large logical variable into 3 concrete parts and assign them to different PS tasks. And one nice thing about doing things this way is if you take that embedding variable and then you pass it to some of the embedding related functions, like embedding lookup, for example, it will take advantage of the knowledge about the fact that it's going to be partitioned, and it will offload some of the embedding lookup computation and the gradients to the parameter server devices themselves. All right, that was a lot of detail about device placement, but it is a very big topic. I guess you could say it's a combinatorially large problem domain that we have to solve. The main thing I want you to take away is that the TF-train replica device setter is this simple heuristic that works for a lot of distributed training use cases. And you can customize it if you need to by providing these optional strategies for things like load balancing and partitioning, or even writing your own device functions that override the simple policies we provide. And this is definitely an area where we're always on the lookout for new and better device placement policies. So if you do end up implementing your own and you think it might be generally useful, we'd really encourage you to send it as a pull request, and we can add it to the set of tools that people have to make their lives easier. All right, so you've built your graph. You've got all of the devices set, and now you want to go ahead and run it. But when you create a TensorFlow session using code like this, that session will only know about the devices in a local machine. And let's say you have 200 computers sitting idle over there. How do you make it use those computers? And the answer is that you create this thing called a TensorFlow server in each of those machines. And you configure those servers in a cluster so that they can communicate over the network. Now, looking at it in more detail, the first thing we need to do is to provide a cluster spec. This is something that tells TensorFlow about the machines that you want to run on. A cluster spec is really just a dictionary that maps the names of jobs, so that's things like worker and PS in this example, to a list of 1 or more network addresses that correspond to the tasks in each job. Now, we don't actually expect you to type in all of these addresses by hand. It gets kind of error prone. But in the next talk, Jonathan's going to be showing you how a cluster manager like Kubernetes or Mesos will do this for you. And if you're using a cluster manager, internally we use a cluster manager called Borg that a lot of this stuff was inspired by. So typically your cluster manager will run an instance of your program on each machine in the cluster, giving it the same cluster spec. And then it'll start a TensorFlow server in each program. It'll pass it a particular job name and task index that matches the address of the local machine in that cluster. And then finally, when you create your session, you specify the local server's address as the target, which is what enables it to connect through that server to any of the machines mentioned in the cluster spec. And then you're good to go. So your session run call can run code on any device in the entire cluster. And typically what the worker will do is it'll start a training loop that just iterates over its partition of the data, running training op over and over again. Okay, so that's what a worker looks like. PS task is much simpler. So PS tasks simply, they have basically no client code. They just respond to incoming bits of graph that are sent to them by other workers. So in this case, you just build the server, you say it's job name PS, and then you call join on the server. And all that does is it blocks waiting for connections to come in from other nodes in the cluster. It's a bit weird, so I deal with a lot of questions on Stack Overflow, and one of the common ones is, can you show me where in the implementation of server.join the parameter server code lives? And if you go and look at it, it's like 5-10 lines of C++. It just does some error checking, and then it blocks on a couple of threads. It joins a couple of threads. That's why it's called join. It's like a reasonable misconception, because this is your PS task. What's that actually doing? Well, this highlights something quite important about how distributed TensorFlow works. So parameter servers, everything, all the behavior of a parameter server is not implemented at the low level in these servers or in the execution engine, but instead it's built out of TensorFlow programming primitives as these little bits of data flow graph that a worker ships to a server to say, manage some parameters for me and update them this way. And that representing the way we program the parameter servers as little fragments of data flow graph is what gives us the flexibility. So it lets you change everything about how parameter management is implemented. If you want to customize the optimization algorithm, or maybe change the synchronization scheme for applying the updates, you can do that just by changing the graph. And we've gained a lot of performance by doing that in some of our algorithms. All right, so now that your servers are listening, your sessions are all created, and your training loop is running, are we done? Well, whenever you run some long-running training job on a set of machines, I hope you take the wise words of Leslie Lamport to heart, and always use a saver in any long-running training process. So a saver, for those of you who haven't seen that before, is just what you use to write out a checkpoint of your model parameters to disk. The same saver can be used for local and distributed training, but it has a couple of useful features in distributed mode that I want to highlight. The first one is that you'll almost certainly want to set sharded equals true when you create your saver. So in this example, we have 3 PS tasks, and so sharded equals true tells TensorFlow, write the checkpoint in 3 shards, one each containing all the variables from one particular parameter server. And that means that the parameter servers can write directly to the file system, and we don't have to collect all of the values in one place in order to write them out. So actually the default behavior is kind of pessimal, because if you set sharded equals false, it will bring all of the variables into one save op, meaning they have to be materialized in memory at one process before it writes the first byte. And if you have these really big models, well, that's a sure way to have an out-of-memory error. So always use sharded equals true. That's if you remember one thing. Okay, second, if you are using between graph replication, you now have a choice of several worker tasks that could be responsible for writing this checkpoint. And by convention, we give some extra responsibilities to worker task 0. We just picked that because there's always a worker task 0 in our jobs, because that's where the numbering starts. And we call it the chief worker. And so the chief worker has a few sort of important maintenance tasks that it has to carry out, doing things like writing checkpoints in this case, also things like initializing the parameters at the start of day and logging summaries for TensorBoard. These are all done by the chief. And then the last thing to note is that savers now support a variety of distributed file systems. So instead of writing to a local file, you can write to Google Cloud Storage, let's say if you're running on CloudML, or if you're running on top of a Hadoop cluster, you can write straight to HDFS. And using a distributed file system here is a smart idea because it gives you more durable storage. You're not going to lose your model checkpoints if one of the machines goes on fire. It also makes it easier to read a checkpoint from another machine. So one common pattern we use is we have a separate evaluation task that's running on a separate machine, and it just goes and picks up the latest checkpoint of the model and evaluates a test set on that. So this makes that kind of loosely coupled coordination a bit easier. All right, so you're writing checkpoints now. That's a good step. That guards against failure. But what actually happens when you experience a fault? The best case, there are a few cases to consider, and the best case is that one of your non-chief workers fails. And the reason this is the best case is because these workers are typically sort of effectively stateless. So when a non-chief worker comes back up, all it has to do is contact all the PS tasks again and carry on as if nothing happened. And usually we have a cluster manager that will restart a failed process as soon as it crashes. If a PS task fails, well, that's a little worse because PS tasks are stateful. All the workers are relying on them to send their gradients and get the new values of the parameters. So in this case, the chief is responsible for noticing the failure. It interrupts training on all of the workers and restores all the PS tasks from the last checkpoint. The trickiest case is when the chief fails, because we've given all of these extra responsibilities and we need to make sure that we get back to a good state when it comes back up. So training could continue when the chief is down, but when it comes back up, we don't know if, for example, another task has failed, so it has to go and restore bits from a last checkpoint. So the thing we do is just to interrupt training when the chief fails, And when it comes back up, we restore from the checkpoint, just like a parameter server fails. This is a pretty simple and a pretty conservative scheme. And it only really works if your machines are like reliable enough that they aren't failing all the time. And it keeps the logic for recovery really, really simple. But depending on how common failures are in your cluster environment, maybe it would be beneficial to use a different policy that tries to keep the training job running without interruption. And I just want to sort of provoke some thinking here. One thing you could do is maybe use a configuration management service, something like Apache Zookeeper or etcd, to choose a chief by leader election, rather than saying it always has to be worker 0. And then if you did that, you could pass on the responsibility of being a chief when one of them fails and kind of do a failover without interrupting the training process. If somebody wanted to try that out and contribute it back, that would be just great. But if you do like that simple policy, we've got something for you. So you can use this recently added monitored training session class to automate the recovery process. So going back to our simple single process example, when you create a TensorFlow session, usually what you do is you explicitly initialize the variables or restore them from a checkpoint before you start training. And monitored training session looks a lot like a regular TF session, but you'll see that it kind of takes a little bit more information in its constructor. It needs to know if it's the chief or not. It needs to know what server you're using. And you'll note that there's no init op in the program anymore. Instead, what the monitored training session is going to do is it will automatically ensure that all of the variables have been initialized, either from their initial values, like the randomly initialized variables, or by restoring them from the latest checkpoint, if one's available, before it returns control back to the user. And it does something slightly different depending on if you're the chief or not. So if you're the chief, it's going to go and look and see if there is a checkpoint, or it's going to run the initializers. If you're not the chief, it just sits there waiting until the chief does its work, and then as soon as it's done, it can carry on running the training loop. There's a lot of potential for customization here, so we support these installable hooks that you can attach either when you create the session or before or after doing a session run call. And the monitored training session is sort of a tastefully curated set of these hooks that makes distributed training a bit easier. So it comes with standard hooks for like writing a checkpoint every 10 minutes, writing summaries every 100 steps. And if you want to, you can customize its behavior by adding more hooks or replacing the ones that are there. Okay, finally, by this point, some of you might be thinking, wow, that is a lot of effort that you have to go to just to run training on a distributed cluster. Couldn't it be easier? And yeah, well, if you do things from scratch and if you use the low-level API, there are a lot of things that you have to take care of. But fear not, because as you might remember from Martin's talk this morning, we now have these high-level APIs that have great support for training and evaluation on a single machine. And there's like TF contrib level support for training on a distributed cluster. So what does that look like? Well, this distributed training support uses a recently added class called experiment to package up the training and evaluation of an estimator using a cluster. So when you create an experiment, you bundle together an estimator with some input functions. You tell it how to read a particular data set for training and for evaluation. You give it some more configuration options. And here, like, you could specify a little canned estimator in a few lines. So this is a pre-canned DNN classifier with 2 hidden layers. You could do something more fancy by passing in a custom model function, or you could even pass a Keras model in there to do distributed training. And you wrap that in an experiment function and pass that function to something called learnrunner.run, which, if you're running on CloudML, will pick up the configuration from the environment and it will run the appropriate low-level APIs for you. So your code can be almost as simple as this. It's probably like 5 lines of boilerplate that you'd need at the top to run distributed training. Actually, I've been told, Martin told me that the contrib function, learnrunner, is going to change its name soon. So I know we're 1.0, but we still like changing names of things. This code example is a little bit more aspirational than some of the others, but hopefully it gets across the idea that the high-level APIs can take care of a lot of the gory details for you. And so, yeah, I mean, these estimators are great if your training process follows a standard pattern. And 9 times out of 10, they're probably what you're going to want to use when you're running distributed TensorFlow. So you can start getting your programs running on sort of nicely lit data centers like these in no time at all. But sometimes you're going to want to bend the rules. If you have some more complicated requirements, or you want to sort of go slightly outside think slightly outside the box. So in this talk, I've shown you how distributed TensorFlow gives you the flexibility to do just that. You can scale training out to hundreds of GPUs. You can train outrageously large models with tens of billions of parameters. And you can choose between customizing every last detail of the execution or defining the whole training process in just a few lines of code. If you are interested in learning a bit more about distributed TensorFlow, I'd encourage you to check out these links, which cover the sort of low-level system architecture, the low-level distributed API, and the high-level API. But at this point, I'd like to thank all of you in the room and on the live stream for listening. Thanks all very much. All right, so this talk was a fairly inward-looking approach to distributed TensorFlow. Jonathan now is going to tell you about how some of the great work he's been doing to interact with other sort of open-source big data projects and the other ecosystem work he's been doing. And here's the clicker for you, sir.
Thank you, Derek. Okay. Hi, I'm Jonathan. A lot of you are probably running a lot of infrastructure already in your organization, or you want to think about running various other pieces of infrastructure, and I'm going to tell you about how TensorFlow fits into that. So, the clicker.
Thank you. Sorry. That's okay.
Okay, thank you. So first I'm going to talk about all the steps you go from training to serving a model in production. And it typically involves these 3 steps. Usually the raw data that you have isn't fit for training yet, so you have to do some form of data preparation. After that, you do training, and then you serve your model. So for data preparation, there are 3 essential steps that are involved in data preparation. So you'll import the data from various sources. This might be Hive, MySQL, and so on. You'll typically perform some sort of pre-processing on the data. You'll compute aggregates or do joins. And then you'll export the file in a file format supported by TensorFlow, and I'll explain that a bit later. So a lot of people have been using typically these 3 things for doing this process: Spark, Hadoop MapReduce, or Apache Beam. And it works well with all of these at the moment. And as a visual example, we have, you're feeding in data from MySQL, say it's user data, and you have data in Hive. An example might be web impressions or web clicks. You want to join that data, compute aggregates like user data per region. Often you'll do vocabulary generation, particularly if you're using embeddings. Vocabulary generation essentially means like mapping from words to IDs, and the IDs map to an embedding. And then after that, you'll typically have a training test split. And after this process, you'll output to a file format that TensorFlow understands. And why might you want to do this? So the input file format that you use with TensorFlow actually matters quite a bit. So one example is, suppose you're training Inception on P100 GPUs. You want to keep the P100 saturated. Actually, one of the most important things you can do to make that work well is work on your input pipeline. And that involves working with queues. There are tutorials on the TensorFlow website, but specifically in this case, I'll talk about file formats. Some file formats are faster than others. We have specifically optimized the path for working with TF example and TF sequence example protocol buffers. Sequence example is typically used when you're training with RNNs, and TF records is a TensorFlow specific file format that we use with TensorFlow. And this is by far the fastest. We use this internally, and we've optimized this path pretty well. Additionally, TensorFlow also natively has ops to support reading from various file formats like CSV, JSON, fixed record length files. We have upcoming support for Avro. So you can use those. Those are a little slower, but since they're native ops, they actually work pretty well. More commonly, people, if you read examples of TensorFlow code on the web, people will be feeding data directly in Python. And this is by far the most common. It's the easiest to experiment with. It also has the most flexibility, meaning that you can use any file format that Python natively can understand, and then convert it to NumPy arrays, which can be fed as tensors in TensorFlow. It's also useful for settings like reinforcement learning, but it's also the slowest option. So if you're running experiments, this makes sense. But if you're trying to productionize a pipeline and you care about training speed, then you might want to consider switching to the first option. Okay, I'd like to mention actually why it's a bit slower. There are 2 things that are involved. reading from specific file formats using Python itself may not be too fast. So you have that part. And then when converting from NumPy arrays to TensorFlow tensors, there's a copy involved, and that induces additional overhead. So I've recommended TF record support. Hopefully at this point you're convinced. And how well does it work? So Apache Beam, as of a few weeks ago, actually has native support for this file format. But a lot of you aren't running Apache Beam, and you'll be running Hadoop MapReduce and Spark jobs already, and you just want to use that. So if you go to the ecosystem repository in the TensorFlow GitHub organization, we have code to make to work with TF records there. Note that I didn't mention protocol buffers at all. Protocol buffers actually has native support for a lot of the languages you would be using. Okay, so now that you've exported this training data, you want to go to training. There are two common ways of doing training. One is, say you have a GPU on your desktop or laptop, you want to do local training. This works well for the specific cases of debugging or working with smaller data sets. But as Megan mentioned in the intro talk, distributed training, like 64 GPUs, you actually get a 58x speedup in images processed per second if you run on distributed, like just distributed setting with 64 GPUs versus one GPU. So you train much faster. And for a lot of people in your organization, this could mean the difference of taking a month to train a model versus taking a day. And the feedback loop is pretty important to make machine learning work well in your organization. So there are two essential components if you want to start with distributed training in your organization. Derek was talking about cluster managers. We know organizations that have been using all of these to make distributed TensorFlow work well. So we'd recommend any of these. By Hadoop here, I mean Hadoop Yarn. And so we actually have configuration examples for Kubernetes and Mesos specifically in the ecosystem repository. So if you're already running that, then you can get started pretty quickly that way. But in addition to a cluster manager, you should also be running distributed storage. Derek was talking about this a little bit, but these are the ones that we work with. We added HDFS support in TensorFlow 0.11. TensorFlow also has native support for reading from Google Cloud Storage. And if you're running on Amazon's cloud service, then users have reported it working well with Amazon EFS. So the reason you would want to run distributed storage is mostly because for two reasons. For your input data, so each worker can read from a single source, and for output for your model, so for checkpoints and the exported model itself. So containers are completely optional, but highly recommended. So containers isolate your workers from their environment. And one reason this is useful is because certain jobs might have certain version dependencies that might differ from other jobs. And a specific example here is eventually we'll release TensorFlow 2.0. TensorFlow uses semantic versioning. And at 2.0, we may make some backwards incompatible changes. And suppose you want to upgrade to TensorFlow 2.0 in your organization, then the containers make it much easier to do gradual updates, because you don't have to upgrade every job at once. You can just update jobs. You can pin the jobs to a particular TensorFlow version and update each one by one. So getting started with containers makes sense. Docker is supported in both Mesos and Kubernetes, and we recommend that. So as a refresher for what Derek was talking about, I'm going to show you what distributed training code looks like, or as a refresher of what Derek mentioned, and what configuration involves. So there are essentially two types of jobs that you have, parameter servers and workers. And Derek mentioned that the most common setup, and the setup that we recommend, is between graph replication. And in that case, workers operate completely independently. So the workers don't necessarily talk to each other or even know about each other. They only communicate with the parameter servers. And for that, Derek actually showed this, but across multiple slides. This is the code involved if you're using core TensorFlow. With the higher level APIs, a lot of this goes away and becomes much fewer lines of code. But in essence, your cluster manager specifies all the other parameter servers and workers that this worker must communicate with. You start a server. If you're a parameter server, you just stop there. But if you're a worker, then you need to assign variables to parameter servers and set the worker device so that this graph belongs on this particular worker. So configuration really depends on which cluster manager and which distributed storage system you chose. We have examples, again, in that repository that I mentioned, the ecosystem repository, and we're adding more, and feel free to contribute any that you know that work well in your existing infrastructure. Additionally, I'd like to mention that Yahoo recently open sourced code to run on Spark. And why is this useful? Because you might think that Spark is like a data processing framework. Why would it be useful to run on Spark rather than a cluster manager? So Spark actually has support for running on Mesos, Yarn, or in standalone mode. And a lot of you will already be running Spark in your organization. And this actually might be the easiest way to get started. And for sure, it's difficult to run distributed TensorFlow on Hadoop Yarn. And for sure, it's much easier to get started if you're running Spark on top of Yarn than to try to run distributed TensorFlow on Yarn directly. So I'd recommend this in specific cases where you're already running Spark. And Dandelion talked about TensorBoard. You might wonder, how do you use this with distributed training? So with distributed training, typically you have output, which are summaries and events that go to a directory that you specified on distributed storage. All you need to do to run TensorBoard is run the TensorBoard command and point it to that distributed storage directory. It will start an HTTP server locally that you can just look at. You can look at your losses, you can go through the embedding visualizer, and all that stuff works. So I've skipped a lot of steps here. Like suppose you need to do hyperparameter tuning and so on, but suppose you're already done with all of that and you're happy with your model, you want to export it and serve it in production. So currently we have two common ways of doing that, but in the long term it will be one. We highly recommend you go with save model. It's going to be the standard file format for TensorFlow going forward. And the advantage to save model over everything else is that it includes all the assets you need to serve your model in production. I mentioned that vocabularies are pretty common for embeddings, and you use a specific vocabulary at training time. You want to make sure to use the exact same vocabulary at serving time. It includes all those files for you. So the other advantage to save model is it's a bunch of graphs, and you can specify which one you want to use for a particular use case. GraphDef right now is pretty common in particular uses, particularly on mobile. So in the mobile example, you typically freeze your variables into constants in your TensorFlow graph. The advantage to GraphDef right now is that GraphDef is actually a protocol buffer which acts as like a single file. So you only have to distribute a single file. That's much easier to deploy. But that advantage is going away. As of recently, you can also freeze a save model. So hopefully you've exported the save model. You want to serve it. Noah, the subsequent talk is actually going to go much more into TensorFlow serving. And I'm only going to talk about the top two here, TensorFlow serving and in-process TensorFlow. So these are both options for serving your TensorFlow model after you've exported it. But they're quite different. TensorFlow serving in its typical mode runs as a separate service that you make RPCs to. So why might you choose one over the other? So Noah's going to go much more in depth here, but serving a model actually has a lot of hidden nuance that you might not be aware of when you just think about it. So if you're just deploying a model as a one-off, then it might make sense to just use in-process TensorFlow. But if you think about, like suppose you have a job that trains every day on new data, and you want to serve a new model every day. How might you start serving that new model? You can think about it. There's like two basic ways that might happen. In your server, you can completely unload the old model, and then wait for that to finish, wait for all requests to finish, and load your new model. This is memory efficient because you only have one model loaded at a single time. Or you can simultaneously load the new model while it's running and double your memory usage. TF serving offers that as a configuration option. Additionally, for efficiency, particularly if you're serving on GPUs, you want to batch your inputs. This also has some benefit on CPUs, but particularly if you're serving on GPUs, you want to batch to fully utilize your GPUs. As you can imagine, there's some nuance to how you want to batch, particularly in low latency settings. So TF serving handles that. Also, if you're serving multiple models, isolation between those models, they're going to contend for hardware resources, and there's some difficulties in isolating between them. Particularly in TensorFlow, you have to think about which threads, like how to size thread pools and so on. You don't have to think about that if you're on TensorFlow serving at all. So that's the next talk. Now that I've explained all the benefits, you're like, okay, then why don't I just use that all the time? Why should I use in-process TensorFlow at all? So in-process TensorFlow is actually the standard mode for certain things. Specifically, if you're running on a mobile device, Pete actually went over this. Basically, you have a TensorFlow session and you run it. If you're running batch inference, like if you already have a TensorFlow model, you have a ton of data, and you want to run inference over that data using Beam or Spark, then it's much better to just use in-process TensorFlow than to start another TF serving service. There's the specific case of very strict latency requirements where you don't want to do the RPCs back and forth with TensorFlow serving. But this is a very rare case. Usually the latency involved there is very small. Operationally speaking, it's much easier to run one service than to run two. So if you want to simplify your deployments, that's also a reason to do this. But regardless of which one you choose, the first two steps between them is practically the same. You want to export your saved model, make it accessible, and then you have to write the code to do inference. And I'll show you what that looks like in a moment. For in-process TensorFlow, you have the additional step of linking to the TensorFlow shared library, which we actually distribute. And you can see that in our Go and Java instructions, and you can just download it right there, or you can build it yourself. So here's a Go example of what inference looks like. It's actually not too much code at all. And actually, if you go to the Go repository on GitHub, you can actually see real inception code that works in Go. So what it involves is first loading your saved model. You pass the directory that the saved model is in. As I mentioned before, saved models involve multiple TensorFlow graphs. So after you specify the directory, there's a set of tags that you can use to specify which TensorFlow graph you want to load. When you execute your model, all of you are probably already familiar with TensorFlow sessions if you've ever used TensorFlow at all. It's essentially the same thing as the Python API, but in another language. You take a tensor, here we have a batch of images, and you run your TensorFlow model using that tensor, and as output, you get probabilities for each classification for each image in the batch. And you do something with it. So I showed Go there. Jeff mentioned that we support a ton of different languages. These languages are all on our TensorFlow GitHub repository. So you can actually just go to the TensorFlow GitHub repository and start using any of these. All of these languages can actually be used to build and execute TensorFlow graphs. But a common question is, can any language besides Python be used for training? And the answer is a bit nuanced, but the short of it is no. And the reason is because a lot of supporting libraries, like the training libraries, the high-level APIs, optimizers, the RNN library, all of those are only available in Python at the moment. So I would personally recommend that you only do training in Python, but you can do inference in any of these other languages. The instructions for using the shared library are in the READMEs that are associated with each language. So you can either download it or build it yourself. I won't go into too much detail here. So as a summary, these are the basic steps. You're probably running infrastructure already around it. The point I want to emphasize here is that especially if you have a lot of data in your organization, you really should be thinking about how to make distributed training work well and what you should be running to do that. As Megan said, there's like a 58x speed up when running on 64 GPUs, and you can imagine what kind of effect that would have on the engineers working with TensorFlow models, but when training TensorFlow models. And thank you. I will now hand it off to Noah, who leads the TF serving team here at Google.
Hi, everybody. I'm Noah Fidel, and I'm going to share with you today how you can serve your models in production with TensorFlow serving. So we're going to start with that image on the bottom right, and really this is just showing how, as an industry, software engineering is quite mature and advanced, and machine learning is still early on in the early days. So if you think about all the great things we're used to with software engineering and best practices that we've all come to understand, things like source control and continuous builds we might take for granted. In machine learning, we don't even know what some of those things are yet, and that motivates a lot of what we do with TensorFlow serving. So starting with a few stories, who has taken a commercial airline in the last 10 years? Okay, so half of us are awake and the other half probably have as well. So going back about 12 years ago, I was working on a system that did the flight planning software for the majority of the world's commercial air flights. This included things you might care about, like how much fuel to take on your plane to get somewhere. It didn't have source control when I joined. It did when I left. And I was helping do that. But this kind of motivates that even though source control was an understood thing at the time, just because we have a best practice doesn't mean everybody uses it yet. And that's something with TensorFlow Serving. We want to make best practices that you all can use and make them easy enough that you get them kind of by default. So in 2010, I was at a small startup doing photo sharing on mobile apps. It was really great. We had some great engineering. We tried to do all the best practices. We had source control and continuous builds and so on. And one day we decided to add a machine learned model to do face detection and auto cropping. And it was really great. We loved it. Our users loved it. Our investors really loved it. But we had no continuous build for machine learning. And at the time, the tools were kind of ad hoc enough that we checked in the weights to the model in the execution environment, but you couldn't retrain the model, right? And now it's a kind of understood best practice. You want to be able to do that. So here we are today in 2017. We have lots and lots of great tools, but really just we're getting started, and we have a long way to go for machine learning. And hopefully all of us together can build a great ecosystem around machine learning and best practices and so on and share those. So here's the agenda for today's talk. To answer the first question, what is TensorFlow Serving, I'm actually going to introduce what is serving. So some of you probably know what it is. This might be kind of the basics for you. But for those who aren't familiar with it yet, if you ever want to deploy your machine learning into production, you'll want to become familiar with these concepts. So serving is how you apply a machine learning model after you've trained it. Seems pretty simple and straightforward. It has some attributes, though, that might be unexpected or new to you. And taking another view on this, hopefully everybody is familiar with the orange boxes on the left side of the slide. So you have some data. You're going to use that to train a model in TensorFlow. And then you have that model, and you have your application on the right. Let's say you're showing video recommendations to users in your application. Somehow you need to get that model such that it's usable inside your application. So the most common way to do this is using an RPC server. And TensorFlow Serving can be used both as an RPC server and as a set of libraries inside your app on embedded devices or in mobile. So a key attribute for serving is that it's online and low latency. And this differs quite a bit from training and other big data pipelines you might run. Your users don't want to wait for the recommendations. They're not going to wait a minute. They're probably not going to wait 10 seconds. You really need to be fast and consistently fast. Another thing that's different from many big data tools out there is that you'll have many models in a single process. So let's say you had a great production model, it's serving great recommendations to your users, and then you have a new experiment you want to run. The most common pattern that people do is they want to load, say, a second experimental model in their server alongside their main production model. So it's really common. Another thing is an emerging best practice that we're seeing a lot inside Google, and we want to bring more to industry, is that you'll have many versions of your model over time. So the data that you trained on last week might not be as relevant to the data you gathered yesterday, and so you want to continually train your models and continually deploy them. Last but not least, I'm just going to mention the last bullet here. Is anybody familiar with mini batching? Okay, good number. So mini batching is where you take a bunch of examples at training time, maybe queue them up, and then you run them through your graph together to get more throughput and higher efficiency. And this is really great. It lets you train models more quickly, process a lot more training data. And so the challenge here is how can you do that in a production setting where all of your requests arrive asynchronously, and you want to keep a nice bound on latency. And we have some good tools both at the library level and binaries for you to do that. All right, so moving on to what is TensorFlow Serving. So it's a flexible, high-performance serving system for machine-learned models, and it's designed for your production environments. TensorFlow Serving has three major pillars. The first are C++ libraries. These are what we use internally to build our binaries, and they're all open source, and they're very low levels. They include things like how to save and restore a TensorFlow model, as well as how to load new model versions over time. We have binaries that incorporate all of the best practices we've learned thus far out of the box, and for the emerging ones that we're not sure if it's a best practice yet, flags so that you can enable and try them. We also have Docker containers and tutorials and code labs that let you auto-scale our binaries on Kubernetes and so on. And finally, we have a hosted service with Google Cloud ML, as well as an internal version of that. Okay, so diving into our libraries, our core platform is completely generic. And what this means is, let's say you have a current system, maybe you're serving on a legacy or in-house built ML system, and you want to adopt TensorFlow, but for some transition period of time, you might want to mix that in with your legacy system. So our core platform lets you include any C++ class you want as a servable. The components of the libraries are all a la carte. So every component, if you go look at our page, every single class we have is used by some customer inside Google on its own. And in just about any combination that you can imagine, they're also used and deployed. And taking the last 3 bullets together, the highlight here is that all of our APIs, by and large, allow you to plug in your own implementations. So you can add support for different model storage. Maybe you're already an existing user of ML. Maybe you have hundreds of models in a database. If we provide a way to get models off of a file system, you can easily extend that to support a custom database or a custom data store. Okay, so I'm going to walk you through, hopefully this is not too complex. This is our libraries at a high level inside TensorFlow Serving. And they're also arranged here exactly as they are inside our binaries that we pre-build for you. So the green boxes are our standard kind of abstractions with APIs. And the yellow boxes are plugins into those abstractions. So let's imagine that this is a server and you're doing video recommendations and you have version 1 of your model loaded and it's called My Model. So you have a source, and the source is responsible for identifying new models, and that should be loaded. So we have a file system plugin to the source. It does exactly what it sounds like. It monitors the file system, sees that there's a new version. Let's say, aha, version 2 arrived, right? And now we want to load version 2 because it has, is trained on fresher data, and it's going to provide better recommendations to users. So it's going to create a loader of a TensorFlow saved model. And it's important to note that the loader of a saved model knows how to load the saved model, and it knows how to estimate the resources such as RAM or GPU storage that will be used by that model. It doesn't actually load it yet. That's the job of the manager. So this loader is emitted to the manager as an aspired version. And it's actually up to the manager to figure out when it's ready, when it has thread scheduling available, and when it has enough resources to load that new model version, it'll do so. And this is where one really key plugin comes into play, which is the version policy. And it turns out that in almost all scenarios, if you're serving something like video recommendations to users, you want that serving system to always be available, right? You never want to have a downtime. On the other hand, there are use cases out there where, let's say you have an offline big batch pipeline that's maybe annotating these videos in batch, right? And it's not directly user-facing. And let's say that your model is very big. You might prefer to have a little bit of unavailability in that pipeline and save a bunch of memory, right? So instead of loading both versions of that model at once, you can actually delete the old one and then load the new one and just have a little hiccup in your serving. So the version policies let you preserve availability or preserve resources. So it's a nice thing there. Okay, so on to some strengths of the libraries. First and foremost is they're optimized for very high performance and robustness. So these are used in some of the largest serving systems at Google at pretty large scale. And we do things like ref count accesses to your models. So from the previous slide, let's imagine that version 2 of the model is loaded, and this is kind of getting into the details, but version 2 is loaded. You can't actually immediately unload version 1 because there might still be requests pending to it. So we actually keep track via ref counting of the requests in flight on each version of your models, and only after all the requests have quiesced can we delete a version that's no longer needed. And last but not least, just kind of re-emphasizing, we have these nice plugin APIs, so you can build your own sources to get models from a database, an RPC layer, a pub sub system, kind of whatever you like. Okay, so last show of hands. Who's used TensorFlow serving libraries so far? Great, a few of you. So for anyone who's thinking of using this, you would just see this by default. This is in our tutorials. But for those of you who've used the current libraries, what we found internally and externally is that you had to, setting up all of those libraries with the best practices took a bunch of boilerplate and kind of common code. So we made a new class called Server Core. And what this does is it lets you declare the set of models you want loaded and pass them to Server Core and say, just give me a manager of these models, please. I don't really care about the details. Give me all the best practices out of the box. And so this should let you delete about 200 to 300 lines of code. So give that a try. Send comments and feature requests. Okay, so this slide is intentionally short. The binaries are very, very simple. They take all of the best practices from the libraries of TensorFlow serving and just wrap them in a gRPC layer, along with some flags and configuration and monitoring and other things you would need. Our binaries are based on gRPC, which is Google's high-performance, open-source universal RPC framework. And you can extend this as well, but this is what we provide out of the box. In terms of the specific APIs, currently open source complete with the API and implementation, we have a low-level tensor-oriented predict API. So this should be usable for any kind of modeling inference that you would need to do. Coming soon, we have regression and classification interfaces. The APIs are already on GitHub, and the implementation is out for review, so it should land very soon. All right, now I'm going to move on to some challenges that we've seen, along with the best practices for how to solve them. So the first one, this was a great story around isolation and latency. So this is a graph of latency with each of those spikes is approximately daily Mountain View time at noon. So this is for a large Google customer serving several 100,000 queries per second. And right around, give or take noon, there was this latency spike at the 99.9th percentile that put that serving customer outside of their SLA. So we looked into this, and it turned out that there was a fantastic engineer we've been working closely with, really liked to push new experimental models right before or after you went to lunch. Who knew? And it actually threw us for a loop because it did move forward and backward by an hour or two every day, and so we didn't find any automated jobs doing this. But we did find the problem. It was loading a new model could have a pretty big latency impact on your existing models running inference. So if you dive in a little bit deeper, it turns out that the default, and I think it's a very good default for TensorFlow, is to optimize for throughput. That's what most of us want in most situations. So you don't have to go set a flag that says, please give me throughput. But a side effect of that is, by default, optimizing for throughput, pretty much all the models and all the sessions on your task will get access to all of the threads. So again, very good default, but for the specific case of you have many models and many versions loading over time, what you really want to do is isolate the loading threads away from your inference threads. So we added, it's a pretty fancy slide, but we added just one flag. You can set the number of loading threads, and we typically set it to somewhere around 1 or 2. And I'll show you the after slide. So you can see much more detail, but the main point from here is that the y-axis dropped by 10x. So the latency spikes now are roughly 100 milliseconds. This is completely inside the customer's SLA. Customer's happy. We have a best practice now that all of you can use. The next challenge, and I hinted at this earlier in the talk, is about batching and handling asynchronous requests and getting the efficiency of mini batching at serve time. So if you look at the little graphic on the right, you have the green, blue, and orange boxes. And these represent your user queries arriving at different times, kind of falling down towards your server. And what you want to do ideally to get that mini batching-like performance is kind of wait for some period of time, take a few requests, put them together, and run one graph computation. At the same time, you really want to keep a strict upper bound on the latency you're willing to wait. So we've done quite a bit of investment here. Our batching is available as a library as well as via flag for the server. And there are a lot of interesting nuances here that we didn't even realize what we were getting to when we first started doing this. And as just one example, let's imagine that you had 2 models on the same machine. What you might want to actually do is schedule their batches back to back instead of having them overlap and contend for threads. So we have the concept of a shared batch scheduler. So each model has its own, and they cooperate via shared scheduler. As a teaser for later, sequence models make this really interesting, given that they're typically not just a feed-forward network, and the sequences can be of varying length. So it gets very tricky and challenging for how to batch these together. And Eugene is up in a couple of talks. He's going to go into much more detail about batching and sequences. A few areas of emerging tech. So Jonathan was mentioning Save Model. We're quite excited to announce this and encourage everybody to adopt it. So Save Model is the universal serialization format for TensorFlow models. It's included in TensorFlow 1.0 and also in TensorFlow serving as of right now live on the repo. There are 2 marquee features of Save Model. So the first one is support for multiple metagraphs. And for folks who have been mostly doing training, you might not know why you'd want this, but once you hear some more details, you'll see at serve time, it's really important to have different metagraphs. And the use case here is, let's say you were training a model, and you went to save it for serving. So you typically want to remove things that are training specific, like input queues and dropout layers. You really don't want those in your production serving models. A few people have tried, you get really bad results. Or no results at all if they just hang on a queue. Other things you might want to do is you might want to transform your serving graph. So you might want to have a quantized graph for serving on a GPU or a TPU. And what the multiple metagraph support does is it lets you have as many metagraphs as you want, and you can store and access them by simple tags. So you can tag one with serve, one with train, one with serve and GPU or TPU, and so on. The next concept is signature defs. So a signature def defines the signature of a computation supported by a TensorFlow graph. And this is really important. So if you look at the slide, most people probably can right away, especially for humans, we're good at this, you can read input, classes, and scores and probably figure out what's going on with this graph. But if you handed this graph without those labels to a serving system, it would probably have no idea what to do with it. Right? With these graphs, you can feed or fetch from just about any node in most graphs. So how would you identify where your input goes and where your output goes? And that's what signature defs do. So in this case, they specify that that middle node on the left is where you want to feed in your TensorFlow example, and the top right node is your string classes, and the bottom right is your floating point scores for, say, a classification. Building on a signature defs, we're adding support for multi-headed inference. So this is one of the top feature requests we've had from the community. Is anyone familiar with multi-headed inference? Okay, very few. This is going to be really popular and more common as people productionize and deploy machine learning in their products. So it's really, really common that you might start with one model, maybe a click-through model to do predictions on, say, your video recommendations. But over time, you might decide, we'd also like to train a model for conversions or maybe people who watch the whole video. And quite often, people would go about this by actually training a second model. But for starters, you're training on almost all the same data. All of your data pre-processing, all of your hidden layers quite often are the same. And then at serve time, you're doing a lot of redundant computation. So you're parsing your input, pre-processing it, doing the same hidden layer computation, and really only the output layers change. So our multi-headed inference support builds on signatures. It lets you specify multiple signatures together and say, run these together in one request, and it'll do that. Performing multi-headed inference will save you operational overhead and complexity of deploying multiple models. It'll save you bandwidth, CPU, latency, and so on. So we're really excited, and that should land sometime in the next week or two. All right, so wrapping up, and again, Eugene is going to go into much more depth on sequence models. I just wanted to highlight that there are many flavors of sequence models. They are generally very expensive to serve, both in compute cost and latency. And we're investigating specifically batching, padding, and unrolling strategies to make them more efficient and effective for all of you to serve. All right, so for anybody who's interested, we really warmly welcome collaboration, pull requests, feature requests, bugs, and so on. We sync all of our code to GitHub weekly. We have a developer on call, and it includes facilitating your pull requests, answering questions, comments, and ideas, and so on. To get in touch, you can reach us at discuss@tensorflow.org. So here are a bunch of links for how you can get started. I'll let you read these offline, and please do get in touch with your questions and feedback. All right, so thanks very much, and up next is Ashish. The ML toolkit. Ashish is going to present the ML toolkit. Thank you.
Hi, I'm Ashish. I'll be talking about ML Toolkit. So let me start by saying that TensorFlow is this really amazing piece of technology. At Google, it's already powering systems ranging from search ranking, ads auction, YouTube recommendations, translate, photos, and many, many more. We can train complicated models with hundreds of billions of parameters and serve them on platforms ranging from mobile phones to cluster of TPUs. However, TensorFlow is this really low-level framework. And as Martin mentioned in an earlier talk, we are working on higher-level primitives like layers, estimators, losses, and metrics to make it easier for researchers and developers to create custom model architectures. However, what's still missing from TensorFlow is algorithms that work out of the box. What a lot of developers really want is packaged solutions that they can quickly and easily integrate into their workflows. So I'm happy to tell you that now we have a toolkit of really popular machine learning algorithms that we have built right on top of TensorFlow. So starting with linear and logistic regression, k-means and Gaussian mixture models for unsupervised clustering of data, Walls matrix factorization, which is a popular collaborative filtering algorithm for recommender systems, support vector machines, all the way to state-of-the-art algorithms like SDCA, stochastic dual coordinate ascent for convex optimization, random forests and decision trees, and various architectures of deep networks. Now, all these are available on GitHub, and we're constantly working on improving and expanding the set. Next, I'll highlight a few of these algorithms to give you a better sense of the existing and upcoming features for these algorithms. Starting with k-means. So here we implemented the standard Laird's iterative algorithm, along with random and k-means plus initialization. We support both full batch and mini batch training modes. And we also allow the user to specify distance functions like cosine or Euclidean square distances. Now, GMMs, on the other hand, model the data as a mixture of Gaussians. These are much more powerful models and also harder to train. For these, we use an iterative EM algorithm, and we allow the user to choose from a combination of means, covariances, mixture weights to train on. Next, we have Walls, which is matrix factorization using weighted alternating least squares. Note, I'll be revisiting this later in my talk as well. So here you're given a very sparse matrix. For example, you could be given ratings that users have provided on videos. Note that the matrix is sparse, so not all the videos are being rated by each user. And now you want to answer questions like, which video should we recommend next to the user? Or to find user-user similarity or video-video similarity. Now, this is typically done by factorizing this huge matrix into a product of two factors, two dense factors. Note also that as the algorithm name indicates, this loss is weighted, which allows you to, say, downweight things that were unrated in the original input, or to avoid your spam or popular entries from drowning the total loss. So this problem is highly non-convex. However, it turns out that if you fix one of the factors, there's a closed-form analytical solution for the other factor. And so the training works in an iterative way, where you first fix V, compute U, then fix U, compute V, and go on. Next, we have SVMs. So these work by finding a decision boundary that maximizes a margin. We are working with soft margin methods using a hinge loss, and the current implementation is of linear SVMs with L1 and L2 regularization. Note that SVMs become much more powerful with a nonlinear kernel, which allows a much more complicated decision boundary. So we are working on providing nonlinear kernels using the kernel approximation trick. Next, we have SDCA. Now here you have a convex loss function with L1, L2 regularization. And SDCA uses a neat trick of transforming this loss function into a dual form. And it turns out that for many problems, solving it in the dual form is much more efficient. And it turns out that this algorithm can power models from linear and logistic regression all the way to SVMs. We also have random forests and decision trees. Random forests are ensembles of decision trees, and decision trees work by creating a hierarchical partitioning of the feature space. Currently, our training method is what we call extremely random forest training, which allows better parallelization and scaling. And we're also working on having gradient-boosted decision trees, which are very, very popular also. So I talked about the different algorithms. Now we want to make it really, really easy for users to use them. All of these are exposed via very high-level scikit-learn-inspired estimator APIs. Here's an example for how one might do k-means clustering. So you start by creating a k-means clustering object, and here you can pass in a bunch of options like the number of clusters, how you want to train, how you want to initialize, and so on. Next, you call the fit function and pass it your input. And that's it. Now TensorFlow goes behind the scenes, it creates the graph for you, it will run training iterations, configure the runtime till the training is done. When you're finally ready, you can start inspecting the model parameters, like the clusters, and start running inference, here finding the assignment to clusters and so on. So I talked about higher-level APIs, but you also want to maintain the flexibility and extensibility that TensorFlow promises. So these are not opaque objects that are only accessible via this API. We, in fact, allow the users to inspect the graphs and also to be able to embed these graphs into larger training models. So here's a toy example that embeds k-means as a layer in a bigger, deeper network. You start with an input, you run k-means and get your graph for k-means. It also returns your training op to drive the clustering, and the output is the input transformed to a distance to cluster space. Next, you feed this to your dense stack of layers, you create your supervised loss, you run SGD to get a final DNN training op. Now you have these two training ops, you can join them to create a single training op that can drive the co-training of these two models. Here's a code snippet for the same. So you start by creating a k-means object, and you inspect the training graph. It returns you a training op and the output. Next, you feed your output into dense layers, and you create your model architecture as usual. Finally, you get a training op to drive your supervised loss or your dense stack. And finally, you use TensorFlow's group operation to group together these ops so that you have a single op to drive the co-training. So just to recap the talk so far, I talked to you about the different algorithms that are available now. I showed you examples for how to use high-level APIs to access them, and also talked about flexibility and extensibility of these algorithms. Next, I want to highlight the fact that all these algorithms are backed by distributed implementations. Just to give you a better sense of the complexity hidden behind these few lines of Python code, I'll dig deeper into the implementation of one of the algorithms. So in general, the distribution architecture is going to be the same. You will have a set of parameter servers, which will store all the parameters in a sharded way. You will have a bunch of worker replicas that will be running training steps with many batches of inputs. In each step, the worker replica would fetch some parameters. It will run compute on the input to compute the new value of the parameters. And finally, it will write back these updates to the parameter server. So let's look at walls again. So just to recap, with walls, you want to factorize a really sparse matrix into dense factors. And as I told you, the training algorithm involves fixing one of the factors, computing the other one, and iterating. Now we want to be able to scale to inputs that are terabytes in size. And we want factors that have hundreds of millions of rows and hundreds of columns. So how do we make this work? So we have to carefully think about all the RAM, compute, and network bottlenecks. The first obvious thing is, given the size of these factors, you will have to distribute them across parameter server shards. So you take your use, split them across all these shards. Next thing, given the amount of compute involved, you want a bunch of worker replicas. The sharding scheme that we use for these worker replicas is row slicing. What that means is each mini batch is a subset of rows of the input, and we compute the corresponding rows of U. Note, however, there's still a problem. Each update to U depends on the full V factor. And as I said, V could be large, it could be terabytes. So what this entails is that you might be copying terabytes of data to each worker in each step. So how do you get around that? So at this point, we use some linear algebra magic. It turns out you can compute certain summaries, let's call them G, and given G, your updates to U only depend on a few rows of V. And these are specifically the rows that correspond to the non-zero entries of the input. So this is great. What that means is that instead of copying terabytes, you can just copy megabytes of data per step. So at this point, we can run TensorFlow's gather operation and get the required rows. We run compute using highly optimized custom C++ kernels that we wrote. And finally, we use TensorFlow scatter operation to write back these updates to the parameter server shards. So how well does this work? We believe our implementations are really high performance. We did some benchmarking, and on single machine, our implementations in general look on par with scikit in terms of model quality and speed, often even working faster for moderate size problems as well. But where TensorFlow really shines is being able to run seamlessly across hundreds of thousands of machines. In fact, in many cases, we were able to train models that were much larger than what we had seen in literature. For example, with random forests, we were able to train thousands of trees with billions of nodes. And we have a paper in NIBS that talks about that. With SDCA, we saw 10 to 50x faster convergence compared to Google's highly optimized internal coordinate descent-based implementations on logistic regression for datasets with billions of examples. With walls, we were able to factorize a huge matrix, 400 million rows by 600 million columns, into factors with 500 columns in under 12 hours. Note that this is 50x larger than what we could do with an earlier MapReduce-based implementation. So in summary, we have really high performance, distributed, and extensible implementations of different ML algorithms that are working out of the box in TensorFlow. These bring together the ease of scikit with the power and scalability of TensorFlow, and moves TensorFlow one step closer to being a more complete ML solution. I'm hoping at this point you guys are excited to get started. So here are some links to code and documentation. And here are a bunch of estimators that are ready to use. With that, thank you.
Hey everybody, I hope your neural nets have all been trained to know that when you see me, it's time for a break. From here, we're going to take about 20 minutes. We're running a little late, so be back here in 20 minutes, and we have 4 more talks about RNNs, about medical research, about art and music, and wide and deep. So I'm looking forward to seeing you. Also, the talks from this morning are already up on YouTube on the Google Developers channel. All right, thanks a lot. Hello, everybody. After you carefully trained your neural nets, I'm an example that doesn't fit your model because here I am back and there's no break after me. What we're going to do here is we have 4 more talks. We're going to talk about RNNs. We're going to talk about wide and deep. We're going to talk, and then we're going to do some stuff about art and music and medicine. But let's lead this off with Eugene, who is one of our engineers who works on the RNN API, and we're really excited to have him. This is a great talk. Come on up.
Hi, so I'm Eugene. I'm going to talk about the sequence models and the recurrent neural network API in TensorFlow. First, the motivating example. Google Translate. This is an awesome product. A lot of people really love it. And how does it work? You type in or you speak in a sentence in a source language. Some magic happens in the background, and you get the translation in a target language. And as of a couple of months ago, the magic got a little bit more magical. And that's because the product is now backed by a neural network, and specifically a sequence-to-sequence model. So what is a sequence-to-sequence model? Basically, it's 2 recurrent neural networks. One on the left is the encoder. And the encoder reads in 1 word or word piece at a time. From left to right. Then it creates some intermediate representation. Then the decoder, which is a second recurrent neural network, or RNN, it receives a start token that says start decoding in this target language. And it emits 1 word or word piece at a time in the target language. And once it emits a token, it feeds that back into the next time step. And that token and the previous state are used to figure out what to emit next. Now, in practice, the model is a little bit more complicated. You've seen this slide a couple of times today. And let me just focus on the fact that, again, here, there's an encoder, RNN on the left. There's some intermediate representation in the middle. And on the right, we have a decoder, RNN. And we're going to refer back to this slide a couple of times. But let's talk about what we're going to talk about. First of all, we'll talk about how to read and batch sequence data efficiently in a distributed setting for training. We'll talk about the RNN API itself. And as we talk about that, we're going to start talking about fully dynamic calculation in TensorFlow, and I'll give you some tools that allow you to do that. Then we'll switch tracks a little bit and talk about how to trade off flexibility for efficiency in the RNN. And finally, we'll talk about a neat new library that we're working on that allows you to perform dynamic decoding. All right, so reading and batching sequence data. So as we scale up our training for, let's say, the translation model, it's very important to be able to feed in large mini batches of variable length data. And so here we're going to be focusing on the source sentence, which is on the lower left, and on the target sentence, which is on the lower right and on the upper right. And we're going to focus on how to do this efficiently in a distributed setting. So for this, we have Proto, called the sequence example. And Google protobufs are, as you've heard, language agnostic, architecture agnostic data storage format. And the sequence example format is made specifically to store variable length sequences. So some of the pros, it provides efficient storage of multiple sequences per example. It supports a variable number of features per time step, which we won't talk about, but is an important feature. And also, we provide an efficient parser that reads in a serialized proto string and emits tensors and/or sparse tensors according to the configuration that you provide. And coming soon, well, you heard Noah talk about TensorFlow serving. The sequence example proto is going to be a first-class citizen in TensorFlow serving. So you'll be able to use it for creating data both at training time and at serving time with TensorFlow serving. Okay, so now that you can read in a sequence one at a time, you need to be able to batch it. And there are a couple of ways to do this. So one way is you basically do the padding yourself. So you pick a maximum sequence length, and each of your inputs you pad to that maximum sequence length, and then you pass it into the standard TensorFlow batching mechanism, the function tf.train.batch. So the major negatives of this approach: one, you need to know beforehand the longest possible sequence length, and then you'll always pad to that maximum length. And as a result, you're wasting both space and time during training. So can we do better? So the next best thing is to allow the batching mechanism to perform the padding for you. So you get your variable length sequences one at a time, and you feed them into this special padding queue. And the queue, when it reads off a mini batch, it finds the longest sequence, and it pads all of the other sequences up to that maximum length. So this is a little bit better. You don't need to know the maximum length. When you get a mini batch, you're no longer wasting space or time because you're only padding up to the maximum length within that batch. However, as you're trying to scale up training, for example, and your batch sizes become larger and larger, 64, 32, 32, 64, 128, you're more and more likely that at least one of the elements in every mini batch is going to be long. And so as a result, you're back to where you started in the previous slide, wasting space and computation time. But we can do better. So the solution here is to actually create a number of different queues, which we call buckets, running at the same time. And when you pass into this mechanism variable length sequence, it will put it into one of a number of queues. And each queue will contain only sequences that are about the same length. And when a mini batch is available from that queue, it will be that mini batch is returned to you as the next mini batch. And all of the sequences within that mini batch are about the same length. There's a little bit of padding, but this still gives you the best of both worlds because every mini batch, everything's about the same length. You're not padding too much. You're not wasting too much computation time or space during training. And most of the time, you get your short or medium length sequences as they come in, almost as quickly as they come in. Every once in a while, you'll get a mini batch from your spillover from the very long sequences. But again, here, even though it takes longer to compute and uses more memory, at least all of the sequences within this mini batch are all pretty long, so you're not wasting time. Okay, and we have a function for that. It's called bucket by sequence length. Finally, for those of you who are not necessarily interested in sequence-to-sequence models, but are interested in building language models or variational autoencoders, for example, we have a state saver, which allows you to implement something called truncated backpropagation through time. So what this means is that you pick a fixed number of time steps that you'll unroll for, and any sequence which is longer than that number of time steps gets split up into multiple segments. When you finish your mini batch, any sequences or segments which are not the completed sequence, the state is saved for you. Some bookkeeping is done in the background. And at the next training iteration, that state is loaded. And is then, you continue processing that sequence with that saved state. And we have a function for that. It's called batch sequences with states. All right. So now we've talked a little bit about how to efficiently read in variable length data and batch it, let's talk about RNNs. All right. So just to get everybody on the same page, what is an RNN? An RNN is basically a unit of computation that you repeat over and over. It's essentially a for loop. And the way that the forward calculation flows, you get inputs from below, so x at every time step, and you have some inputs which are the state from the previous time step. So these are the arrows from the left. And this intermediate calculation emits a new output, h, and an updated state for the next time step. Right? So this diagram specifically is an implementation of an LSTM, or long short-term memory, which is a very popular RNN architecture. So as I said, you can think of it as a for loop. And in fact, you can implement it, say in Python, as a for loop. So let's go through this relatively straightforward approach. So you have a function RNN. It accepts a function cell that reads in inputs and state and emits new outputs and state. You also provide it with a list of input tensors, and you provide it with some initial state. So you set your state to the initial state. You loop over your list of input tensors. So these are dense floating point tensors. And at each iteration, you call cell. You emit an output and a new state. You append this output to your list of output tensors. And at the very end, you return this list and the final state. So as I showed you on the previous slide, you have, for an LSTM, for example, the state is actually 2 tensors, not just 1. For a GRU, which is another popular architecture, there's only 1 tensor for this state. And so the simpler problem, or one of the problems, is that the cell function and the initial state are coupled. So you need to provide an initial state. This is 1 or a couple of tensors, which usually have all 0 values. And if you want to change your architecture and try another one, so you change your cell, you need to be able to easily generate, for example, a new initial state with a different structure. So that problem is actually fairly easy to solve by changing the functions to objects, and I'll talk about that next. The harder problem is that here you have a list of input tensors. And this is a fixed size list. You're in Python, after all, and you're building a graph that has a fixed number of time steps. And so as a result, you're basically losing the ability to run a variable number of iterations. We'll talk about that next. So first, the RNN cell. So the RNN cell is a base class that we provide, which a different architecture subclass, and it provides helper properties that give you knowledge about that architecture. Now, the second important feature of the RNN cell class library is that you can treat each time step as building a time step as building a layer. And so you heard Francois talk about Keras, and for the last month or so in the background, we've been working to make RNN cells act like Keras layers. And so eventually we hope to have full compatibility between the two. But let's go through an example. Suppose you want to implement an LSTM. First, you build a basic LSTM class. It's a subclass of RNN cell. It has 2 important properties. The first one is state size. And what this state size tells you is that my state is composed of 2 tensors, and each tensor has num units columns. So these are the depth of the LSTM. The second property, output size, tells you I emit at every time step a single tensor, and it has num units columns. Finally, there's a call method that accepts an input tensor and a state tuple in this case. It decomposes the state into 2 tensors, performs the intermediate calculations for the time step, and emits a new output, new h, and the new state tuple. Okay. So this is a fairly flexible framework, and we have a fairly sizable library of different implementations of different architectures, including basic RNN cells, LSTM, GRU, a bunch of other interesting research-oriented architectures. One that's particularly interesting is the bottom one, NAS cell. So if you heard Megan talk this morning about neural architecture search, one of the fruits of this research program is this new architecture that was basically learned via reinforcement learning on different possible RNN architectures. And so we have an implementation of that as of this week on TensorFlow GitHub. It's called NAS cell. So check it out, see if it provides you with a performance quality boost. And within Google, we have dozens of slightly different or radically different RNN architectures that are used by different teams to solve their problem. Okay, so we've talked about solving the simple problem. Let's talk about how to perform dynamic calculation in TensorFlow. And there are basically two tools that I like to talk about. And these are the main primitives that are used to build dynamic calculations. The first one is the TF while loop. And it allows you to build dynamic loops and supports backprop. The second one is called TensorArray. And this is required to be able to efficiently read and write slices of tensors, and also supports backprop. Okay, so the while loop was developed by Johan, who is a research scientist on the Brain team. And it's a function that basically accepts 3 arguments: the cond, lambda, the body lambda, and loop vars. So the cond is the condition function that tells you, should I continue this loop or not? The body implements the actual computation per time step. And the loop vars are the initial conditions being fed to the while loop. So let's go through an example. We'll start with a tuple of tuples, ijk naught. The values it takes on are 0, 1, and 2. The condition lambda looks at the first component I and says, continue looping while I is less than 10. The body takes both of these parameters, variables, I and jk, increments I by 1, and updates jk with the calculation that you see there. You pass these into the while loop, and at the output, you receive a tuple of tuples of tensors. So the final value of I, which if you look at this, basically is going to be equal to 10. And jk final, which is a tuple of tensors, which contains the result of performing the calculation there 10 times. Okay, so while loop gets you almost all the way there. But if you need to be able to process slices of tensors at every time step, you need to be able to efficiently access them and to write new ones. So for this, we have a tensor array. So let's suppose that you have a matrix, and you don't know at graph build time how many rows that matrix has. But you can use the TensorFlow primitive TF_shape to access that at runtime. So let's say this is equivalent to an unknown sequence length, right, in your mini batch. So first you create a tensor array whose number of entries, its size, is equal to matrix rows. And then you can unpack or unstack the matrix into that tensor array. Then inside the while loop body, you can access any index that you want, and you'll get back out a vector. You perform some processing, and then you need to take the result and store that in a new matrix. So the way you do that is first you create a tensor array. Again, in this case, you know the size that it's going to be, but in fact, you don't even need to know the size beforehand. Then within the loop, you write and update that tensor array at whatever row you want, and the result of your calculation is that vector. You pass it in there. You take that tensor array, you update it. At the very end of the while loop, you get the finally updated tensor array, and then you can stack it, pack it, and you get a new matrix. Okay, and that's the result of your calculation. Between these two primitives, you can get pretty far. In fact, we have a whole library of functional building blocks in TensorFlow that you can use based on these. So we have a map function. We have TensorFlow scan, which is somewhat similar to Theano scan, in some ways more powerful. We have the left fold and right fold operators. We have the dynamic RNN function, which I'll talk about next. We have a couple of other variants of RNN. And also we have a dynamic decoder function, which I'll also talk about towards the end of this talk. Finally, there are a bunch of other interesting algorithms that you can implement using these primitives. All right, so let's talk about the encoder of the translation model. So a couple of interesting things that we can see in this encoder. First of all, it has 8 stacked LSTM layers. And each one sits on a different GPU device. And between each of the layers, there are residual connections. So residual connections are actually very important in being able to train a performant model that has such a large stack of layers. So we'd like to implement this using the API I presented to you. Turns out it's 2 lines of code, fairly gnarly code, but let me step you through them. So first of all, you build your LSTM cells. Each one has, say, a depth of 512. You then would like to add residual connections, so you wrap each of these objects in a residual wrapper. You'd like to put each of these layers on a different GPU, so you wrap that in a device wrapper, and each one goes on GPU 0, GPU 1, and so on. So you make a list of these, and then you wrap that in a multi-RNN cell. Okay, so you take this object, and you pass it to the dynamic RNN function. It takes the cell, it takes a tensor of mini batches of inputs, it takes a vector with the sequence lengths of each of the mini batch entries, and a couple of other arguments that control the trade-off between memory consumption and performance. Okay, so what I've presented to you so far is a fairly flexible API for customizing and implementing your own RNN architectures and dynamic decoding. Sometimes you know that you want to use an LSTM, or you want to use a GRU, you want to use an established RNN architecture. So in these cases, you have the option to trade off flexibility for performance. And in TensorFlow, we provide 3 ways to do that. The first one, Chris and Todd talked about earlier today, is XLA. I'll talk about that one first. There are also handwritten C++ kernels that provide manually fused implementations of, say, LSTM per time step. And there are also manually designed, fully fused RNN implementations that fuse the entire calculation across time. So as you look at these, think about the kinds of trade-offs that you're making. So you're trading off flexibility for speed. Some of these implementations don't work well on some architectures, but are faster on others. And I'll mention these. So let's first talk about XLA. The nice thing about XLA is that there's very minimal flexibility trade-off. You implement an RNN cell, and you get an architecture that you care about, and then it's basically one step to get it compiled. So if before you had a stack of 8 LSTM cells, and you want to fuse each of them individually per layer, you simply wrap that LSTM cell in something called a compiled wrapper, which we recently released, and this basically builds the JIT compilation for you per layer. Alternatively, if you want to be a little bit more aggressive and try to fuse across all layers, you basically move the compilation outside of the multi-RNN cell. Okay? So pretty easy to use and flexible. When is this a good idea? So when should you use XLA? You saw some slides about that in previous talks. I also ran a couple of benchmarks myself, training a multi-RNN cell with 3 separately fused LSTM layers running for 50 time steps. And I tried this on slightly different architectures with different architecture sizes. So what are the takeaways? First of all, if you're doing this on a GPU, say I had a Tesla K40 available, and you're using a small batch size and a small depth for your cells, today it's kind of a toss-up of whether it's actually faster. The XLA team is actively investigating this area, and hopefully the performance will be sped up for this regime. In more realistic training cases where you have a large batch size, 16, 32, and so on, even with a small cell depth, or with larger cell depths, as you increase these numbers, your performance on a GPU is going to improve. 15%, 30%, 45%. And again, this is an area under active development, so it's going to continue to improve. Now, with a CPU, there's currently not much benefit, so don't use XLA there. Now, if you're looking into or you're interested in ahead of time compilation for an embedded device, say a Android device or iOS device, today it's not faster to use XLA, but there are other benefits. There's a reduction in memory usage by the model, a reduction in the binary size, and again, while I didn't benchmark these aspects of it, this is something worth doing as you're looking into building embedded models. So my current recommendation, try XLA. benchmark your intended use case. The benchmarks are actually open source. They're in a GitHub repo, so you can look at them and use them to compare the runtimes and the memory usage yourself. OK. Moving on from XLA, we have some handwritten C++ kernels for the LSTM and GRU cells per time step. And these work on CPUs and on GPUs. They tend to be faster for smaller batch sizes and on mobile devices. Okay? So try them out. If you're interested in fully fused calculations, especially on mobile devices, the LSTM block fused cell is even faster for these cases. So look at that. Now, if you're working, you have NVIDIA GPUs, you're using cuDNN, we have cuDNN wrappers that allow you to speed up your training up to 3 times, which is awesome if you're working with these devices. And it's fairly flexible, supports bidirectional RNNs, stacked RNNs for LSTM, GRU, and a couple of other architectures. And as of about a month ago, you can take the parameters that these layers use, and during export time, convert them from the custom cuDNN format to a canonical format, so that you can then take these checkpoints and load them in a different graph that uses one of the other LSTM implementations. What that means is that you can train on GPU and then perform inference on a CPU or on a mobile device, which is pretty cool. All right, so we've talked about that. Let's look at this neat new API that we're working on for dynamic decoding. And in fact, decoding tends to be the most complicated part of many sequence-to-sequence models. And that's partly because you have to attend to the encoder output, and partly because you have, you're emitting an example at every time step, and then you're feeding that back in. And the decoder has to decide when to stop. Okay, so the goal, okay, so we have this library. It's a new object-oriented API. It's under active development. It's, we hope to release a new neural machine translation tutorial which uses this library. And the code is already in TensorFlow GitHub master branch in the tf-contrib seek-to-seek package. So the main goal of the decoder is to make a plug-and-play and batch-friendly decoding library that allows you to first pick a sampling method, pick the RNN architecture, then pick, if you want to have a fancy decoding approach, say using attention or an in-graph beam search, and then decode. So let's start by first picking a sampling method. So during decoding, when you're training, oftentimes you want to just use the ground truth as your inputs at every time step. So in this case, we have a helper called a training helper. And you feed it that's tensor decoder inputs and the sequence lengths, and that's all you need to do. However, you want to try something a little bit more fancy. Let's say you want to use scheduled sampling, another popular approach for training decoders. So use another helper. In addition to the ground truth decoder inputs, you can also say, well, the RNN is going to emit an output. I'll treat that as logits. And I'm going to sample from these and get a sample ID, and I'll use that as lookup in an embedding table and feed that in as the next input. So here you have to provide the embeddings, as well as the probability with which you're going to choose whether you use ground truth or you're going to sample. Finally, at inference time, you don't have ground truth, but you do have your embeddings, and what you can do is you can read the outputs of the RNN, treat them as logits, and take the argmax, the highest probability output in your vocabulary, and look that up in the embeddings and feed that as your next input. So you pick one of these, then you pick your RNN architecture, and in this case, it's the same architecture as we had for the encoder. And then you build your decoder. So this is an object that combines the cell architecture and the helper object, the sampling approach, and possibly also provides an initial state. Now, the simplest one doesn't do anything extra. However, this week and next week, we're actually working on releasing an attentional decoder where you provide an attention mechanism that describes how you, at every time step, say in translation, you look at the output of the encoder and say, oh, maybe I should be attending to this part of the input sentence, and that will help me to decide what word to emit next. So finally, you have your decoder. Just decode, call dynamic decode on it. This will return to you the output, the dynamic decoder output, it's the tensor, and the final decoder state. So the outputs for a simple decoder, there are two. One is the tensor of the RNN outputs at every time step, and the second one is a tensor with the sample IDs. So if you chose sampling decoder, this will emit the actual categories, the actual words that were chosen at every time step. And in this case, for the final decoder state, because you have a stack of 8 LSTMs, it's going to be a list of 8 tuples containing the LSTM states. So to combine everything, essentially 4 lines of code. First, you choose your sampling method. Then you choose your RNN architecture. You build your decoder, and then you decode. So we hope that this is something that will take a fairly complicated procedure and make it as simple and flexible as possible. All right, so to summarize, I talked about a flexible sequence input pipeline that allows you to scale up distributed training of sequence models. I've talked about the RNN API in TensorFlow. It has hundreds of users within Google and many, many users outside of Google as well. I've talked about dynamic calculations within TensorFlow and dynamic RNNs. These have a reduced memory footprint compared to the basic for loop approach. They allow you to cache your GPU activations to the CPU, reducing the memory usage. And they're essentially as fast as the equivalent for loop. I've also talked about how to improve the performance of your RNNs via fusion and some of the trade-offs that you make there. And finally, I've introduced a new decoder library that we hope you'll all check out and try. It's available on GitHub now. So thank you very much. I would like now to introduce our next speaker, Hung, and he is going to be speaking about TensorFlow Wide and Deep, where he is the tech lead on that project.
So, hey everyone, thanks for coming to the talk. My name is Heng Zhi, you can call me Heng. I work at Google Research. And today I'm very excited to tell you all about wide and deep learning and how you can use it to combine the power of memorization and generalization on TensorFlow. At Google, we started the Wide and Deep project with a mission to combine the power of memorization and generalization on one unified machine learning platform for everyone. And when we say everyone, we really mean not just every product teams at Google, but also everyone in the open source community, everyone in the academia, as well as industry. So we started working towards this mission by jointly training wide linear models on the left and deep neural networks on the right, and create an easy-to-use API, high-level API available in TensorFlow so users can start with simple linear models and gradually add complexity without ever having to leave the platform. So the first question is, what do we really mean by memorization and generalization? And to answer that, before we dive into machine learning, let's take a step back to think about how we learn as humans. So as little kids, we start forming our knowledge by observing everyday events. For example, seagulls can fly, or pigeons can fly. Right? We're very good at memorizing these maybe unrelated, boring facts very precisely, right? But as you can imagine, this good memorization probably doesn't scale well to over 8 million animal species in the world. You're not going to see all of them and not going to memorize all of their names and whether they can fly or not. So the very powerful step in our learning is generalization. By saying animals with wings can fly, we're basically summarizing all these sparse observations into one very compact representation of knowledge, and that's whether the animal has wings or not, right? Using this compact rules, you can generalize to many more animals you may or may not have seen before. However, generalization has its own limitations because it doesn't always work on all cases. For example, penguins, well, at least they try, but the best they can do is some sort of free fall into the ocean, right? So the real power lies in how do we combine the power of memorization and generalization. And interestingly, this is very similar to what we observed in the progression from a pure wide model for memorization to a pure deep model, which gives us more power in generalization. And finally, in combining wide and deep, which is generalization plus memorizing exceptions, which is saying animals with wings can fly, but penguins cannot fly. Okay? So enough with the hypothetical animal examples. Now let's come back to a real-world example, and I'll walk you through it. In this running example, we'll see how we can apply wide, deep, and wide and deep learning on the Google Play app's recommendation problem. So suppose one of our favorite user, Chris, recently installed the Priceline app. The question we want to ask is, which other apps should we now recommend, right? And one way to frame this problem is to frame the recommendation problem as retrieval and ranking. So let's start from the upper left, where I'll walk you through a life of a query. So we get a query from the users in the recommendation system case. It's the user feature plus some contextual features, maybe at the time, and so on. And then our retrieval system will retrieve the relevant items that related to this user and context, and maybe, let's say, give us hundreds of candidates, right? The ranking module will rank these candidates and present the most promising ones, the most relevant ones, to the user. The user take a look at the items on their phones, and they can take one of the possible actions, like click on the app, install the app, and so on. All of these are recorded in the logs, which the learner picks up and trains a new model. And this new model will power the next iteration of ranking. And that's a cycle of recommendation, right? So this talk will focus on how we use wide and deep learning to solve the ranking model of this app recommendation problem. And the query features, as I said, is user and contextual features. The item features are the app impression features, which we show to the user's phones. And the objective we're optimizing for is app installs. So if the user install the app, the label is 1, otherwise the label is 0, okay? So let's get started. Now the first, probably the simplest model you can pick is a linear model, or known as logistic regression in this case. So the inputs are a bunch of features, right? You can have the user features, installed app is Priceline, and impression features, which is if we show kayak as impression, what's the likelihood of install, right? So the impression app, let's say, is kayak, and we want to predict the probability that the user will install the app. Now, how do we add generalized memorization capability? This can be done by adding a crossed feature, which is the AND operation over these binary base features. So the cross feature can be install app is Priceline and impression app is kayak. If both are true, what is the likelihood of install, right? And if we go into the data and we see a lot of correlation, people who installed this also install that later, then you can memorize this frequent co-occurrence of these features, right? So crosses help you with that. Now, you might think that, well, that's very specific, right? How do we actually generalize to other apps that are not Priceline or Kayak? Well, one way you can do it with wide linear models is to add less specific features like app categories. So for example, if you add a clause saying, if install app category is travel, and the impression app category is also travel, what is the likelihood of user installing that, right? So once you learn this, you can apply to other travel apps, not just Priceline or Kayak. Now, the problem, which you might have seen already, is that the feature space is very wide and very sparse. There are millions of apps, billions of users. If you cross apps with apps, that's million times million, which is trillion combinations, right? So most of these user impression apps pairs will never occur in your training data. So how do you actually generalize to these unseen pairs without doing a lot of manual feature engineering that we did in the last slide, right? And remember, in many cases, it might be hard for humans to come up with these really good, high-level, less specific feature crosses in the first place. So one way to solve this, to generalize more automatically, is to use deep neural network with an dense embedding layer. So starting from the bottom, you still have your base binarized features, which is user install Priceline, and let's say impression app is Yelp now. And let's say you happen to never shown Yelp after people who install Priceline, so you cannot memorize. Now, one way you can train this is for each unique feature ID, you look up dense embedding vector, and these are initialized randomly. So initially, you'll make a very poor prediction, and you compare the error between your prediction and the ground truth label, and you start adjusting your embeddings, so you predict better and better, right? So over time, the embeddings will act more like automatically extracted features, high-level features that very well describe these base features. So combined with the hidden layers on top of it, you can now automatically learn complex interactions between these base features. Now, we've talked about wide and talked about deep. So when is wide better than deep and vice versa? Right? So we can look into the traffic patterns. So on the left, using the wide model, you're basically learning a matrix to memorize which user install app and impression app combinations correlates with install and which one doesn't. The problem is there are these question marks, which means there are no data to train on. So if you notice that in the rows and columns, there are a lot of repetitive or similar structures you can leverage. So if you map all of these apps onto a lower dimension embedding space on the right, you might have that similar apps, they will be closer to each other in the embedding space. So you can now generalize your prediction to any app in the embedding space, right? And in this hypothetical example, on the left, you will need 22 floats numbers to memorize these interactions, whereas on the right, you only need 20 floats to store the embeddings. Being able to kind of represent the same or even richer information using less number of parameters, meaning you're leveraging the structure of the data better. Now, on the other hand, there are a lot of specific user taste, niche apps, or just exceptions in the app training data, right? So for example, a Sheldon Cooper Bazinga app probably wouldn't make sense to recommend unless the user have seen the show Big Bang Theory, right? So there are all these kind of niche combinations, and if we use a wide model to memorize, you can just use 5 ways to memorize this diagonal matrix in this hypothetical example, right? Whereas if you still try to learn a low-dimensional embedding, then you will still need 20 floats, and now the learner will try very hard to push these irrelevant apps away from each other, but find it very hard to do so in a crowded, low-dimensional embedding space. And what will happen is you will accidentally recommend less relevant apps to the user. And that's partly because, if you have a high-rank sparse matrix like the diagonal matrix on the left, it's theoretically very hard or impossible to find these lower dimensional embedding that will reconstruct the left. Okay? So our idea is very simple. Why not just combine the power of wide and deep, right? So we not only get the combination of memorization and generalization, and in many recommendation systems and search ranking problems, we often want to balance relevance versus diversity as well. So we satisfy our users' need. So that's what we did. We jointly trained a wide linear model and deep neural network simultaneously by backpropagating to both sides at the same time in training. So we connect them to the same loss function and backprop to both sides. Now, you might notice that this is somewhat similar to common ensemble model, but in the ensemble model, you would train two models separately without knowing each other, and only at prediction time, you will combine their predictions, right? So we've been trying both, and what we observed that is doing a joint training, because they know each other in the training time, the wide model only needs to augment what the deep model cannot learn well, and vice versa. So you often get a much smaller model, whereas if you train an ensemble, both models need to be fairly large and self-sufficient model, so their ensemble will make a good prediction. And we're definitely actively working on comparing the performance of both, and we're happy to hear what you find as well. Okay. So this is what we got eventually that was launched into the production of Google Play Apps recommendation. So it's a 3-layer neural networks on the left. And down below, you have your continuous feature and categorical features that feeds into the model. And this is augmented by a cross-product transformation, a cross between the user install app and the impression app, and both are connected to the logistic loss for joint training. And we published this result in the paper previously. We ran online experiments on Google Play, and we've seen that the wide and deep model had a significant 4% gain on our wide model, which is a very mature, highly optimized previous generation model that's been used. And we also compare it with the deep part of the wide and deep model, and it has a 1% gain on top of it. And that's pretty significant for Google Play. Now, the good news is all these you can do today in about 10 lines of code using the high-level estimator API, which Martin and others have talked about. So all you have to do is first define the features you want to use in your wide models, and configure the crosses you think that might be useful for memorizing a lot of combinations. And second part, you define the features you want to use in the deep model and the embedding configurations. And finally, define your model structure, like how many hidden layers, how wide is the hidden layers, and boom, you can start training right away. So I encourage you to go online and search for wide and deep learning to learn more about wide and deep from the resources we provide. So we've open sourced it. We have blog posts, paper, a YouTube video, and also TensorFlow tutorials to walk you through these. And we found it useful for general recommendations, search, and ranking problems, especially if you have sparse categorical inputs with a large number of unique feature values. We're excited to learn if you find it useful in other use cases as well. And finally, I think we all want to learn wider and deeper about machine learning and maybe just everything else. But I think the true power lies in the word together. So in the wide and deep project, we brought two pretty different modeling techniques together on one unified platform, and that benefited many product teams at Google. And by open sourcing and sharing our findings, you and we are now able to collaborate, even if we're not in the same organization. And together, we can get a deeper understanding of how to combine these machine learning technologies with a community that's wider than ever. And I think that's a very powerful thing. So I'd like to thank all the contributors to the Wide and Deep project, and thank you very much for listening to the talk today. Thank you. And now I'd like to introduce the next talk. This is my favorite. Doug, who leads the Magenta project in Google Brain, is going to talk about how to generate art and music with TensorFlow.
Waiting for this live mic to be, there's a live mic. Okay, now for something completely different. I know it's past 5 o'clock and you can't have beer yet, but we'll get there. And in the meantime, we'll talk about music and art generation. My name is Doug, and I'm a team member on the Google Brain team. And I'm going to talk to you about a project called Magenta that's focusing on a really hard challenge, which is generating music and art using deep learning. So why are we here? We're here to ask the question, can we use deep learning and reinforcement learning to generate compelling media? And treating that generally, we're talking about music and images and video and text, for example, joke telling. And this is a hard problem. I missed the keynote this morning, but someone in the audience maybe still is working with robots and painting. Is that person still here? All right, so you know this is hard, right? This is not an easy thing just to generate. But furthermore, we want to generate things that are interesting and are surprising, and we want to measure success. So we want to understand what people are really doing with this media. And I think it's an exciting time to be able to try a project like this, where we have some of the tools available to us that weren't there before, and this is what we're about. So one of the things that we're trying to do is do this out in the open and do this, build a community. So a community of creative coders and a community of artists and musicians to work with us. So everything that we're doing in Magenta is being put into open source in GitHub, in the TensorFlow repo, Magenta repo and TensorFlow. And we're trying really hard to have tools, for example, Jupyter Notebooks, that allow people to really quickly do some things so that we can draw them in and all work on this together. So this is an example of style transfer that's out there. But I think more to the point, and I think the challenge that I want people to leave with, if you're going to think about this problem, and I think it's a problem we're thinking about, a challenge, is understanding just how important it is for these models to be embedded in the world and to get critical feedback. As a thought experiment, you can imagine we train some model that can just generate, tens of thousands or hundreds of thousands of songs that sound just like the Beatles or whatever. It's not very interesting to just think of pushing that button, right? You just keep generating more and more material and it becomes overwhelming. I think more interesting is thinking about making a feedback loop where Magenta is being used by musicians, being used by artists in some interactive way, and also the stuff that's being generated is being evaluated by people. Another way to look at this is with respect to kind of what we can do as engineers and what we can do as artists and musicians. Art and technology have always co-evolved, right? The film camera was initially thought of as this device that is not artistic and is there just to capture reality, and B, something that is kind of not very interesting compared to what painters are doing. And people came along and turned it into an artistic instrument. And you would note that when people turn things into artistic instruments, they tend to try to break them or to use them in ways in which they're not intended. So on the slide you're looking at now, on the left you'll see Les Paul. He's one of the inventors of the electric guitar. Rickenbacker is another. And what they were trying to do with the electric guitar was make it louder so that it could compete with other instruments in a concert setting. And they weren't trying to make it distort, right? And they weren't trying to distortion was a failure case, right? And you have people like Jimi Hendrix above or St. Vincent on the bottom. They come along and they take this technology and they do things with it that are unexpected. And I think that's a really important part of the recipe. What makes, I think, Magenta interesting with respect to this, if you will, is to say, okay, what if we can make something like an electric guitar or like a drum machine or like a camera, but that it itself has some machine learning intelligence. So it's pushing back a little bit. The idea that you might actually have something that you as an artist or a musician can push against, that listens to you, that responds to you. And the question then is, can we, the people on Magenta, probably more like Les Paul or Rickenbacker than like Jimi Hendrix. So I do play guitar, and I am left-handed, so there's a little bit of Jimi Hendrix in me. The basic idea is, can we as engineers build some technology and then create that loop of collaboration with artists, right? Okay. So let's dive into a little bit of research now. Let's talk about a nice problem, image inpainting. How many people in the room are familiar with this basic idea? Okay, quite a few. It's interesting that you chop a chunk out of an image, and then you try to fill it back in. And it's a kind of generative problem, except in one way it's easier than generating an image from whole cloth because you don't have the surrounding context, yet it's also harder because you have to obey the surrounding context. This image is actually research from Pathnak, not from the Magenta team or Google Brain, but I thought it was a great image. You see that the human artist on the upper right has filled in the missing spot quite nicely. Probably those of you that have looked at the recent work in GANs, generative adversarial networks, are aware of this finding that a normal L2 loss will give rise to something kind of blurry and boring and safe, and that you need something like an adversarial network or reinforcement learning to force models to generate away from the mean and do something more interesting. So we had an idea led by Anna Huang, who was a Google Brain intern working with me in the Magenta team, to say, can we compose music using something similar? And this wasn't a one-to-one reuse of inpainting. The idea was that you would take multi-voice music, in this case Bach, and you would then remove voices. A voice is sort of one melodic line, and there are 4 voices in this music. We used Bach because the data was available and because for some reason AI music generation people obsess on Bach, so we did the same thing. And you can either remove part of the score as a chunk, or more interestingly, you can remove a voice at a time. So you remove one voice, and the other 3 voices are providing context, and then using Gibbs sampling, you sample in the missing bits, and then you remove another voice from the original data, and you sample in the missing bits and continue. And so you can do this really interesting conditional generation, conditioned by the original data, or you can simply start with something empty and start to build voices one at a time. And it turns out the sampling helps a lot. So the first thing I'd like to do is just play this. Don't pay attention to the quality of the sound, it's just MIDI. Pay attention to the melody and see if you think there's anything there in what's been generated. So this would be the time to play the video. So it's not perfect, but it's quite interesting. And what's interesting about it, the graph that I'm showing you is from our paper. We compared the 3 different sampling routines to real Bach. And we found that when listeners were asked to rate the music, they actually preferred the Gibbs sampling to Bach himself, thus proving that we're better than Bach, right? Game over. No, what it shows, I think, is that these models capture something interesting. I think the way we put it in listening to them is, of course, it's not as good as Bach, but it captures almost some cartoonish aspects of Bach. It's almost like more Bach than Bach because it's simpler than Bach, but it captures some salient, Bach pieces. I'm also convinced if we had gone out to musical experts, not standard side-by-sides, that we would have found something different. That said, we were happy to see that we had the kind of structure that people just didn't go, God, this is horrible, right? So yeah, more Bach than Bach with very big quotes around either more or Bach. You take your pick. Okay, so now with what little time is left, let's move on to some image-based work. Also some work done in Brain with an intern, Vincent Dumoulin, some style transfer where we can do style transfer very quickly. We participated in Magenta in this project and actually put out on our GitHub some, I think, really nice code for doing style transfer. This was a tweet yesterday from Josh here at Google. Recommended Magenta style transfer code, works out of the box with their Docker image. So I put that in as a plug to maybe get you people to try things out. I also think they're really beautiful images. It's a really nice use of multi-style transform or pastiche. Here's the obligatory video. I believe we'll be at a point where we can do this in real time on device. Also would point out that because there's a nice latent space, you can move back and forth between styles and mix them and match them. This is a Magenta team member's dog. Shout out to Peekaboo. However, I think the main reason, we've all seen a lot of style transfer. I want to point out that at least from the viewpoint of Magenta, the style transfer work that's being done is extremely preliminary. I mean, first, it's really interesting. I think it's really cool that we can do this, that we can pull style from one network and then via convolution apply it to another. But to give you an example of where the challenges lay, we just have a kind of standard style transfer up above, and down below are 4 portraits by Picasso. And what I would argue from looking at portraits by an artist like this is that, when artists are playing with geometry, when they're playing with sort of the deeper geometry of the human face or something else that has to do with deeper structure, it's clear that these convolutional patch-based, pixel-based models are lost. They simply can't do these kinds of transfers. And it turns out that structure, whether it's structure in language to understand meaning across paragraphs, or structure in music, understanding phrases of music that span longer time scales, or structure in art, it all boils down to that, to this understanding of meaning at deeper and deeper layers. And I think that's where the sort of the grail is for us in terms of research. So why TensorFlow? Magenta is a TensorFlow GitHub. We are GitHub/TensorFlow/Magenta. And we're dedicated to being, if you will, the glue between TensorFlow and the artistic community and the music community. It has some real advantages for us. The first one is because it's Python, we're able to work with everything. A lot of working with music and art has to do with just piping data around, being able to do the simple things. It's hard to see in the blue over there, but I just grabbed some of our HTTP archive dependencies. Pretty MIDI and Mito are 2 big MIDI I/O packages that we can just use immediately in Magenta, thus in TensorFlow. We have really fast and flexible image, audio, and video I/O, which is crucial. A lot of our machine learning for even music becomes I/O bound if we're learning from, say, 16 kilohertz audio. It's just a lot of data to move around. We have TensorBoard. Like, if you're not using TensorBoard, you want to be using TensorBoard. Here's a view of just some spectrograms from some audio generation stuff we're working on. It's so nice to be able to, while models are training, sample from them, look for us at their spectra, and listen to them, play with them without having to stop the model training while the model's working. And finally, there's the developer community. There's all of you. So the ability to build out a community of coders and of artists and musicians that can work with us. What's next? Well, first, you could follow our blog at magenta.tensorflow.org. We use the blog to communicate the research that we're doing and to also highlight some code that we've written. And also, please, just if you're a coder, and I guess everybody in this room is, this is a developer conference, give a shout at trying out some things with Magenta. We're just sitting there at GitHub tensorflow.magenta/magenta, and we have Docker install. We also have a pip install. It's all pretty painless to use. So in closing, I want to leave you with this quote. I won't have time to read it all, but there's this beautiful thing at the end. The excitement of grainy film, of bleached out black and white, is the excitement of witnessing events too momentous for the medium assigned to record them. I think the exciting part of Magenta is this idea of actually taking machine learning and its generative capacities and actually connecting it to people and allowing people to experience and work with this. The opportunity to create something like a drum machine, but that actually has some intelligence to it, I think is compelling. I want to thank you for your time. I also want to mention we will have a demo during drinks that is an ability to play along on a piano keyboard with a Magenta piano model. So that could be kind of fun. Stop by. I'll have a beer in my hand, and we can look at that together. And then I'm going to introduce our next speaker, Lily, who's going to talk about TensorFlow and analyzing retinal images to diagnose causes of blindness. Thank you very much for your attention. Cheers.
Hi, everyone. So I'm Lily. I work on our medical imaging team in Brain. And in a previous life, I was a doctor, and I've been repurposed as a product manager at Google. So one of the projects that we've been working on in our group is using deep learning for retinal imaging. In particular, we are looking at a disease called diabetic retinopathy. So that's, other than a mouthful, it's actually also the fastest growing cause of blindness in the world. And it's because this is a complication of diabetes. And diabetes, there are 415 million people in the world with diabetes, and each one of them is at risk for going blind due to what we called DR, or diabetic retinopathy. The key to preventing blindness is regular screening. So every guideline sort of worldwide recommends about once a year screening. And it's because this is pretty asymptomatic until you get to a point where there's irreversible vision loss. And at that point, it's a little too late to intervene. And so this is done by taking a picture using a specialized camera of the back of the eye through your pupil. And then a doctor grades these images. We look for these little hemorrhages and little spots on the image, and we grade them on a sort of 5-class scale from no disease to the end stage, which is sort of proliferative DR. In many places in the world, including in India, where sort of our story originated, there are just simply not enough doctors to do this task. So in India, there's a shortage of 127,000 eye doctors. And because of this and other sort of systematic issues, about half of people actually suffer vision loss before they're even diagnosed. And so for something that's completely preventable, this is sort of unacceptable. And here is a picture of some of people who are waiting in line to get screened. So even if you get to a place where there is screening, there's a long wait, there's long turnaround time. And so a lot of people end up being lost to care. The other issue is that even when available, doctors are surprisingly variable. So here in this graph, each color represents a different class of the category of disease, and each row is a patient image of that fundus image. And each column represents an ophthalmologist. These are US board-certified ophthalmologists, and we had given them this sort of test set when we were kind of trying to attack this problem to see what the grades were for each of them. And as you can see, when there's no disease, there's pretty good agreement. There's one person who thinks otherwise, but everyone consensus is there. And then of course you look at the end stage when there's sort of proliferative disease, there's good agreement there too. But in between, there's actually a lot of variability and disagreement about where this should actually fit, even though there are pretty well-known guidelines. And it's because human beings in general just aren't super great at being very precise about what we see in that image. And of course, you can see the two highlighted rows there in black. These images got every grade in the book, right? So depending on who you saw, your management would be kind of different. So a little bit more about that later. So where we thought we could help was, let's train a model. And so we actually built a labeling tool. We started off with 130,000 images, and we've gotten much more since then. And we hired an army of ophthalmologists to help us label. And from our 54 ophthalmologists, we got 880,000 diagnoses for these images. And you can see from the previous slide why we did that, because sometimes it took up to 7 reads to get something consistent. Then what we did after we got this data cleaned up and labeled, we kind of used our trusty, dusty inception network that works for a lot of image recognition tasks, from cats to puppies to melanoma and now to DR. And we trained it to detect sort of these 5-class predictions, but we also asked it to predict, sort of housekeeping things that might be important for a clinician to know, whether or not this image is of sufficient quality for grading, whether or not this is a left or right eye. Sometimes we get confused, and also the field of view, which is like what part of the retina you're actually seeing. And then we built a front end to this. I'm gonna try a demo here. This is literally what I call a toaster. We try to drag and drop something. I don't know actually how do I move the cursor to, oh, there we are. Okay, so I'm gonna open up a web browser and hopefully that works. And so I'm gonna drag one of our images over. I can't see it. Oh, there we go. And analyzing. it should be faster, but the demo gods, oh, it's cooperating. So here we are able to tell you that there's proliferative disease here. There's no what we call DME, which is a different type of DR. And we are saying that this is somewhere between moderate and severe. And this is indeed something between moderate and severe. So that's a little demo. Let me close out this browser. Oh, I did something bad, I'm sorry. So then I get to stand here awkwardly as we restart. And I'm sorry, you guys have to go through all that again. I just do what the slide says. Excellent. So I kind of showed you how it works, like a case-by-case basis. But then, how does it work sort of over a lot of images? Well, here we actually published and shared sort of how we did this work in the Journal of the American Medical Association. And this is one of the tests or the validation sets that we used. The model was not trained or or tested on this previously. And out of 9,963 images, we actually we predicted whether or not it had referable disease. So the y-axis is sensitivity, the x-axis is 1 minus specificity, and our algorithm and the two black dots, if you can actually see it, is in black. That's our algorithm, and then the little colored dots are US board certified ophthalmologists. And up and to the left is good, and you can see that essentially that we're very close to most of the ophthalmologists in terms of performance. And in fact, if you look at our F-score and you compare the algorithm's F-score to that of the median ophthalmologist, we're sort of in the middle of the pack. And one of the reasons we also decided to publish in JAMA was because we believe that engaging the medical community is really important to get these technologies out into the hands of the people who can actually use them. And so it was actually quite well received. You can see some quotes from real doctors about our work, and so we're really excited about that. So how did TensorFlow help us? Well. Every step of the way, I think, it helped us really start with quick prototyping, right? So we had starter architecture, pre-trained models, and we actually were able to try out different sort of variations of neural networks. And we actually found, we literally found that Inception v3 at this point worked the best, but we could try out things very quickly, and we also pre-trained. So we actually pre-trained on the classic ImageNet, and we found there was a boost in performance there. So it also helped us to experiment at scale. So GPU support and fast training. This allows us to run all these different experiments, different sort of labeling. If we had new labels or different labels, it kind of helped us do that. And finally, what I think is really important is that it really allowed our team to reinvest sort of the efforts. So the blocker was no longer in machine learning and in training, right? That's always been that's been hard to do. And if you look at what we did here, we actually applied very straightforward ML techniques here. What was the magic sauce was actually finding the right problem, getting the data, getting agreement about what was in the image, and then we were able to use sort of this package, these tools that were able to sort of allow us to train the models that actually performed really, really well. And that also then allows our team to focus on validating the algorithm and figure out ways to deploying it into healthcare systems, which in itself is a huge challenge. So what's next for us? We train a model, it works really well. And now we need to actually clinically validate it. We've been working with 2 hospitals in India, Aravind and Sankara, and they're running clinical trials of the algorithm as we speak. Actually, Arvind's finished, and they found essentially the same results, that we were slightly better than sort of the average of their ophthalmologists there. And so what we're doing is working with a fellow alphabet company, Verily, that's a life science-focused company, and a hardware maker called Nikon. You may or may not have heard of that little company. But the idea is, now that the algorithm works pretty well, the bottleneck becomes the hardware, right? Because we need a specialized camera to take these pictures. So we're working with the hardware manufacturers to essentially figure out ways to deploy sort of lightweight hardware that's easy to use, et cetera. So, one of the, taking a step back, one of the main reasons I got into medicine was, I was an MD PhD. And so I really was very excited about bringing sort of breakthrough science from bench to bedside. And there's a part of you when you go through training and your PhD and you're like, this is never going to happen, right? Because it's just not possible to solve these problems. And with TensorFlow and sort of all the work that's been done here, it's actually possible to do that. It's possible to train algorithms that really can help physicians deliver care where people need it most. So that's the end. And with that, I'd like to introduce Zach, who's going to close this out and let us eat food.
Hello again, everyone. Wow, we have covered an enormous amount of material today. And I hope we've convinced you that TensorFlow 1.0 is fast, flexible, and production ready, suitable for all your machine learning needs. But this is just the beginning. As you've seen today, the TensorFlow community is truly global, and we're really interested in collaborating directly with you and in facilitating collaborations among you to extend TensorFlow further, bring it to new platforms, bring it to new applications, and make TensorFlow better for everyone, the whole global community. Now, you've started many interesting conversations today, whether you're here in Mountain View or abroad, and we'd love to continue those conversations. There are a lot of different ways to do that. First and foremost, I would love it if you would fill out the survey that we're emailing now. I know, surveys, but we read every comment, and your feedback is invaluable to help us make even better TensorFlow events in the future. So please take just a few minutes, fill out the survey. We'd also love it if you would keep asking questions on Stack Overflow and filing issues on GitHub. Our teams monitor those closely, and also we have significant participation from the community in looking after the active questions on TensorFlow. You can follow us on Twitter at TensorFlow. That's a great way to find out about the next set of TensorFlow events and also about new releases, news, guides, and tips and tricks, and amazing projects that we spot out in the community. I'd also encourage you to subscribe to the Google Developers YouTube channel, which is where a lot of the videos from today have already been posted, and soon all of today's talks will be posted so you can watch them, freeze frame, and see that code that Pete was putting up in tiny text to help you deploy TensorFlow on mobile. So, Google Developers YouTube channel. Finally, I'd just like to say thanks to everybody who made this an awesome day. I can't possibly name everyone, but I'd like to start with all of our remote viewers, everyone who's tuned in via the live stream. Thousands of you all over the world, thank you so much for spending the time with us today. And thanks to all of the Googlers and the Google developer groups who organized events in so many places to bring so many people together. Next, I'd like to thank all of you here in Mountain View. The room has been packed all day. The energy's been so high. The conversations during the breaks have been great, and you can look forward to continuing those conversations in just a few minutes at the after party. I'd also like to thank our speakers who have prepared these amazing talks, our external guests, and of course, all the many, many, many different teams across Google that have collaborated to make this possible, including the events and production teams that have been operating seamlessly behind the scenes. So finally, I'd just like to say on a personal note, I'd ask each and every one of you who's watching this to go today and figure out how you can do something amazing with TensorFlow. It doesn't have to be big. It can be a tiny thing. It can be a side project. It can be for work. It can be for play. But go out there, do something amazing with TensorFlow, and tell us about it. We'd love to hear it. So let's stay in touch, and I can't wait to see all of you at the next TensorFlow developer event. Thanks very much. Thanks for joining us.